Welcome to The Explainer. Today, we're taking a journey to uncover the hidden, truly awe-inspiring forces that hold our entire universe together. You know, we walk through our world every single day, feeling the solid ground beneath our feet, completely unaware of the terrifying and magnificent invisible battles happening at the microscopic level that literally make our reality possible. We're going to explore the magic of electromagnetism, and I promise you, by the end of this explainer, you will absolutely never look at a piece of iron, a light bulb, or even your own two hands the same way again.
Okay, let's dive into this. I want you to imagine a scenario for a second. You're standing at arm's length from a friend. Normally, you don't feel any physical pull or push between the two of you, right? But what if there was just a tiny microscopic imbalance? What if each of you suddenly had just 1% more electrons than protons in your bodies? Just 1%. You'd repel each other, obviously, but how much?
To really wrap our heads around the scale of that repulsion, let's look at how gravity compares to the electrical force. We all know gravity. It keeps us anchored to the ground. But gravity only attracts. The electrical force, on the other hand, attracts and repels, positive and negative charges. And here is the mind-blowing part. The electrical force is roughly a billion times stronger than gravity. I mean, that is a ridiculous number. But we don't notice it because the positive and negative charges in our bodies and in almost all matter around us balance each other out perfectly. So back to our question. If that perfect balance was disrupted by just 1% at arm's length, the repulsive force between you and your friend wouldn't just be a gentle shove. It wouldn't just be enough to lift the Empire State Building. It wouldn't even just lift Mount Everest. No way. That 1% imbalance would create a repulsive force strong enough to lift a weight equal to the entire planet Earth. Yeah, you heard that right. That is the staggering, unimaginable power of the electrical force hiding inside you right now.
Now, knowing that, you might be wondering, well wait, why don't the positive protons and negative electrons just crash into each other then? Well, that's actually due to quantum uncertainty. Electrons simply can't be pinned down that closely without their momentum just going crazy. But what about the nucleus itself? It's packed with positive protons. Shouldn't it violently explode from that Earth-lifting electrical repulsion? Honestly, it would, if not for nuclear forces. These act like a sort of short-range superglue, but in massive atoms like uranium, the nucleus is so large that the electrical repulsion almost overpowers that glue. If you tap it with a neutron, it splits. The protons fly apart due to that massive electrical repulsion. And this brilliantly illustrates that what we call nuclear energy in an atomic bomb is in reality immense electrical energy finally breaking free.
Section 1. Visualizing the invisible world of fields.
So how do physicists actually make sense of this invisible superpower? How do we calculate something we can't even see? Well, they use fields. A field is a physical quantity that takes on different values at different points in space. Think of a scalar field kind of like a temperature map of a room. Every point has a temperature, but a vector field, which we use for electricity and magnetism, has both a magnitude and a direction at every single point. The easiest way to picture a vector field is to imagine the velocity of a flowing liquid. At every point in the water, the current has a specific speed and a specific direction. Electric and magnetic fields work the exact same way mathematically.
Now, what's really interesting about this slide is how we measure this field using something called flux. Think of flux as the outflow. If this were water, flux is simply how much water pours through a hula hoop you're holding right there in the middle of the river. Mathematically, it's just a measure of the normal component of the vector, the arrows pointing straight through the surface, multiplied by the area of that surface.
Alongside flux, we have another incredibly vital concept, circulation. To explain this, the brilliant physicist Richard Feynman proposed a really great analogy. Imagine a velocity field in a flowing liquid. Now, imagine you instantaneously freeze the liquid everywhere, except inside a closed circular tube.
What happens to the unfrozen liquid that's now trapped inside that tube? Well, because of the momentum of the water that was already moving, the liquid trapped inside the tube would just keep right on circulating. Mathematically, circulation is just the measure of those arrows pushing tangentially along the path, multiplied by the circumference of the loop. Flux and circulation, outflow and rotation. It's like a giant puzzle, and these two simple mathematical ideas literally describe all the laws of electricity and magnetism.
Moving on to Section 2, Electricity meets Magnetism. Let's see how these mathematical rules directly govern the physical, real-world relationship between electricity and magnetism, because the truth is, they're not separate forces. They are absolutely two sides of the exact same coin. Imagine a wire hanging above a standard bar magnet. When we turn on an electric current, the charges inside the wire start moving. The magnetic field from the bar magnet exerts a physical force on those moving charges, and the entire wire actually gets pushed sideways. A magnetic field pushes moving electric charges.
But physics is all about balance, right? If the magnet pushes the wire to the left, the wire must push the magnet to the right. Otherwise, we'd violate the conservation of momentum. The current in the wire creates its own circulating magnetic field, these circular loops going right around the wire. And that circulating magnetic field exerts a force right back onto the bar magnet.
Let's move to and see how this builds. If a wire carrying a current creates a magnetic field, and a magnetic field pushes on a current carrying wire, then what happens if we put two wires right next to each other? Well, they interact directly. If the current runs the same way in both, the magnetic fields cause the wires to physically attract. If the currents run in opposite ways, they repel each other.
This leads us to a truly fascinating realization. We can remove the bar magnet entirely and replace it with a coil of wire. When we run a current through the coil, it acts exactly like the bar magnet did. It pushes the hanging wire. This proves that magnetic fields are just produced by moving electrical charges. So what is an iron bar magnet really? It's simply a material where the electrons inside the atoms are spinning on their axes, all lined up in the same direction, creating perpetual circulating electrical currents. Iron magnets are literally just electric coils on a subatomic scale.
Section 3. Maxwell's Revolutionary Legacy.
So, the crucial point is, this is where James Clerk Maxwell solved a glaring mystery. We know a current in a wire makes a circulating magnetic field, but what about a circuit that isn't a continuous loop? Take a capacitor, for instance, which is just two metal plates with a gap between them. As current flows to the plates, a magnetic field is generated around the gap, even though no physical electrons are moving across the empty space. Maxwell realized that simply changing the electric flux across that gap acts exactly like a current. A changing electric field produces a circulating magnetic field all on its own, with absolutely no wire needed.
Now, I want to blow your mind one more time regarding the true nature of this magnetic force. Think about electrons zipping through a wire. How fast do you think they're actually moving? The speed of light? Not even close. The average speed of electrons moving along a typical wire is only about 0.01 centimeters per second. They are crawling. A literal garden snail could easily outrun the electricity powering your home right now. Because these electrons are moving so incredibly slow, if you apply Einstein's theory of relativity to them, the relativistic correction to their forces, due to their movement, is a minuscule factor of 10 to the negative 25. That's 0.24 zeros and a 1. It's a correction so tiny, so unbelievably small, it should be completely unnoticeable to us. But here is the grand secret of the universe. We absolutely do notice it. Why? Because, as we learned at the very beginning of this explainer, the normal positive and negative electrical forces in a wire cancel each other out with mind-boggling perfection. They balance out so utterly and completely that the only thing left over is that tiny microscopic relativistic correction of 10 to the negative 25. That leftover relativistic effect is what we call magnetism. Magnetism isn't even a separate force, it's literally just the relativistic effect of slow-moving electricity.
And Maxwell's equations showed us the ultimate consequence of this. If a changing electric field creates a magnetic field, and a changing magnetic field creates an electric field, they can trigger a chain reaction. They can leapfrog off each other, propagating right through empty space. We call that radiating chain reaction light, electromagnetic radiation. It is astounding to think that humanity's knowledge went from the ancient Greeks rubbing amber with fur just to attract little pieces of papyrus, to discovering the fundamental equations that gave us the telegraph, the entire power grid, television, and our fundamental understanding of light itself.
I want to leave you with this incredible perspective from Richard Feynman on Maxwell's discovery. He said, from a long view of the history of mankind, seen from, say, 10,000 years from now, there can be little doubt that the most significant event of the 19th century will be judged as Maxwell's discovery of the laws of electrodynamics. The American Civil War will pale into provincial insignificance in comparison with this important scientific event of the same decade. When you turn on a light switch today, consider the invisible, earth-lifting forces and the relativistic magic that just flowed right through your walls. What other invisible forces are shaping our reality right in front of our eyes, just waiting for the next Maxwell to come along and write their equations? Thank you so much for watching The Explainer.
Welcome to The Explainer. Today, we're diving into a truly fascinating intersection of math and reality. We are going to look at how physicists take the messy, incredibly complicated physical world and translate it into elegant mathematics. And we're doing it through the lens of one of the greatest scientific communicators of all time, Richard Feynman. We'll be exploring his intuition-first approach to vector calculus and seeing how grounded physical ideas shape the complex equations that govern our entire universe. So here is our roadmap for today. We're going to cover thinking like a physicist, scalar and vector fields, the gradient and change, the magic del operator, divergence, curl and Maxwell, and finally, heat flow and beyond. Let's jump right in. Section 1. Thinking like a physicist. We are starting with Feynman's highly unique intuition-first philosophy to understanding physics. Okay, let's dive into this with a perfect quote from theoretical physicist Paul Dirac. I understand what an equation means if I have a way of figuring out the characteristics of its solution without actually solving it. This is Feynman's approach in a nutshell. To really understand physics, you can't just blindly crunch the numbers. You need to know what should happen in a given physical circumstance before the math even begins. It's really about developing a gut feeling for the physical reality first. This sets up a really fascinating contrast. You see, a mathematician might look at a dense set of differential equations and think, well, these equations are all there is. If I understand the math, I understand the subject. But they actually get led astray sometimes in physics because they lose sight of the physical world itself. A physicist, on the other hand, absolutely must maintain a true heuristic feel for reality. They use models to keep the actual physical situation perfectly clear in their mind. Moving on to Section 2, Scalar and Vector Fields. Let's build up that physical intuition by looking at the simplest physical fields. The absolute simplest is a scalar field, which is characterized at each and every point by a single number. Imagine a solid block of metal with varying internal temperatures. At any exact point you pick, there is one specific temperature, and that creates a scalar field right across the material. And this brilliantly illustrates the concept. Think of them like a topographic map, but instead of elevation, these imaginary lines, called isotherms, map out where points share the exact same temperature in space. There are arrows tracing the flow of heat too, but we will get to those in just a second. Okay, so that brings us to the vector field. Instead of just a single number, a vector gives us a specific directional quantity for every single point in space. It tells you how much and in what direction. And just like a scalar, this varies from point to point in the real physical world. To picture this, think about the atoms inside a spinning disk. Near the center, they aren't moving very fast. Near the edge, they are flying, but everywhere they have a clear direction of motion. Or alternatively, look at the specific directional flow of heat moving from hot to cold. Those are vector fields in action. Section 3, the gradient and change. Now, before we measure how these fields change as we move through space, I want to pose a conceptual question. Does physical reality actually depend on our coordinate axes? Think about it. If you walk from a hot room to a cold room, the actual physical difference in temperature you feel doesn't change just because someone decided to tilt the imaginary x, y, and z axes we use to measure it, right? The physical reality is totally invariant. It just exists. So the crucial point is how we mathematically track that unchanging physical reality. We use a displacement vector, let's call it delta r, to track the temperature difference between two physically separated points. We can break that movement down into its components along the x, y, and z axes. The actual change in temperature is the rate of change along the x-axis times the x distance, plus the rate along the y-axis times the y distance, and so on. But what happens if we completely rotate our coordinate system to a new set of primed axes? Even if we twist our entire mathematical grid, that underlying physical change, that difference in temperature, remains exactly the same. Because of this, the three rates of change along the three axes transform perfectly as a true physical vector. We call this new vector the gradient. The gradient of a scalar field, like our temperature, is simply a vector that naturally points straight up the steepest slope. Which brings us to Section 4, the magic del operator. This is a real game changer. Meet the del operator, symbolized by an upside-down triangle. On its own, it doesn't represent a number or a standard vector. It's purely an operator. Feynman humorously described it as an operator left hungry for something to differentiate. It basically contains the instructions for finding the spatial rate of change in the x, y, and z directions, just waiting for a physical field to be fed into it. And when we finally satisfy that hungry operator, we get three main combinations, and they are incredibly powerful. First, if we apply it to a scalar field like temperature, we get the gradient, which outputs a vector pointing up the steepest slope. Second, if we take the dot product of del with a vector field, we get the divergence, which outputs a scalar number representing how much the field is spreading out. And third, if we take the cross product of del with a vector field, we get the curl, which outputs a new vector representing rotation. It's literally one tiny symbol giving us three fundamental descriptions of physical change. Section 5, Divergence, Curl, and Maxwell. Now for the grand payoff. These are Maxwell's equations. By using the divergence and curl combinations we just learned, this tiny upside-down triangle elegantly packs the entire classical theory of the electromagnetic field into four remarkably short lines. Just look at how clean it is. The divergence of the electric field relates to charge density. The curl of the electric field relates to the change in the magnetic field over time. The divergence of the magnetic field is always zero. This sophisticated notation strips away all the arbitrary coordinate systems and just shows us the pure physical content of electromagnetism. Finally, Section 6, Heat, Flow, and Beyond. Let's bring this abstract math back to reality. Imagine heat flowing through a slab of material. If you heat one side and cool the other, we intuitively know that heat flows downhill in temperature, from hot to cold. Well, using our new notation, we can perfectly summarize this physical truth. The heat flow vector is simply equal to a constant times the negative gradient of the temperature. That minus sign is there specifically because the heat moves opposite to the steepest uphill slope. It moves downhill. With just a few symbols, we have the complete differential equation for heat conduction, perfectly tied to physical reality. So as we wrap up this explainer, I want to leave you with this final thought. How does a simple change in notation completely transform our ability to comprehend the complexities of nature? We started with a gut feeling about hot and cold blocks of metal, and we ended up with a mathematical framework that perfectly describes both heat flow and the invisible electromagnetic forces that power our modern world. Notation isn't just about making equations look nice. It's about giving us a direct, unclouded feel for the universe. Maintain that physical intuition, and math literally becomes a window directly into reality. Thanks for joining me, and keep exploring.
All right, let's jump right into this explainer. Today, we're looking at how physics takes this messy, swirling, chaotic real world of ours and translates it into, well, elegant math. We're talking about the underlying math that governs everything from how your morning coffee cools down to the way water swirls down a drain. But before we get completely bogged down in the abstract math, we've got to ask, how do we even measure things we can't physically see? Think about it. Radiating heat, invisible electric fields, the hidden circulation of fluids. Well, physicists rely on a very specific set of tools, namely vector integral calculus, to track all these invisible flows. And today, we're going to decode those exact tools.
To make sure this all clicks, we're going to build these concepts up dimension by dimension. So, here's our roadmap for this explainer. First, the math of invisible fields. Second, measuring the outward flow. Third, seeing heat conduction in action. Fourth, we'll dive into circulation and the curl, and finally, we'll tie all these theorems together.
All right, part 1, the math of invisible fields. Let's start with the absolute simplest case and just look at how things change along a basic one-dimensional line.
So, if you want to find the total change in a field, like imagine you're literally hiking up a temperature hill, you just integrate its rate of change. That rate of change is the gradient. It's represented by that little upside-down triangle symbol, and it gives us the exact rate of change at one specific pinpoint spot. Now picture evaluating that rate of change as you move continuously along a path through space, going from point A to point B. At every single microscopic step you take along that curve, the vector gradient is present, and it's always pointing in the direction of the absolute greatest possible change. It's kind of like a mathematical compass for steepness. And this is the whole secret behind a line integral. You see, we don't actually need to tackle the entire curvy, complicated path all at once. Instead, we just chop that curve up into an infinite number of tiny, straight segments. By finding the change across each little microscopic piece and just adding them all up, boom, we get the exact total change from start to finish. It's a remarkably simple idea, but absolutely crucial for everything else we're going to cover. Moving on to part 2, measuring the outward flow.
Let's see how this exact same geometric logic holds up when we jump from 1D lines to 3D spaces, basically asking how much stuff is leaking out of a room.
To really wrap our heads around a concept called divergence, we first need to distinguish between the 3D volume trapped inside a boundary and the 2D surface area of the boundary itself. Think of it like a balloon. The air inside, that's your volume. The rubber stretching around it, that's your surface area. So if we want to know how much air is, say, leaking out of the whole balloon, we actually just need to measure what's passing right through that outer 2D rubber skin.
Now, imagine taking a volume with stuff actively flowing out of it and making an imaginary slice straight down the middle. We just made two smaller volumes, right? Well, the total flow out of the main outer boundary is exactly equal to the sum of the fluxes out of the two smaller pieces. And here's why. Along that shared internal boundary, that new slice we just made, whatever flows out of the left half flows right into the right half. They just perfectly cancel each other out.
So what happens if we keep slicing, shrinking those volumes down into an infinitesimally tiny little box? We hit a massive concept in physics known as Gauss's theorem. It turns out the outward flow or flux from the surface of this microscopic cube is exactly equal to the divergence of the vector times its volume. Divergence isn't just some abstract math term. It is literally the outgoing flow per unit volume being generated at one specific point in space. It's a brilliant way to connect the microscopic generation of a flow to the macroscopic leakage out of the whole boundary.
All right, part 3, heat conduction in action. We've got the 3D math down, so let's ground this in a real physical phenomenon to see how it works in practice.
I actually love this quote because it frames the matter almost like a detective story. If heat is conserved, meaning, it doesn't just spontaneously vanish into thin air, we can track exactly where it's going. If there's a net flow of heat leaving a closed boundary, then the total heat trapped inside that volume absolutely has to be decreasing by that exact same amount, no exceptions. Picture a tiny heat source buried deep inside a solid block of metal. That heat is going to flow outward radially, right? In all directions at once. Because it has this perfect spherical symmetry, we can just mentally draw an imaginary bubble around it. Using those divergence rules we just talked about, the total heat passing through that spherical bubble has to perfectly match the heat generated right at the center point. This incredibly elegant setup lets physicists easily calculate that the heat flux drops off inversely with the square of the distance. It's just one of those really beautiful moments where pure math perfectly matches our physical intuition.
Which brings us to part 4, circulation and the curl. Now we're shifting gears from outward radiating flows to the swirling, rotational circulation of fluids.
So how exactly do we capture a swirl mathematically? Well, we start with a massive, irregular boundary loop, and then we just chop it up into a grid of tiny, manageable squares. From there, we just meticulously add up all their individual circulations. It's a great trick, taking this wildly complex shape and reducing it down to bite-sized arithmetic.
And check this out. Notice the exact same cancellation magic we saw earlier with the 3D volumes? It's happening with these loops too. If you split a large loop into two adjacent squares, the flow along their shared inner boundary goes in opposite directions. So they completely cancel each other out. The only flow left standing, the uncanceled part, is the overall circulation around the outer edge. Scaling this concept way up gives us Stokes' theorem. By breaking a huge loop down into an infinite grid of microscopic squares, we can calculate the curl of every single one. And curl is just what it sounds like, the tendency of the field to rotate at that specific tiny point. When we sum up all those thousands of little inner swirls, the internal boundaries all wash away, leaving us with the precise total circulation around the entire outer border. It's just a perfect bridge between microscopic spin and macroscopic current.
Finally, let's wrap this up in part 5, tying the theorems together. We've conquered the one-dimensional temperature hill, the three-dimensional radiating heat, and the two-dimensional swirling fluid. Let's unite these concepts.
When you look at these theorems side by side like a summary cheat sheet, it's pretty amazing. We can literally translate mathematical operators directly into physical reality. The gradient theorem shows us how a basic line integral gives the total change of a field. Gauss's theorem scales that up, proving that the surface integral of an outward flow perfectly equals the volume integral of its internal divergence. And Stokes' theorem proves that the line integral around a loop is exactly the surface integral of its internal curl. But notice the pattern here? They all share one profound underlying logic. The infinite sum of the tiny internal microscopic parts always gives you the macroscopic behavior of the entire boundary.
I really hope this explainer empowered you to look at the world just a little bit differently today. Because once you actually know the language, you realize the invisible flows of the universe are literally everywhere. I mean, whether it's the Wi-Fi signal radiating invisibly through your living room or the wind currents swirling outside your window right now, it all boils down to gradients, divergence, and curls. So if the universe is ultimately just a giant sum of microscopic math rules, what invisible field are you going to look at differently today? Think about that for a bit, and I'll catch you in the next explainer.
Hey everyone, and welcome to this explainer. Today we're tackling something literally foundational. We're going to demystify electrostatics, and we'll be doing it by climbing Richard Feynman's brilliant conceptual ladder. We're going to start right down in the trenches with raw brute force math, and then step by step, we'll build our way up to this incredibly elegant geometric understanding of the universe. It is an absolutely fascinating journey from complicated to beautifully simple. So here's our roadmap for the day. First up, forces and electric fields. Then we'll look at the electric potential shortcut, move into the bullet analogy in flux, unveil Gauss's law, and finally, visualize the invisible. Right, to begin, we actually need to define our sandbox here. Electrostatics is essentially the study of a perfectly paused universe. Imagine just hitting the freeze dream button on reality, so that every single charged particle is perfectly and permanently fixed in space. Nothing's moving, nothing's vibrating. By completely removing the chaotic elements of time and motion, we can isolate the absolute core mechanics of electricity to really see what's going on underneath the hood. And you might be wondering, why does this paused universe actually matter? Well, as Feynman famously pointed out, all of electromagnetism is contained in the Maxwell equations. Basically, every rule governing our paused universe is the exact same rule that governs moving currents, radio waves, and light. By mastering this simple static setup, we're actually unlocking the fundamental forces that hold our very bodies together and power the entire modern world. It's a big deal. Okay, Section 1. Forces and electric fields. Let's look at the traditional, honestly exhausting way of calculating how electrical charges interact. Imagine a random, uneven blob of electrical charge just floating in space. To find the electric field at just one single point nearby, you'd have to break that entire volume down into microscopic pieces and sum up every individual interaction. Mathematically, you're forced to solve these giant, messy, three-dimensional vector integrals. It's kind of like trying to map out every single gust of wind in a hurricane 1 cubic inch at a time, while calculating exactly how they push against each other. As Feynman notes, this is quite literally a job for a computing machine, not us. And to make matters worse, the forces we're dealing with here are absolutely massive. Take the number 9 billion. That's a rough approximation of Coulomb's constant, which is the giant multiplier dictating the force between charges. Just to put that into perspective for a second, if you had 2 standard units of charge separated by just 1 meter, the force pushing them apart would be 9 billion newtons. That's roughly the force you'd need to lift a whole mountain. So trying to calculate those staggeringly gigantic forces interacting in complex 3D geometry all at once, yeah, that is a seriously heavy lift.
Section 2. The electric potential shortcut.
Thankfully, there's a much smarter, way more elegant way to handle this without totally frying our brains. By simply shifting our focus, we discover a brilliant shortcut. Instead of calculating complex force arrows pointing everywhere in space, let's just look at energy. We just ask, how much energy, or work, does it take to actually carry a small test charge from point A to point B against the electric field? Think of it like carrying a heavy boulder up a steep, invisible hill. We don't care about the wind or the complex vectors, we only care about how much sweat it takes to reach the top. And here's where it gets cool. Whether you take a straight, direct line to your destination, or some staggered, crazy, zigzagging route making loops and weird steps, the magic of the electric field is its path independence. Because moving sideways around a charge requires zero effort, kind of like walking perfectly flat along the side of that hill, the total work done remains exactly the same no matter how wild your route actually is. So here's the ultimate contrast of working smart versus working hard. The brute force method? That requires evaluating 3 separate mind-bending directional equations. But the smart shortcut? We compute just one single scalar number at each point in space representing the total energy, the electric potential. Then we just look at the gradient, which is basically just the math way of measuring exactly how steep our imaginary energy hill is to find the actual force. I mean, it is just incredibly elegant. Section 3, the bullet analogy and flux. Let's step up to the next rung on our conceptual ladder. To help us grasp the heavier math coming up, we use a highly tangible physical analogy. What exactly is the flow of an electric field? Well, Feynman gives us this wonderful thought experiment to make it visible. Imagine the electric field as a constant stream of little conserved bullets shooting out of a positive charge in all directions. Now, if you draw an invisible, closed box in space, how many of those bullets actually pass through it? Well, if a point charge is shooting these imaginary bullets from completely outside our invisible box, pure geometry takes over. Because these conserved bullets travel in perfectly straight lines, every single bullet that enters the front face of our invisible shape absolutely has to exit out the back face. There's literally no other option. Therefore, that leaves us with a net flow or flux out of this box of exactly 0. And even if we tilt to the end surfaces of our invisible box to make things incredibly complicated, the rule still holds perfectly. Sure, a tilted surface has a larger overall area, but it catches the incoming bullets at a much shallower angle, which decreases the intensity by the exact same proportional amount. So pure geometry ensures the flow in perfectly, mathematically cancels the flow out, 0 net flux. Section 4, Gauss's law unveiled. Because we understand that zero flux concept, we can now reach the ultimate trick that completely changes the game. Ask yourself, what happens if we trap the charge, the central gun shooting the bullets, inside our closed box? Now field lines are radiating outward, piercing the surface from the inside out in every single direction, with absolutely nothing coming in from the outside to cancel them out. In this scenario, the net flux is absolutely not 0. To measure this exact flow, let's just wrap the charge in a perfect sphere. And here is the absolute magic of this geometry. As our imaginary sphere gets bigger, the electric field getting hit by the bullets gets weaker by the square of the distance. But the surface area catching those bullets grows by that exact same squared rate. They perfectly cancel each other out. So the radius of the sphere vanishes from the equation entirely. The total flow of bullets is completely independent of how big the sphere is. It literally only depends on the charge trapped inside. This revelation right here is Gauss's law. The total outward flux equals the total enclosed charge divided by a constant, epsilon naught. Guys, this is the master key to electrostatics. It expresses the inverse square law in its deepest, most structurally efficient form. This is exactly why engineers can instantly calculate the electric fields for complex, real-world objects, like long copper wires and giant capacitors, completely bypassing those terrifying impossible integrals we talked about at the beginning. Section 5. Visualizing the invisible. Let's wrap up by translating all these abstract mathematical shortcuts into beautiful, visible geometry. Check this out. Notice how around a single point charge, the solid field lines, our bullets, and the dashed equipotential rings, our energy shortcut, always cross at perfect 90-degree angles. It's a perfectly symmetrical, wonderfully simple system. Now compare that to a dipole, two opposite charges interacting with each other. At just a single glance, this beautiful, complex geometry maps out both the force and the energy of the entire system simultaneously. It's like a giant, perfect puzzle. But I want to leave you with a provocative thought here. Feynman warns us that if we push this bullet analogy too far into dynamic, moving fields, it eventually breaks down and produces mathematical errors. Physical analogies are incredible stepping stones that help our human brains grasp unimaginably complex concepts. But eventually, to truly understand the deepest layers of the universe, we have to let go of the bullets and learn to embrace the pure, abstract mathematics of the fields themselves. Thank you so much for joining me on this explainer, and keep questioning the world around you.
All right, welcome to this explainer. Today we're unpacking the invisible scaffolding of the universe. Seriously, whether you're looking at the super intricate structure of a single atom or the massive chaotic electrical forces inside a raging thunderstorm, there is this hidden mathematical framework holding the whole thing together. So we're going to dive deep into the laws of electrostatics, specifically Gauss's law. We'll discover why the universe literally demands dynamic motion, how physicists use geometric shapes as a kind of cheat code for complex math, and how a physical law that's verified to 1 part in a billion might actually be hiding a massive secret at the very edge of quantum physics. Let's get into it.
So let's kick things off with a bit of a paradox. I want you to picture perfectly empty space. Now, if you take a single positive charge, could you balance it perfectly in midair purely by using the electric fields of other stationary charges around it? Like, say by placing negative charges in a perfect triangle around it. It sounds like a pretty simple physics puzzle, right? You might think, well, sure, if you just arrange the surrounding charges symmetrically enough, the forces will eventually cancel out, and that positive charge will just sit there in perfect, stable equilibrium. But here's the catch. If you actually try it, or if you run the math, you'll find that if that charge is displaced even a tiny fraction, it just shoots off. It turns out there are absolutely no points of stable equilibrium in any electrostatic field. Well, unless you're sitting right on top of another charge.
And this brilliantly shows us exactly why the answer is a hard no. Check out that imaginary boundary drawn around the center point, which we'll call point P0. For our positive charge to be completely stable right there in the middle, the electrical restoring force would have to point inward from literally every single direction. If it moves left, a force pushes it right. If it moves up, a force pushes it down. But Gauss's law, which is one of the foundational rules of electrostatics, states that the total inward flux of an electric field through a closed surface is physically impossible unless there is a negative charge actually sitting inside that boundary. Because there's no charge right at point P0, an entirely inward-pointing field straight up violates the laws of physics. You just cannot balance a charge in empty space.
Now, believe it or not, this impossibility actually shaped early atomic theory. On the left, we've got Thomson's static model of the atom. He basically imagined positive charge as this uniform jelly, with negative electrons just sitting rigidly inside it, kind of like plums in a pudding. But because we literally just proved that static equilibrium is impossible for collections of point charges without the whole thing collapsing, this model had to be completely thrown out. It was a physical impossibility. And this forced the scientific community to adopt the Rutherford-Bohr model on the right, which is totally dynamic. The electrons have to actually orbit the nucleus, kept from falling in by their constant motion, very much like planets orbiting the sun. So the absolutely crucial takeaway here is that matter simply cannot exist as a static, frozen collection of point charges. If electrostatics were the only force at play, the whole universe would just collapse in on itself instantly. Now, even that planetary model had its flaws, because orbiting electrons should theoretically radiate energy and spiral right into the nucleus. The actual true stability of atoms requires quantum mechanics. Thanks to the uncertainty principle, the electron is basically forced to stay spread out in space. If you confined it too closely to the nucleus, its momentum would become wildly uncertain, which would actually give it the energy to escape. So it's motion and quantum fuzziness that are literally the only things preventing our physical reality from instantly imploding.
Section 1. Geometry meets electricity. Now, if everything is constantly moving and constantly interacting, how do physicists actually map these invisible forces without drowning in impossibly complex equations? Well, they use a geometric cheat code called Gauss's law. Instead of calculating the force from every single tiny charge on, say, a long straight wire, physicists just imagine a shape around it. Here, they draw an imaginary cylinder perfectly lined up with a uniform line of charge. Because of the symmetry, the electric field can only point straight outward, right through the curved sides of the cylinder. Suddenly, the math becomes incredibly easy. By just looking at the surface area of the cylinder, Gauss's law instantly shows us that the electric field decreases linearly with distance. So if you move twice as far away, the field drops by exactly half.
But watch what happens if we change the shape. If you have an infinitely flat sheet of charge, you don't draw a cylinder. Instead, you draw an imaginary rectangular box that just cuts right through the sheet. The electric field is forced by symmetry to point straight out, perfectly parallel to the box's sides, and it only exits through those two flat end faces. When you run the numbers on this, you get a wild result. The electric field of an infinite sheet incredibly doesn't change magnitude with distance at all. It doesn't matter if you are 1 millimeter or 1 mile away from this infinite sheet, the force you feel is exactly the same.
And it gets even more interesting for a uniform sphere of charge, which, by the way, is a really good simple approximation for an atomic nucleus. If we draw an imaginary spherical boundary on the outside, it acts exactly like a single point charge at the center. But if we draw our imaginary sphere inside that uniformly charged sphere, the math reveals something entirely different. The electric field inside actually grows proportionally as you move away from the center. Right at the dead center, the field is zero, and it steadily increases in a straight line until you hit the outer edge.
What's really mind-blowing about this is just how elegantly simple the math becomes when you use the right imaginary shape. You don't need supercomputers to figure out these baseline fields. Lines, sheets, and spheres yield these perfectly predictable results, completely bypassing the complex calculus integration you'd normally be stuck doing. Gauss's law proves that the geometry of the source directly dictates the geometry of the invisible force field around it. But all of these beautiful geometric cheat codes rely entirely on one absolutely core assumption: Coulomb's inverse square law.
Section 2, a 1 in a billion proof.
So how do we actually know that this whole geometric framework and Coulomb's inverse square law that it's built on is telling us the truth about reality? Well, look at any random point inside a charged spherical shell. If you draw two opposing cones radiating out from that point, they'll hit the surface of the shell. The cone that goes farther hits a larger surface area. By the rules of geometry, that surface area grows exactly by the square of the distance. Now, if Coulomb's law is perfectly true, the electric force drops by exactly the square of the distance. Because those two things, the area growing and the force dropping, are both tied exactly to the square of the distance, the pushes from both sides completely cancel out to zero. If the electric force dropped off by the cube of the distance, or even the distance to the power of 2.0001, the field inside simply wouldn't be zero.
And the ultimate takeaway here is that this mathematical perfection isn't just some rough approximation. We can actually test this by looking for even the tiniest electric field inside a hollow conductor. Maxwell first proved it to 1 part in 10,000. But then, in 1936, experiments by Plimpton and Lawton proved the inverse square law is accurate down to 1 part in a billion. And later on, Lamb and Rutherford verified that it holds to that exact same billionth level precision, even down at the atomic scale, by looking at the energy states of hydrogen atoms. Seriously, this is one of the most precisely verified truths in the entire field of physics.
Section 3. The ultimate electric shield.
Okay, let's look at how this 1 in a billion precision actually physically protects you every single day. Conductors, like metals, are absolutely full of free electrons that can move around super easily. If you apply an electric field to a chunk of metal, those electrons instantly rush around and arrange themselves until they completely cancel out the field inside. We're talking fractions of a second here. This is a cold, hard fact, proven by touching a little metal ball to the inside of a highly charged spherical shell and then touching it to an electrometer. The meter doesn't even twitch. It gets absolutely zero reading. The field inside the metal and the cavity within it is perfectly, flawlessly zero.
And this reveals the ultimate superpower of conductors. The universe enforces this cancellation rule so incredibly strictly that even in a totally irregularly shaped, lumpy, weirdly contoured empty cavity of a conductor, the field remains exactly zero. The electrons on the surface conspire perfectly to act as an impenetrable electric shield. This is exactly why you can safely sit inside the high-voltage terminal of a 1,000,000-volt Van de Graaff generator without feeling a single thing, or why being inside a metal car during a massive lightning storm keeps you safe. Gauss's law is literally what guarantees your safety.
But I want to leave you with one final, pretty mind-bending thought. We know this perfect inverse square law works brilliantly at the scale of meters and even all the way down to the size of atoms. But when physicists smash protons with energetic electrons at distances smaller than 10 to the negative 14 centimeters, this perfect, beautiful law suddenly seems to fail. The electrical force acts about 10 times too weak. So you have to ask yourself, is the fundamental rule of the universe actually broken at the very edge of reality? Or, as a lot of physicists suspect, is there a deeper, entirely undiscovered structure to matter itself? Maybe the proton isn't a point charge at all, but some smeared-out cloud of mesons and pions. We started by mapping the invisible rules of the universe, but it turns out, at the very bottom of it all, the map is still being written. Thanks so much for joining me on this explainer.
Welcome to the Explainer. Today, we're going on a seriously cool journey. We're going to explore exactly how physicists decode the invisible, abstract world of electric fields and somehow transform that fundamental understanding into awe-inspiring real-world technology. It's literally the story of how abstract math becomes entirely real.
Now, that brings up a pretty massive challenge right out of the gate, doesn't it? I mean, how do you solve a puzzle you can't even see? Electric fields are invisible forces, yet physicists have somehow developed these brilliant cheat codes and mathematical tricks to understand and manipulate them. Let's find out exactly what those cheat codes are.
Okay, let's dive right in. Here's our roadmap for today. First, mapping the invisible. Then, a physicist's clever trick, storing charge with condensers, sharp points and sparks. And finally, seeing atoms.
All right, part 1, mapping the invisible.
So, to really wrap our heads around these complex, large-scale electric fields, we've got to zoom way in to the microscopic building blocks that create these invisible forces in the objects all around us. And that brings us to the concept of a dipole. A dipole is, quite simply, a pair of closely spaced, equal, and opposite electrical charges. Now, you might be thinking, most atoms and molecules are perfectly neutral overall. And they are. But if there's even a tiny separation where the positive and negative charges don't perfectly overlap, it creates a microscopic dipole field.
Let's ground this in the real world for a second. Think about a glass of water. Even though a water molecule is neutral overall, its hydrogen atoms have slightly less of the electron cloud, and the oxygen has slightly more. This means water essentially acts as a tiny dipole. If you look at the vector arrows mapped out here, you're looking at the exact reason why water behaves in the unique, life-giving way that it does. It all comes down to this microscopic charge separation.
Now here's a really fascinating mathematical quirk. If you have a single-point charge, its electric field drops off proportionally to the square of the distance. But because the dipole has two opposite charges sitting right next to each other, their fields actually partially cancel each other out. Because of that, the electric field of a dipole drops off incredibly fast, specifically as the cube of the distance, or 1 over r cubed. This means the dipole field is super powerful up close, but it vanishes in a flash as you move away.
Moving on to part 2, a physicist's clever trick. Okay, so point charges and dipoles make sense, but let's shift gears and look at a very practical problem. Real-world physics isn't just floating dots, we have giant sheets of metal, curved surfaces, and totally arbitrary shapes. So how on earth do we calculate the messy, complicated fields around charged conductors? Well, if we do it the hard way, we'd be calculating complex surface charge integrations forever. Nature balances these charges out until the surface is a perfect equipotential, but modeling that is mathematically brutal. So physicists invented a literal cheat code, the clever way. It's called the method of images, and it basically involves pretending there's a phantom image charge sitting behind the surface.
And this perfectly illustrates what I'm talking about. Notice how a positive charge sits in front of a flat grounded plate. Calculating that resulting field seems impossible. But if you just pretend the plate isn't even there and instead place a perfectly mirrored negative image charge at the exact same distance behind where the plate used to be, the math magically works out. The field lines exactly match reality. It's just an incredibly elegant shortcut.
And the best part? This elegant trick isn't just for flat planes. It actually works to calculate the messy fields around conducting spheres too. By calculating the correct distance and strength to place an image charge inside the sphere, we can perfectly model the equipotential surface of the sphere's exterior without writing out a single impossible integration. It's a huge testament to human ingenuity.
All right, part 3, storing charge with condensers.
Let's step out of abstract theory for a minute and into tangible reality. How do we actually intentionally manage and harness these fields to do work for us? The answer is the condenser, or what we now commonly call a capacitor. Check out the uniform field trapped between the plates here. By taking two large parallel metal plates and separating them by a tiny distance, we can put equal and opposite charges on them. The charges are heavily attracted to each other across the gap, spreading out uniformly. And this creates a perfectly uniform electric field safely trapped between the plates, which allows us to store massive amounts of charge without the voltage spiking dangerously high.
Now, why does this invisible trapping of charge matter to you and me? Honestly, because without this specific application of physics, the modern world just wouldn't exist. This ability to safely store and release charge drives everything. We're talking the simple wax and foil condensers in old radios, the massive power supply filters running your household appliances, resonance circuits, and even the fundamental memory inside the computer or phone you're using right now.
Which brings us to part 4, sharp points and sparks.
Let's raise the stakes a bit. Condensers use nice, flat, parallel plates. But what happens when a conductor isn't perfectly flat and we introduce a sharp point? This is where we encounter the sheer, raw danger of high voltage. Remember, charges on a surface desperately try to spread out and push away from each other. When you have a sharp tip, kind of like the small sphere in this approximation model, the charges get shoved all the way to the tip. Because the area is so ridiculously small, a relatively small amount of charge creates a massive surface density. And high charge density means abnormally high, violently intense electric fields right at that sharp point.
And that gives us a fundamental rule of thumb in electrostatics. The smaller the radius of the curvature on your object, basically the pointier it is, the more insanely intense the electric field becomes at that surface. This is exactly why lightning rods are pointed, and conversely, why high-voltage scientific equipment has to be perfectly smooth and rounded to avoid disastrous accidents.
So the crucial point here is how this high field actually creates a spark. It's essentially a massive chain reaction. Step 1, that intensely high field grabs a random loose charge in the air and accelerates it to incredible speeds. Step 2, that hyperfast charge slams into a neutral air atom, knocking an electron completely off it. Step 3, now you've got two charges accelerating, which hit more atoms, knocking off more electrons, creating this massive glowing avalanche of ions. And that right there is what we call a spark or high voltage breakdown.
And finally, Part 5, seeing atoms with the microscope.
Now, sparks and high-voltage breakdowns sound like huge problems, right? Well, here is the absolute climax of this explainer. Physicists ingeniously weaponize the sparking problem to create a true scientific miracle. On the left, we have our sharp point with its intense field. On the right, we have the field emission microscope. Physicists put an incredibly fine, sharp metal needle inside a vacuum glass bulb coated in fluorescent material. They apply massive voltage. The field at the tip becomes so intensely high, literally millions of volts per centimeter, that it rips electrons right out of the metal tip and shoots them straight across the bulb onto the screen, glowing exactly where they hit. It literally projects an image of the needle's tip onto the glass.
There was just one catch. The image using electrons was kind of blurry because of quantum diffraction and random heat movements. But scientists figured out a brilliant workaround. They realized that by reversing the polarity and pumping a tiny bit of helium gas into the bulb, they could use heavier helium ions instead of electrons. Because helium ions are heavier, they don't smear around as much from thermal energy. And just like that, the resolution of the image absolutely skyrocketed.
And when I say skyrocketed, I mean they hit magnifications of up to 2 million times. 2 million! That was a magnification 10 times better than the absolute best electron microscopes of the era. The invisible electric field we started with was now acting as the greatest magnifying glass in human history.
Which brings us to this incredibly profound realization. By mapping these tiny dots on the fluorescent screen, humanity crossed a major threshold. The arrangement of the glowing spots literally showed the individual atomic structure of the tungsten needle. As the quote points out, the field ion microscope provided human beings with the means of seeing atoms for the first time. We traveled all the way from abstract math and invisible fields to literally gazing directly at the building blocks of the universe.
And that leaves us with something pretty incredible to chew on. By mastering the abstract and manipulating the totally invisible electric field, human ingenuity allowed us to finally see the atom with our own eyes. So I'll leave you with this. As we continue to decode the hidden rules of the universe, what invisible puzzle will human ingenuity solve next? Keep questioning, keep looking closer, and thanks so much for joining me on this explainer.
Welcome to the Explainer. Okay, let's dive into this. Have you ever stopped to wonder what forces are secretly holding our physical world together? Or, what unseen hands guide the technology we use every single day? We are literally surrounded by invisible architects. Electric fields aren't just boring lines in a textbook. They're these incredibly dynamic hidden structures that shape literally everything. We're talking about the vast natural wonders of our upper atmosphere, all the way down to the microscopic folds of our own biology and right into the everyday electronics sitting in your pocket. So today, we're going to pull back the curtain and take a look at the blueprints. Here's our roadmap for today. We'll start with the math of invisible fields. Then we'll move into plasma and radio, shrink down to explore colloids, salts, and proteins, and finally wrap up with the electrostatic grid shield. All right, Section 1, the math of invisible fields and the quote-unquote magic of complex variables. Before we can actually build real-world technology, we need a way to map these unseen forces. And in physics, there's a mathematical miracle that gives us an automatic trick for doing exactly that. To solve for electric fields in 2 dimensions, we use complex variables. Whenever you write a function with a complex variable z, it automatically splits into a real part, u, and an imaginary part, v. What makes this so miraculous is that both u and v will automatically satisfy Laplace's equation. In plain English, this means any complex function you can dream up automatically generates perfect, physically accurate electric field maps right out of thin air. You literally just make up the function, and the math hands you a real-world electric field. Now, what's really interesting here is what happens when we use a simple squared function. If we take our complex variable and just square it, the resulting u and v functions plot out this beautiful, almost artistic pattern of rectangular hyperbolas. The solid lines and the dashed lines cross each other at perfect right angles. It looks like modern art, sure, but this specific geometric pattern is incredibly useful. Now you might be wondering, so what? It's just a neat math trick. But this directly translates to the physical world. We can see how this exact hyperbola pattern maps the electric field perfectly into the inside corner of a metal conductor. And even cooler, by shaping 4 metal electrodes into exactly these hyperbolic curves, physicists create a quadrupole lens. They generate a precise electric field where the pole gets stronger the further you move from the center. This is the exact technology used to focus high-energy particle beams in advanced physics labs. The elegance of this rule is it's absolutely crucial. As the source material notes, whenever we choose a function f of z, we get from u and v both the equipotentials and field lines. It's basically a 2-for-1 deal. The solid lines give you the voltage mapping, the equipotentials, and the dashed lines running exactly perpendicular give you the directional pole, the actual field lines. Moving on to Section 2, Plasma Oscillations and Radio, the bouncing electrons. Let's step out of the pristine world of abstract math and into a much more dynamic, chaotic environment. We're going up into the Earth's ionosphere, where gases are just bombarded by the sun and turned into a soup of free electrons and heavy ions. In a plasma, those heavy positive ions mostly just sit there, but the tiny electrons are completely free to move. If you disturb them, say by squishing a bunch of them together, they violently repel each other. As they rush away to find equilibrium, they pick up kinetic energy and actually overshoot their mark. Then the electrical forces pull them back. They literally bounce back and forth, sloshing around. It's incredibly similar to how a sound wave travels through the air, but here the restoring force isn't gas pressure, it's the raw electric force itself. This bouncing happens at a very specific natural rhythm that's totally based on the density of the electrons. We call this the plasma frequency. So the crucial point is that this specific frequency acts like a giant invisible bouncer at the door of the ionosphere. It fundamentally dictates how radio waves are going to interact with our sky. Think about it like this. If you try to send a radio wave up into the sky, the ionosphere's plasma frequency decides its fate. If you use a high-frequency wave, one that's vibrating faster than the plasma frequency, the wave punches right through the plasma and out into space. That is exactly how we communicate with satellites. But if you use a lower frequency, the wave simply cannot penetrate. Instead, it gets reflected right back down to Earth. This is a real game changer because it's how AM radio stations can bounce their signals over the horizon to be heard thousands of miles away. And here's a truly mind-bending fact from the source material. Plasma oscillations don't just happen in the thin gas of space. They happen inside solid metals, too. A solid metal is essentially just a contained plasma of positive ions and free electrons. Back in 1953, it was confirmed that if you shoot electrons through a solid aluminum foil, they actually lose energy in exact, discrete quantum jumps. Why? Because as they crash through, they excite the exact same kind of plasma oscillations inside the solid metal. Okay, Section 3, Colloids, Salts, and Proteins, Chemical Shields. Let's shift our mental camera away from the massive sky and solid metals down into the wet, microscopic world of chemistry and biology, and this brilliantly illustrates what's going on down there. Imagine a microscopic, positively charged particle floating in water that has some salt dissolved in it, an electrolyte. Naturally, that positive particle attracts negative ions from the water. You can see how the electric potential of that particle drops off as you move away from it. The particle literally wraps itself in an invisible, tight sheath of oppositely charged ions, effectively masking its own electric field from the rest of the liquid. The physical thickness of this protective ion sheath actually has a specific name, the Debye length. The higher the concentration of ions in the water, like for instance if you add more salt, the shorter this length becomes. That protective sheath gets tighter and thinner. Normally, microscopic particles in a suspension stay perfectly separated because their electric fields push away from one another. But let's walk through what happens when you add salt. Step 1. The particles are happily repelling each other. Step 2. You add salt, which decreases that Debye length we just talked about. Step 3. The protective electrical shields around the particles become incredibly thin. And finally, Step 4. Without that strong repulsive shield keeping them safely apart, the particles randomly bump into each other, stick together, and literally precipitate out of the liquid as heavy lumps. Chemists call this salting out. And guys, this exact same electrostatic principle governs your own biology. Proteins are basically these long, flexible chains of amino acids that carry negative electrical charges. Because these negative charges repel each other, the protein chain stays nicely stretched out and suspended in your cellular fluids. But if you change the salt concentration, you shrink that Debye distance, the repulsive forces get shielded, the chain suddenly crumples and coils right up, and the protein precipitates out. invisible electric fields are quite literally dictating the shape of the building blocks of your body. So far, we've seen how these invisible fields behave in the vacuum of space, in solid foils, and in the wet liquids of our biology. But what happens when we try to actively control them using everyday's solid metal? That brings us to Section 4, the electrostatic grid shield, the wire mesh. Let's move to and see how this builds from the ground up. If we have a flat grid of evenly spaced wires, right near the individual wires, the electric field is wavy and completely chaotic, dipping in and out around every single wire. But look what happens as you move just a short distance away. Those wild, wavy fluctuations rapidly smooth out, and the field becomes perfectly flat and uniform. The math behind this smoothing effect is honestly astonishing. The fluctuation of the electric field drops by a factor of e to the power of -2 pi for every single grid spacing you move away. That is a massive exponential drop. It basically means that any leakage or waviness in the electric field dies out incredibly fast. If you're just a few wire spacings away, the field acts as though the grid is just a completely solid sheet of metal. So, what's the ultimate practical takeaway here? Well, because of this rapid mathematical decay, a cheap, lightweight copper screen full of physical holes works just as well as a heavy, expensive solid sheet of metal for electrostatic shielding. The electric field simply cannot penetrate through the holes before it exponentially decays to zero. This is exactly why sensitive electrical equipment is surrounded by simple wire mesh. It literally acts as an impenetrable wall to electric fields. We've journeyed from elegant mathematical tricks to the plasma in the upper atmosphere bouncing our radio signals, down to the salty fluids folding the proteins in our blood, and finally over to the simple copper mesh protecting our daily devices. These forces might be totally invisible, but they really are the true architects of our reality. So as you go about your day, I'll leave you with this. Where else are invisible electric fields secretly shaping your world? Thanks for joining me on this explainer, and keep exploring. Welcome to this explainer. Man, I am absolutely thrilled you're joining us today because we are going to dive into some of the most mind-bending mysteries of electrostatic energy. We're going to look at exactly how physicists take abstract math and use it to predict the real physical world around us. So get comfortable, focus in, and let's get started. So we've got to start with a pretty massive question. How exactly do we measure the invisible forces that literally hold our universe together? I mean, it's super easy to understand a hammer hitting a nail, right? But calculating the energy of stuff we can't even see, that's a whole different ballgame. Energy conservation isn't just about rolling balls down hills in high school physics. It's actually the master key to unlocking the microscopic world. Today, we're going on a bit of a detective's journey. We're moving from the literal salts on your kitchen table down into the dead center of an atom, and finally, we're going to uncover a massive, reality-breaking flaw in physics that, believe it or not, still exists to this day. All right, let's jump right into part 1, the rules of attraction. Now, before we go breaking physics, we really need to nail down the basic rules of how electric charges interact. And honestly, the foundational rule here is brilliantly simple. If you've got a bunch of charges just floating around, the total electrostatic energy of that whole system, it's just the sum of the energy of each individual pair. You basically calculate the work it takes to bring every single pair together from, an infinite distance apart, and then you just add them all up. And it's really cool to see how this builds when we're dealing with continuous objects, like, say, a solid uniform sphere of charge. Instead of counting individual tiny points, just imagine assembling this sphere layer by layer, kind of like building an onion. You calculate the work done to bring in a thin spherical shell from infinity, wrap it around a core, and then you just mathematically integrate those layers from the center all the way out to your final radius. It gives us this really beautiful, elegant formula for the energy of a sphere. Moving right along to part 2, work, force, and capacitors. Okay, so we've got our math rules, but how do we actually translate all that abstract energy into real mechanical force, the kind that actually moves stuff? Well, we use this clever trick called the principle of virtual work. Picture the two charged plates of a capacitor. If we want to find the force pulling them together, we just imagine moving them apart, just by a tiny, microscopic virtual amount. We calculate the mechanical work that imaginary little nudge would take, and then we equate it to the change in the system's overall electrostatic energy. It's like magic. Just by imagining a tiny physical displacement, we can mathematically reveal those hidden forces. But you know what's really fascinating? It's what happens right exactly at the surface of those plates. If you actually crunch the numbers on the force, you end up with this weird factor of 1/2. Why? Well, it turns out the electric field isn't totally uniform right where those charges live. As you physically pass through that microscopic layer of surface charge, the field actually varies. It goes from absolute zero on the inside of the metal conductor to full strength on the outside. So the average field acting on those specific charges is exactly half. The math just perfectly, beautifully matches the physical reality.
Which brings us to Section 3, the energy of salt. Let's put all this theory to the ultimate test with a real-world chemical mystery. Like, what exactly is holding a tiny grain of everyday table salt together? Picture a massive, three-dimensional checkerboard grid made of positive sodium and negative chloride ions. To figure out the energy holding that whole crystal together, we just apply our very first rule. We mathematically sum up the electrostatic pull between all these infinite pairs of ions. We calculate the intense pull from the nearest neighbors, then the slight push from the next layer out, and so on, basically out to infinity.
And here's the kicker. When theoretical physicists do all that heavy math, tweaking it just a tiny bit for the natural squishiness of the atoms, they get a predicted energy of 7.99 electron volts. Now, when chemists go into the lab and experimentally measure the actual energy it takes to break that salt apart, they get 7.92 electron volts. I mean, wow, that is a massive triumph. It absolutely proves that our pure, theoretical math on a chalkboard can accurately predict the very real physical properties of macroscopic substances we can actually touch and feel.
All right, let's go even deeper. Section 4, Secrets of the Nucleus.
We're zooming way, way in now, leaving the atomic scale and entering the extreme, microscopic world of the atomic nucleus itself. Now, for decades, physicists were really crossing their fingers that the strong nuclear force, the stuff holding protons and neutrons together, would be simple. Spoiler alert, it is not. The force between two protons actually changes completely depending on whether their spins are aligned parallel or anti-parallel. It's almost staggering how complex this gets. Seriously, the nuclear force is just wild. It attracts at large distances. It repels at short distances. It depends heavily on the orientation of the proton's spin. It changes based on the direction they're separating. Oh, and it's even strongly affected by how fast the protons are physically moving. It is literally as complicated as a physical force could possibly be.
But wait, because here is the incredible plot twist. Consider the energy levels of a boron-11 nucleus, which has 5 protons and 6 neutrons, and then compare that to carbon-11, which flips it to 6 protons and 5 neutrons. Their energy levels are nearly identical, and this reveals a really profound truth. Despite all that wild complexity we just talked about, the strong nuclear force between two neutrons is exactly the same as the force between two protons. You can basically swap a neutron for a proton, and the complex nuclear dance barely changes a beat.
So here's the crucial so what of all this. If those nuclear forces are totally identical, why is there any energy difference at all between boron-11 and carbon-11? Well, it's purely because carbon-11 has that one extra proton, which brings extra electrostatic repulsion into the mix. And by using that simple onion sphere math from earlier to calculate that extra electrical push, we can predict the actual physical radius of the nucleus to within a 15% margin of error. Let that sink in. Our basic electrical laws work perfectly, even down to a scale of 10 to the negative 13 centimeters. That's just mind-blowing. Which naturally leads us to Section 5. Where does energy live? This brings us to a truly profound, almost philosophical question. We've been calculating all this energy, right? But where is it actually located in the universe? We instinctively think of energy as living inside the objects themselves, like packed inside those little charged particles. But the math opens the door to a completely mind-bending alternative. The energy doesn't just live in the charges, it actually resides out in the empty space around them. It lives exactly where the electric field is. We call this concept energy density. Basically, for every tiny cubic unit of empty space that has an electric field passing through it, there is a specific, measurable amount of energy physically packed into that void. And grasping this is absolutely crucial, because later on in physics, we learn that energy actually has mass, and mass creates gravity. So if we couldn't pinpoint where the energy of a field literally lives, our entire theory of gravity would be totally broken. It would be completely incomplete. And that sets us up for our final act, Section 6, the point charge paradox. Okay, so locating energy out in the field, that leads us straight into a massive reality-breaking roadblock. Think about it. If energy lives in the electric fields, we have to calculate that field energy for every single charge. But what on earth happens if we calculate the energy of a single infinitesimally small point charge, like an electron? Well, as you get closer and closer to a true microscopic point, the electric field gets infinitely stronger. If you mathematically integrate that energy density down to a radius of exactly 0, the total energy comes out to infinity. Infinity! That is a mathematical and physical impossibility. You literally cannot have infinite energy stuffed into a single electron.
Which leaves us staring down a pretty gripping question. Is our entire fundamental theory of electricity just broken at these incredibly small scales? Does the electron actually have a hard physical radius we don't know about, or does the local conservation of energy just completely break down? This paradox, this infinite self-energy for point charges, is a fundamental glaring difficulty that exists in physics to this very day. So we've journeyed from a simple grain of table salt all the way to a literal flaw in the fabric of how we understand the universe. Pretty wild, right? Keep exploring, keep questioning, and I will catch you in the next explainer.
Welcome to the Explainer. So today we're jumping right into something completely wild. We are going to explore a massive, invisible electrical machine that surrounds us every single day. I mean, we literally walk through it, we breathe it in, and yet we almost never notice it. Let's uncover the incredible mechanics of Earth's atmosphere and the staggering electrical currents humming right above our heads.
Right off the bat, here's the core mystery we're unpacking today. Picture this. On an ordinary, totally clear day, if you just step outside, there is a vertical electric field of about 100 volts per meter right there in the air. This means that technically speaking, the voltage potential at the height of your nose is about 200 volts higher than down at your feet. So, why aren't we powering our light bulbs with the air? And more importantly, why don't we get zapped the second we walk out into the street?
Okay, let's dive into this. The answer is actually pretty simple. Your body is a really good conductor. Ordinarily, the electrical lines in the air run perfectly parallel to the ground. But when you stand outside, you and the Earth essentially form one continuous conductive surface. So your body actually distorts those electrical lines around you, warping them, and that keeps the voltage difference between your head and your feet at very nearly 0, which, thankfully, protects you from a 200-volt shock.
Section 1. Earth's leaking battery. So here is the huge planetary problem we face. Because cosmic rays from deep space are constantly bombarding us, the air actually conducts electricity just a little bit. It's not a perfect insulator. And because of that, there's a constant current of positive charge leaking straight from the sky all the way down to the surface of the Earth. Globally, this downward flow totals a massive 1,800 amps. To put that into perspective, our planet is basically operating as a 400,000-volt system, pulling about 700 megawatts of continuous power.
And here is where the dramatic tension really builds. With 1,800 amps of current constantly leaking out of the sky and discharging into the Earth's surface, the Earth's entire negative charge should be completely neutralized. And I mean fast. At this rate of leakage, it should take only about 30 minutes for our whole planetary battery to completely run flat.
Yet, look around. The Earth obviously hasn't lost its charge. So we arrive at the central detective question of this whole explainer. If the Earth is constantly leaking its charge every half hour, what on earth is pumping it back up? Where is the hidden generator keeping the sky positive and the ground negative? Now, what's really interesting about this slide is the ultimate clue it gives us, which scientists actually found over the oceans. When they measured this global electrical current, they realized it fluctuates in perfect unison by about 15% every single day. And get this, no matter where you are on the planet, whether you're in the Pacific, the Atlantic, the Arctic, the voltage reaches its absolute peak at exactly 7 p.m. absolute London time. So whatever is charging our planet operates on a single global clock.
Section 2. The Thunderstorm Generator.
The magnificent culprit that perfectly solves our time zone puzzle is the global network of thunderstorms. Think about this. Every single day, there are roughly 40,000 thunderstorms crashing across the globe. Together, they are producing something like 100 lightning flashes every single second. These storms are acting as giant batteries, actively pumping negative charge down to the Earth. And the peak of all this worldwide storm activity, you guessed it, it perfectly matches that 7 p.m. London time peak we saw in the global electrical readings.
Section 3. Inside a storm cell.
Let's move to this and see how it builds. To really understand how a storm can power a whole planet, we have to zoom in and look inside a single thunderstorm cell. In the very early stage, warm, moist air right near the ground begins to rise. As it goes up, it naturally expands, cools down, and the water vapor condenses into clouds. Now, this condensation releases heat, which creates this massive updraft. It physically pulls in surrounding air from the sides and builds a towering thunderhead at intense speeds. We're talking up to 60 miles an hour.
Then things get serious as we hit the mature stage. Those water drops are carried so high up into the atmosphere that they supercool and freeze into large ice particles. Once they get too heavy, they finally fall, dragging all that freezing cold air straight down with them. And that creates a violent, totally self-sustaining downdraft. So now, you have this chaotic, churning system of intense updrafts, rapid downdrafts, heavy precipitation, and absolutely extreme turbulence.
Finally, we reach the late stage, the end of the storm's life. The updraft basically starves as it runs out of that warm surface air. The rain finishes dumping all its water, things start to quiet down, and those high-altitude winds smear whatever ice crystals are left at the top out into this wide, flat anvil shape. And with that, the storm cell dies out.
But actually, scratch that. It's during that chaotic middle phase, the mature stage, where the real magic happens. It's a process known as charge separation. For the storm to actually act as a generator, it has to physically rip positive and negative charges apart. A guy named C.T.R. Wilson, a brilliant physicist, proposed one of the best models for exactly how this works.
It goes like this. Because the Earth below is naturally negative and the sky above is positive, falling water drops or ice crystals develop an induced polarity. Basically, the negative Earth repels the electrons to the top of the water drop, which leaves the bottom of the drop positive. As these polarized drops fall through the sky, their positively charged undersides attract and catch these large, slow-moving negative ions floating around in the air, physically dragging a massive amount of negative charge downward.
And this brilliantly illustrates the final setup of our battery. The positive charges get blown all the way to the top of the cloud, while the heavy negative charges collect ominously at the bottom. This creates an absolutely terrifying potential difference. We're not talking about a couple of volts here. We are talking about a gap of up to 100 million volts between the dangerously negative bottom of the cloud and the Earth below.
Section 4. The Anatomy of Lightning.
Which brings us to the explosive climax of the explainer, the exact moment the tension breaks and the battery discharges. When that voltage gets too high, the air literally breaks down. The stats of a single lightning bolt are just staggering. A strike carries a peak current of about 10,000 amps, and it dumps 20 to 30 coulombs of raw negative charge directly into the ground. But what's even more shocking? The storm's ability to recover. A thunderstorm can completely regenerate that massive lost charge in just 5 seconds. Literally 5 seconds, and it's ready to strike again.
Now, lightning doesn't just fall out of the sky all at once. It starts with this invisible thing called a step leader. It nervously shoots down from the cloud at a sixth of the speed of light, pausing every 50 meters or so just to find the path of least resistance. It's feeling its way down. But the split second it touches the Earth, it creates a fully conductive wire. Then, boom, the real flash, the return stroke, shoots massive amounts of negative charge straight up from the bottom of that established column, creating the blindingly bright light and the intense heat that gives us thunder.
So the crucial point is that the storm often isn't quite finished yet. Just milliseconds later, subsequent strikes, which we call dart leaders, shoot all the way down that exact same ionized path, but this time they do it without pausing at all. This is exactly why you see lightning flicker in the sky. It's literally just the storm repeatedly dumping more and more charge down that same established conductive channel.
You know, over 2,400 years ago, Artabanus, who was an advisor to the Persian king Xerxes, observed that lightning always seemed to strike the tallest buildings and trees. Well, today, we know exactly why this happens. It's because as that step leader descends from the sky, tall objects on the ground emit upward brush discharges, rising up to meet it. Our physics have certainly evolved over the centuries, but our absolute awe of this global electrical machine, that remains exactly the same. So the next time you step outside into that invisible 400,000-volt field, ask yourself, if the Earth's atmosphere is really just a giant, humming battery, could we, one day, learn to plug into it?
Welcome to The Explainer. Today, we're unraveling the microscopic choreography of matter to understand how insulators secretly manipulate electricity. We're going to look way beyond the surface of everyday materials and really uncover the invisible forces at play. I mean, we've all seen this, right? You run a plastic comb through your hair on a dry winter day, hold it over some completely uncharged scraps of paper, and boom, they magically jump right up to meet it. It's a classic parlor trick. But think about it for a second. How does something with absolutely zero net charge feel an electric pull at all?
Exploring exactly why a charged object attracts completely neutral paper actually unlocks the hidden mechanics of electromagnetism. So here's our roadmap for solving this little scientific mystery. First, Faraday's dielectric discovery. Second, the atomic secret. Third, the polarization vector. Fourth, rewriting Gauss's law. And finally, forces in real life. We'll shift from everyday stuff down to the atomic scale and back again. Let's get into it. Section 1, Faraday's dielectric discovery. We're starting with a highly counterintuitive observation made by the legendary Michael Faraday regarding capacitors. Remember, at their most basic, capacitors are simply devices used to store electric charge, usually just two metal plates separated by a gap. Well, Faraday discovered something absolutely fascinating. If you take an insulating material, what we in physics call a dielectric, so think glass or plastic, and you literally just wedge it directly between the plates of a charged capacitor, the capacitor's ability to store charge mysteriously increases. If you look at this setup, the plates hold their original charge, but when that insulator is inserted, the total voltage between the plates actually drops. And since capacitance is just the ratio of charge to voltage, a lower voltage means a higher capacitance. But how? How does an insulator, something that intrinsically doesn't let charge flow, affect the electric field spanning that gap? The really crucial point here is that this performance boost is highly specific to the material you use, and it's quantified by something called the dielectric constant. We represent this with the Greek letter kappa. Now, the dielectric constant of a vacuum is exactly 1, but fill that gap with the dielectric, and the capacitance is multiplied by kappa. For the longest time, physicists seriously struggled to explain how a seemingly inert block of plastic could just absorb or cancel out an electric field. Figuring this out literally changed everything about how we design electronics today. Which brings us to Section 2, the atomic secret. To understand what's actually happening inside that insulating material, we can't just look at the block as a whole. We've got to zoom way, way down. Early physicists knew that if they shoved a solid block of conducting metal between the plates, the field inside the metal would just drop to 0. So they kind of guessed that insulators must be filled with tiny isolated conducting spheres separated by idealized insulation. The idea was that these little spheres reacted to the field, creating miniature charge separations. It's a neat idea, but actually, scratch that, this model didn't perfectly match physical reality. It implied the material had specific, rigid grid-like axes, when in fact real dielectrics often behave uniformly in pretty much all directions. The true atomic secret is so much more elegant. You don't need tiny conducting spheres at all. You just need atoms. Think about it. An atom has a positive nucleus surrounded by a negative electron cloud. When you apply an external electric field, the positive nucleus gets pulled slightly in one direction, while that negative electron distribution is displaced slightly in the exact opposite direction. The atom doesn't tear apart. No, it just stretches. Its center of negative charge no longer perfectly overlaps its positive center. Section 3, the polarization vector. This microscopic stretching of literally millions of atoms turns them into tiny dipoles. So instead of those perfectly balanced spheres, we now have millions of microscopic ovals all lined up with the field. And that brings us to a vital mathematical tool for tracking all this chaos. We measure this collective atomic distortion using the polarization vector, denoted by a capital P. It simply tells us the dipole moment per unit volume. Basically, it's our way of calculating exactly how aggressively the material's atoms are stretching in reaction to that external electric field. And this builds into this beautiful chain reaction. Step 1, the external electric field is applied. Step 2, the atoms inside the insulator stretch out into dipoles. Step 3, because all these tiny dipoles line up, they effectively push a net charge to the very outer edges of the material. And finally, step 4, this brand new surface charge creates its own internal electric field that points in the completely opposite direction. It fights back, weakening the total internal electric field. And you know what? That is exactly why the voltage drops. Now, to make the math actually work here, think of it like a strict accounting system. We have to carefully distinguish between two totally different types of charge. First, there's the free charge. That's the charge we physically put on the capacitor's metal plates using a battery. We control that one. Second is the polarization charge, and this is the charge that nature just sort of magically induces on the surfaces of the insulator simply because its atoms stretched. Here's exactly how that polarization charge manifests. Deep inside the bulk of the dielectric slab, the positive end of one stretched atom sits right next to the negative end of its neighbor. They just perfectly cancel each other out. So inside the material, the net charge remains a big fat zero. But at the extreme edges of the slab, there are no neighbors left to cancel out that final row of stretched atoms. The stretching basically leaves an excess polarization charge completely stranded on those outer faces. And this surface charge density is perfectly equal to the magnitude of our polarization vector. Moving on to section 4, rewriting Gauss's law. Because nature automatically generates this hidden polarization charge wherever a dielectric is present, the classic foundational equations of electrostatics actually need an upgrade.
Everything we just looked at assumed a uniform electric field. But what if the external field is messy? What if it's non-uniform? Well, if the atomic stretching, the polarization, is uneven across the material, more charge might stretch into a specific microscopic volume than stretches out of it. And when that happens, the interior cancellation fails completely. This creates a perfectly real volume charge density right smack in the middle of the insulating material.
The source material puts it perfectly, saying, we have a kind of Gauss's theorem that relates the charge density from polarized materials to the polarization vector P. See, by taking the mathematical divergence, which is really just a way to measure things spreading out, we can precisely calculate this internal volume charge. We use this to essentially rewrite Gauss's law. So instead of just tracking the free charges we put into the system, our newly updated Gauss's law automatically tracks both the charges we control and those hidden reactive charges shifting around inside the dielectric matter. Section 5, forces in real life. Let's zoom back out from the microscopic atomic stretching and all those heavy mathematical equations for a minute. How do these stretched atoms create physical, observable forces in the real world? Let's go back to our very first question. Why does the comb pick up the paper? Well, a piece of paper is a dielectric. When the charged comb comes near, it forces the paper's atoms to stretch, inducing that polarization charge. The side of the paper closest to the comb gets an opposite charge, and the far side gets a like charge. But here's the magnificent secret. The comb's electric field is non-uniform. It's intensely strong close to the plastic teeth and much weaker further away. Because of this, the comb pulls on the paper's closer, oppositely charged surface way harder than it repels the distant like-charged surface. The end result? A net attraction. The paper jumps.
And we see this exact same principle on an industrial scale too. Imagine a parallel plate capacitor with a piece of dielectric material hovering just near its edge. Because the electric field subtly bows outward at the edges of the plates, creating a gradient, the dielectric will literally be sucked right into the gap between the plates. It gets drawn into the region of the stronger electric field, just to minimize the energy of the whole system. The forces involved here can be calculated perfectly just by tracking how the system's total capacitance changes as the material slides in. We're going to end this explainer with a pretty profound warning from the legendary physicist Richard Feynman. After building up all this elegant math to describe how atoms stretch, he hits us with this. An equation like D equals epsilon E is an attempt to describe a property of matter, but matter is extremely complicated, and such an equation is in fact not correct. What he means here is that our formulas assume atoms stretch perfectly in proportion to the field, but if that field gets too strong or changes too fast, the material behaves completely unpredictably. We've journeyed from a plastic comb down to stretching atoms, through the math of polarization and all the way back out again. But it shows us that our rules are just beautiful approximations that ultimately break down. It leaves us to wonder, at what exact point does our mathematical maps stop representing the immense chaotic complexity of physical reality?
Okay, let's dive into this. Have you ever actually stopped to think about what's happening at the atomic level when everyday materials get hit by an electric field? I mean, really happening? Today, we are looking inside dielectrics for this explainer. We're going to explore this totally invisible tug-of-war that's going on right under our noses literally all the time, in the gases we breathe, the liquids we drink, and the solid stuff powering our tech. It's an absolutely fascinating world of unseen forces, and we're going to break it all down.
So here's the roadmap for our micro to macro journey today. First up, we'll meet the molecular dipoles. Then, we look at gases and see how they stretch and align. After that, we move into liquids with something called the spherical hole, followed by solids and frozen polarization. Finally, we'll wrap up with the wild world of runaway ferroelectricity.
All right, part 1. Meet the molecular dipoles. This is where we introduce the main character of our story.
So, to really get a handle on dielectrics, we have to meet the dipole. You can think of the dipole as our invisible main character, and we're going to follow its journey through totally different states of matter.
Take a look at the perfectly symmetric, nonpolar oxygen molecule. Notice how the center of the positive charge and the center of the negative charge are sitting right there, perfectly balanced in the exact same spot. But then look at the polar water molecule. Because it's got this uneven kind of bent arrangement of hydrogen and oxygen atoms, the centers of charge just don't overlap perfectly. One side ends up a little more positive, the other a little more negative. And that creates what we call a permanent electric dipole moment. It's essentially this tiny microscopic magnet, but, for electricity instead of magnetism.
Moving right along to Section 2, Gases, Stretching, and Aligning. Let's move to Lens and see how this builds as we add a little more complexity.
So, stepping up one level, how do these tiny molecular actors actually react when they're grouped together into a gas and getting pushed around by external electrical forces? Well, there are two baseline rules for how a gas polarizes. First, we've got electronic polarization. Even in a totally perfectly symmetric nonpolar atom, like helium, a strong electric field is going to literally stretch the atom. It pulls the electron cloud one way and the nucleus the other. It's a physical distortion of the atom itself. Then, second, we have orientation polarization. This one applies to those polar molecules, like the water we just talked about. Instead of just stretching them out, the electric field actually grabs the entire molecule and physically forces it to turn and align with the field itself.
Now, without an electric field, it is pure chaos. Just random thermal heat causing molecules to constantly collide, which keeps them completely randomly oriented. But when we switch an electric field on, well, that chaos suddenly gives way to an average alignment. You can really see the tension here. The field acts kind of like a gentle current in a river, continuously nudging all these tiny dipoles to face the exact same way, all while the constant thermal jostling is desperately trying to knock them back off course. And this brilliantly illustrates the exact struggle going on. Physicists use some underlying math here to calculate the exact energy and alignment of a single dipole moment vector when it gets subjected to that electric field. See, the energy is at its absolute lowest, and the molecule is therefore the most stable when the dipole is perfectly lined up with the external field. The molecule inherently, naturally wants to reach that lower energy state. It's always chasing stability. So this constant push and pull brings us to Curie's law. This defines the core principle that polarization in these gases is inversely proportional to temperature. Now, why is that? Well, because higher temperatures literally mean faster, more violent, and way more disruptive thermal collisions between the molecules. It's this ongoing invisible war, right? You have the electric field trying its hardest to meticulously organize the molecules, and the heat just trying to scramble them right back into a totally randomized mess.
All right, on to Section 3, Liquids, the spherical hole. Let's escalate things into a much more crowded environment.
When we move into the highly dense, jammed-up environment of a liquid state, we hit a massive new complication. An atom in a liquid doesn't just feel the outside electric field. It also feels the microscopic, super-intense electric fields of all its densely packed neighbors sitting right next to it. So the crucial point is that in dense liquids, to calculate the exact electric field acting on one specific atom, we absolutely must determine the local field. You can't just take the average field of the whole container, measure it, and call it a day. No way. You have to figure out exactly what a single atom is experiencing while it's completely jammed into a crowded space, surrounded by other highly polarized atoms inside a dielectric condenser. Honestly, it's a mathematical nightmare.
But to solve this nightmare, physicists came up with an amazingly clever workaround. They basically imagined taking the polarized material and mathematically carving out a spherical hole directly around the specific atom we're studying. By treating the total electric field as the sum of the field inside this imaginary empty hole, plus the field of the uniformly polarized spherical plug of material that we just carved out, we can effectively isolate the exact forces acting on our single atom. It's brilliant.
So by isolating the electric field of just that uniformly polarized spherical plug, we can subtract it out to find the exact local field left inside the hole. This theoretical leap is massive. Seriously, it leads directly to the famous Clausius-Massoudi equation, and what that does is beautifully relate the macroscopic dielectric constant of a whole liquid directly down to the atomic polarizability of its individual atoms.
And you know what the truly amazing part is? It actually works in the real world. If we look specifically at carbon disulfide, the Clausius-Massoudi equation predicts a liquid dielectric constant of 2.76, and the experimental reality is 2.64. That is incredibly close. And for argon, it predicts 1.517 against an observed 1.54. So this entirely theoretical, spherical hole calculation accurately predicts the actual physical behavior of completely different dense liquids. It's not just on paper, it's real.
Moving into section 4 now, solids, frozen polarization. This is where our molecular characters get rigidly locked into place. In solids, our molecular characters transition completely away from the fluid chaos of liquids. Now they are rigidly locked into place, and this structural freezing creates entirely new macro-level properties that we actually use in our everyday technology. Locking these molecules in place gives us some incredibly cool practical effects. First, we get electrets, which are essentially the electrical analogs to permanent magnets. You make them simply by melting wax in a strong electric field and letting the dipole alignments freeze permanently in place as that wax cools. Then we get pyroelectricity, where just heating or cooling a crystal changes its internal dipole moments to generate electricity. And of course, piezoelectricity. That's where bending or putting physical stress on a solid crystal literally forces the internal dipoles to shift, giving off an electrical signal.
All of this magic happens because of the underlying complex crystal lattice. Notice how every unit cell has an identical, built-in, permanent intrinsic polarization. All the tiny dipoles are pointing in the exact same direction naturally. Now, you might be wondering, why don't we get shocked or even notice this massive internal polarization when we hold these objects? Well, it's because stray electric charges from the air eventually drift over and perfectly coat the surface. They neutralize the external field entirely, so the power is there, it's just hidden inside.
And that brings us to our final act, Section 5, Runaway Ferroelectricity. This is where things get extreme.
We are now looking at a bizarre, almost accidental, and highly sensitive phenomenon. This is where these internal, frozen electric fields suddenly push a material to the absolute extreme. Ferroelectricity is basically caused by an escalating mathematical feedback loop. Imagine a lattice where the polarization gets just big enough to increase the local electric field. Well, that larger local field then polarizes the atoms even more, which in turn increases the local field again. If the atoms in the crystal have enough physical give to them, this creates a runaway feedback loop. It just keeps accelerating until the atoms physically jam up, permanently locking the entire lattice into a state of massive polarization.
Now, what's really interesting about this slide is how this runaway effect happens in real materials, like the unit cell of barium titanate we have right here. See that central spot? There is a very specific oxygen cage in there. When the feedback loop triggers, the central titanium atom gets pulled slightly off-center by the runaway local fields. It pulls and pulls until it physically jams into the side of the lattice. It literally gets stuck. And when it does, it generates a permanent, overwhelming dipole moment for the entire cell.
But here's the crazy part. This state is incredibly delicate. It is truly hanging on a knife's edge. At higher temperatures, the crystal lattice expands just enough that the titanium atom has a little room to wiggle, so it doesn't get fully stuck. But the moment you cool barium titanate down past exactly 118 degrees Celsius, the lattice shrinks just a tiny fraction, and bam, the titanium suddenly locks into that runaway state. But it barely sticks, which means that simply applying a tiny external electric field can easily unstick it and flip its alignment right over. That makes it an incredibly useful and highly sensitive dielectric material for engineering, a real game changer.
We can really see the mechanics of this alignment in action here. On one side, we have an anti-ferromagnetic model. Here, the internal fields from one vertical chain of atoms force the adjacent chain to point the exact opposite way, effectively canceling everything out. So, zero macropolarization. But on the other side, we have true ferroelectricity. In materials like barium titanate, there are actually intermediate chains of atoms situated exactly right so that their tiny counterfields force the main titanium chains to all align completely in parallel. It is just a perfectly balanced structural dance.
So, as we wrap up this explainer, I want to leave you with a question. How many other invisible, locked-in electrical mysteries are hiding inside the structures of the objects you are touching right now? Next time you look at a simple block of wax, or a piece of quartz, or the microscopic capacitors powering the device you're using right now, remember the dramatic, invisible atomic tug-of-war that is happening constantly inside all of them. The microworld is infinitely more chaotic, structured, and fascinating than we could ever hope to see with our bare eyes. Thank you so much for exploring the inside of dielectrics with me today, and keep asking questions about what's really happening right beneath the surface.
Okay, so what exactly does a nuclear reactor have in common with a desk lamp and a stretched rubber drum? I know, it sounds like the setup to a really weird joke, right? But the answer to this riddle actually reveals one of the most profound hidden connections in all of physics. It literally connects wildly different physical phenomena under one incredibly elegant roof.
Welcome to this explainer. Today, we are going completely behind the scenes of the universe to look at what I like to call the universal physics blueprint. We're going to unlock the master key of the universe, and I am so excited to share this with you. Because honestly, once you see this hidden connection, it's going to completely change how you look at the world around you.
Here's a quick look at our roadmap for today. We'll start with the universal physics blueprint, then explore heat flow and stretched rubber, move on to diffusing neutrons in water, tackle the mathematics of illumination, and finally wrap up with the underlying unity of nature.
All right, let's jump straight into part 1, the universal physics blueprint, and what this master key actually is. So the legendary physicist Richard Feynman had this brilliant observation that basically forms the entire core of our explainer today. He said, "The same equations have the same solutions." Now, I know that sounds almost too simple, doesn't it? But it's actually an incredibly powerful premise. It means that if you learn one area of physics deeply enough, you essentially unlock a cheat code for a bunch of others. Because, as it turns out, nature loves to reuse the exact same mathematical structures over and over again. And the specific cheat code we're using today, it comes straight from electrostatics. That's the study of stationary electric charges. Now, you're probably thinking, wait a minute, what do stationary electric charges have to do with rubber drums or, nuclear reactors? Well, the underlying mathematics, the differential equations that govern electrostatics, they actually act as our master key. We're going to take this electrostatic key and use it to kick open several entirely different doors in physics today.
Which brings us to part 2, heat flow and stretched rubber. Let's open those first doors.
Imagine you're looking at a classic geophysics problem. You've got this localized, intense heat source buried deep underground. Maybe it's a radioactive burst or a subterranean thermal vent. Geophysicists desperately need to know what the temperature distribution is going to be way up on the surface of the Earth. Like, how hot is it going to get right above that source? And how does that heat dissipate outward? How do we even begin to calculate something like that? Well, here is our massive aha moment. We don't have to invent new math. Temperature maps exactly to electric potential. And heat flow? It maps perfectly to the electric field. That underground heat source is mathematically identical to an electrical point charge buried in an insulating material. We already solved that exact problem in electrostatics, which means, boom, we instantly know how to solve the geophysics problem. No extra work required. And this brilliantly illustrates our next analogy. Just picture a rubber sheet stretched super tight like a drumhead, pushed up in one place and pulled down in another. Now imagine taking a cross-section of that sheet being pushed up by a round rod. If you want to know the exact, precise geometric shape that rubber sheet is taking, you literally just look at your electrostatics notes. The shape of a rubber sheet being pushed up by a round rod is mathematically identical to the electric potential of a long, charged cylindrical rod. The physical displacement of the rubber literally equals the electric potential. Now, what's genuinely fascinating is how physicists historically used this exact parallel backward. Before we had supercomputers, engineers actually used physical rubber sheets, pushing little rods into them to model really complicated electrical fields. They'd even roll tiny little balls across the rubber to mimic how electrons would fly through an electric field. They used this physical model to design the photomultiplier tubes that controlled the automatic headlight beams on vintage Cadillacs. How cool is that? Moving right along to part 3, diffusing neutrons and water. Let's look at some invisible currents. Okay, picture a bunch of neutrons wandering around inside a massive graphite block. Imagine a spherical region right in the center where uranium fission is constantly generating brand new neutrons. These neutrons are violently bouncing around, deflecting off carbon atoms, and slowly diffusing outward. If you are an engineer building a nuclear reactor, it is absolutely crucial that you can calculate their average density and flow. And our blueprint strikes again. The density of that neutron source behaves exactly like electrical charge density, and finding the overall neutron density throughout that entire block, it is exactly like finding the electric potential of a uniformly charged sphere. By simply knowing how to calculate the voltage of a statically charged ball, you automatically know how to calculate the density of neutrons in a raging nuclear reactor core. And the analogies just keep flowing. Imagine the ideal fluid flow past a sphere, represented by perfectly smooth streamlines. The famous mathematician John von Neumann actually called this dry water because it assumes the liquid has absolutely zero viscosity or turbulence, which, real water obviously has. But if you make those assumptions, this fluid flow exactly mirrors what happens when you put a sphere with zero electrical interaction into a uniform electric field.
It's the same puzzle, just with different pieces.
All right, let's step into part 4, the mathematics of illumination. Let's consider a really practical, everyday engineering problem. You have a desk and you want perfectly uniform light hitting its surface. You're going to install long tubular fluorescent lights on the ceiling in a regular grid. The big question is, how far apart should you space those tubes to guarantee the light on the desk is perfectly even, without any annoying bright spots or shadows? Instead of just guessing and checking, we use our cheat code. First, we literally just pretend those fluorescent tubes are a grid of electrically charged wires. Second, we compute the vertical component of the electric field that would reach the desk. And third, we solve for the spacing distance where the ripples, the variations in that field, are less than 1 part in 1,000. The math for the light rays is identical to the math for the electric field lines. It's wild. Now, to put that into perspective, what's really interesting here is the final answer we get straight from that electrostatic formula. 0.83. To get incredibly uniform light, varying by less than 1 part in 1,000, you space your fluorescent tubes at a distance equal to exactly 0.83 times the height of the ceiling. It's actually a surprisingly large optimal spacing, and we found it without doing a single optical experiment, entirely thanks to the math of stationary electric charges. Which brings us to our final section, the underlying unity of nature. Why does this all actually work? At this point, you really have to ask yourself, are we dealing with the exact same stuff? Like, is heat flow physically identical to bouncing neutrons or stretched rubber or light rays? Well, no, of course not. The physical displacement of a rubber membrane is definitely not the same stuff as the temperature of a hot rock. So why do we see this incredible underlying unity? The secret actually lies in the framework of space itself. You see, our smooth differential equations are really just large-scale approximations of a much more chaotic, microscopic reality. If you look incredibly closely at that graphite block, the neutrons are violently ping-ponging around in total chaos. But if you zoom way out, the distribution suddenly looks smooth, because the laws of physics operate within the framework of 3D space, and because they don't prefer any one direction, they naturally fall into the simplest mathematical patterns of how things change across a distance. Electrostatics just happens to be the purest, most basic mathematical representation of how those variations work in space. Which leaves us with a truly mind-bending final thought. If heat flow and neutron diffusion are just smoothed out, large-scale approximations of microscopic chaos, well, what about electrostatics itself? Could it be that even electric fields are just a macro illusion? Does the real world actually consist of tiny hidden particles, let's just call them exons, buzzing around in some complex machinery buried deep beneath the fabric of the universe, and we're just seeing the smoothed-out average? Physics hasn't found them yet, but the math tells us it's entirely possible. I'll leave you to ponder that one.
Welcome to The Explainer. Today, we're taking a seriously mind-bending journey into physics. We're going to jump right into the fundamental nature of magnetic fields, and more importantly, how they connect to Einstein's relativity. It's a story that starts with invisible forces and ends with a complete shift in how we understand reality itself. Let's get into it.
So consider this. What if the magnetic force isn't actually what you think it is, but just an illusion created by your own motion? I know it sounds like pure science fiction, but this paradox is literally at the very heart of modern physics. What we perceive as magnetism is deeply, fundamentally tied to our frame of reference. And by the end of this explainer, you're going to see exactly why.
Section 1. The Invisible Magnetic Force. Understanding the Basics.
Okay, let's dive right in. Picture a moving electric charge. Now, the magnetic force has a rather strange directional character. Unlike gravity or static electricity that just pulls straight in or push straight out from a source, the magnetic force acts at exactly right angles to a moving charge's velocity and at right angles to the magnetic field itself. It's kind of wild. It's a completely sideways push.
And that brings us to the Lorentz force. This is the big equation that governs the total push or pull on a charge. It neatly combines two things, the electric force, which honestly doesn't care if the charge is moving or sitting still, and that tricky magnetic force, which is entirely velocity dependent. Basically, if the charge isn't moving, it feels exactly zero magnetic force. Keep that in your back pocket because it's absolutely crucial for unlocking our paradox later on.
Section 2. Currents and conservation. Continuous flow of charge.
Now, to understand wires and circuits, we need a way to measure this continuous flow of charge without getting totally bogged down in complex calculus.
Enter current density. We represent it by the vector J. Think of it like water flowing in the river. It represents the amount of charge passing through a specific area over a specific amount of time, and it's driven by what we call the drift velocity, which is just the slow, collective forward march of the charges inside the material. So what's really interesting here is what happens when a wire carrying a current sits in a magnetic field. Every single moving electron inside feels that sideways Lorentz force we just talked about, and since those electrons are trapped inside the wire, they end up pushing against the atomic lattice. Millions of microscopic transverse forces add up to literally push the physical wire. This is actually the exact principle that makes electric motors spin.
Section 3. Ampere's law in action. Currents and fields. All right, so when we look at the magnetic field generated outside a long, straight wire, we notice something pretty unique. The magnetic field lines never start or stop from a single point. Unlike electric field lines that radiate out from a static charge, magnetic fields form perfectly closed loops circling around the straight wire. And Ampere's law gives us the exact mathematical machinery to calculate just how strong that field is, all based on the current inside the loop.
Now let's see how this builds when we take that straight wire and coil it up into a tightly wound spiral, a solenoid. Inside the solenoid, the magnetic field lines are strong, straight, and parallel. But on the outside, the field lines spread out at the ends and loop back around. And get this, you're looking at the exact same magnetic field shape as a standard bar magnet. A permanent bar magnet works the exact same way. The only difference is, instead of a wire coil, it's powered by the microscopic circular currents of billions of spinning electrons naturally lining up inside the iron. How cool is that?
Section 4. The relativistic twist. A cinematic shift.
Okay, get ready because here is the ultimate paradox. Imagine a negative particle moving at the exact same speed and direction as the electrons flowing inside a nearby wire. If we look at this from frame S, where the wire is at rest, the particle is moving. So naturally, it feels a magnetic force pulling it toward the wire. But wait, let's switch our perspective to frame S', where we're riding right alongside the particle. In this frame, the particle's velocity is exactly 0. And remember the Lorentz force? If velocity is 0, there can be absolutely no magnetic force. So does the particle move toward the wire or doesn't it? I mean, reality has to be consistent, right?
So the crucial point is this. In our first frame of reference, we have a pure magnetic field pulling the moving particle in. But switch to the second frame, and the particle is completely stationary. Yet relativity demands it must still be pulled toward the wire to keep reality consistent. If it's not a magnetic force doing the pulling, what is it? Well, it has to be an electric field. But how on earth does a completely neutral wire suddenly generate a mysterious electric field just because we changed our point of view? Well, the trick lies in relativistic length contraction. In our particle's rest frame, the wire is now zooming past us backward. And as Einstein proved, moving objects physically contract in the direction of motion. Because the positive stationary charges in the atomic lattice of the wire are now moving relative to us, the physical space between them literally squishes together.
Let's actually walk through this logic step by step. Step 1, the positive lattice of the wire is moving relative to the particle, so it contracts. Step 2, because it contracts, the same amount of positive charge is crammed into a smaller physical volume. Step 3, this means the positive charge density actually increases. Meanwhile, the negative electrons are stationary in this frame, so their density goes down to its normal, unsquished rest state. And finally, step 4, the wire is no longer neutral. It suddenly has a net positive charge density, which creates a very real electric field that pulls our negatively charged particle right in.
Section 5. Electricity and magnetism, united as one field.
And this brilliantly illustrates how the paradox is completely resolved. The mathematics map perfectly onto each other. At low velocities, the magnetic force perfectly equals the electric force. If you calculate the magnetic pull from the first frame and the electrostatic pull caused by length contraction in the second frame, the forces are completely identical. What looked like a purely magnetic phenomenon in one frame is actually a purely electric phenomenon in another.
This fundamentally reshapes how we view the universe. As physics dictates, quote, electric and magnetic forces are part of one physical phenomenon. The separation of this interaction depends very much on the reference frame chosen. Under Einstein's relativity, electricity and magnetism are forever united as a single electromagnetic field. You literally cannot have one without the other. It just depends on how fast you're moving.
So this leaves us with a pretty profound question to end on. If magnetic fields and electric fields can morph into one another based entirely on the observer's speed, and moving field lines are really just a handy mathematical way to describe changing fields from one frame to the next, what does that mean for the physical reality of the space around us?
It means the invisible forces shaping our universe are far more fluid and infinitely more interconnected than our daily human experience could ever let us realize. Keep questioning what you see, and thanks for watching The Explainer.
Okay, welcome to this explainer. Have you ever tried to visualize a magnetic field and just felt completely lost? I mean, with static electricity, things are delightfully straightforward, right? Electric field lines just shoot straight out from charges, kind of like spokes on a wheel. But magnetic fields? They are these complex, twisty, looping mazes that honestly don't seem to start or end anywhere. It's definitely enough to make anyone's head spin. Well, today, we are going to learn exactly how physicists map out these crazy, twisty mazes. We're going to uncover this incredible invisible scaffold that literally holds the magnetic world together, and we'll translate what looks like deeply abstract math into a really satisfying, tangible reality. Let's dive in. Here is our game plan for today. We're going to map the magnetic maze, unmask our absolute secret weapon, the vector potential, apply it to some straight wires, explore a totally mind-bending secret about solenoids, tackle the magnetic dipole, and finally, we'll zoom out to look at the master equation. All right, Section 1, Mapping the Magnetic Maze. Let's build a universal map. So here's the deal. In physics, when shapes are perfectly simple, like a perfect sphere or an endlessly flat plane, we can usually just use our intuition to guess what the field looks like. But let's be real. Real life is messy. We need a universal map that works for everything. Now, thinking about electrostatics, finding the electric field is super easy. If you know where your charges are, you literally just calculate a single, simple number for each point in space. That's the voltage. And then the electric field basically just flows downhill from high voltage to low voltage. It works beautifully because the curl, or the twistiness of an electric field, is always exactly zero. But magnetism? Magnetostatics loops and twists endlessly around currents. Because that curl isn't zero, we absolutely cannot just use a simple scalar number like voltage. We need a totally new approach. Moving right along to Section 2, Unmasking the Vector Potential. This is our ultimate cheat code. Since those old voltage tricks don't work for magnetism, physicists had to invent a new one. They discovered this hidden layer of reality that perfectly solves our magnetic maze. We call it the vector potential, and it's represented by the letter A. Now, instead of just a single number at every point in space, it's a vector. That means it has both a size and a direction. The definition is actually really elegant. The vector potential is a mathematical field whose curl, its twist, produces the magnetic field B. But here's the genius part. Because it's a mathematical tool, we actually have some flexibility in how we set it up. We can purposefully choose the divergence of this vector potential to be zero. By doing that, we basically strip out all the messy, unnecessary mathematical baggage from our equations, leaving us with a totally streamlined tool designed for maximum convenience. To really visualize how this invisible scaffold behaves in 3D space, picture a perfectly uniform magnetic field pointing straight up. The vector potential A that corresponds to that field isn't pointing up at all. Instead, it's actually rotating around that central vertical axis in a flat circle, and it grows stronger the further out you go. You can think of it like an invisible whirlpool, and the swirling motion of that whirlpool is exactly what creates the straight upward current of the magnetic field right at its center. Okay, so how do we actually put this cheat code to work? Physicists use this incredibly clever three-step procedure. Step 1, you find the current density. Basically, where's the steady magnetic current flowing? Step 2 is where the actual magic happens. We pretend, just temporarily, that our current is actually an electrostatic charge. And we solve for the vector potential using the exact same easy math we use for static electricity. We just solve 3 imaginary electrostatic problems, one for the x, y, and z directions. Finally, step 3, we take the curl, that twist, of the newly found vector potential, and boom, the true magnetic field is fully revealed. Section 3, Straight Wires and Currents. Let's see this in some everyday geometries. Let's pull this invisible scaffold out of theory land and apply it to something super common, a classic straight wire. Now, if you have a static electric charge on a metal wire, it all rushes to the outside surface because it's repelling itself. But a steady magnetic current is different. It flows uniformly through the entire cross-section of the wire, exactly like water flowing through a full pipe. Because of that uniformity, we can treat this scenario just like an imaginary solid cylinder of static electric charge. We calculate the vector potential for it, we take the curl, and we end up precisely mathematically proving what you probably already guessed: the magnetic field circles perfectly around the outside of the wire. Part 4. The solenoid secret. Prepare for some seriously mind-bending physics.
So, a solenoid is basically just a tightly wound coil of wire, a lot like a metal spring. But when we apply our vector potential to it, it reveals something highly counterintuitive. If you run the math for the magnetic field of a long solenoid, you'll find a really strong field trapped inside the coil. But the magnetic field strictly outside the coil, it's exactly zero, literally nothing. But wait, look at the invisible scaffold. If we calculate the vector potential outside the coil, it is actually not zero. The vector potential is actively circulating around the exterior of the coil, perfectly mirroring the current inside. This is happening in a region where there is absolutely zero detectable magnetic field. It's wild. The scaffold exists even where the building doesn't.
And this brings up a fascinating thought experiment, a bit of a rhetorical roadblock to really test our understanding here. Suppose instead of a wire coil, we just take a hollow pipe, paint some static electric charges on the outside, and we spin it. Moving charge is a current, right? So it makes a magnetic field inside. But what if you shrink down and you actually sit inside that spinning cylinder? Well, from your perspective, the cylinder is at rest. So shouldn't the magnetic field just vanish for you? Is there such a thing as a relativity of rotation? The answer resolves a major paradox. There is absolutely no relativity of rotation. A rotating system is not an inertial frame of reference. The cold, hard laws of physics dictate that the magnetic field is genuinely, absolutely produced inside that spinning cylinder, entirely regardless of your perspective. In fact, if you were to stick a short, radial piece of wire inside there with you, that very real magnetic field would literally push the electrical charges right out to the ends of the wire. Section 5, the magnetic dipole. The fundamental loops that make up our world. We have officially reached the climax. Because listen, all magnets, from the little ones on your fridge to the Earth itself, are essentially made up of these fundamental, microscopic loops of current. Imagine a simple rectangular loop of wire with a current flowing through it. Trying to map its magnetic field directly is a mathematical nightmare, but if we use our vector potential cheat code, we get a beautiful, clean result. That rectangular loop generates a perfectly circular vector potential that flows horizontally. And when we finally calculate the magnetic field from that, it looks exactly like the electric field of a classic dipole, like a positive and negative charge separated by space. But here's the absolute kicker. There are no actual magnetic poles here. There are no tiny north or south particles anywhere. The magnetic dipole is basically an illusion. It's created entirely by an elementary loop of current and mapped perfectly by our invisible circular scaffold. Finally, Section 6, the master equation. Let's zoom out. So we've zoomed in on straight wires, solenoids, and tiny loops. Now, how do all these specific geometries lead to one fundamental master equation? Enter the Biot-Savart law. Instead of calculating the vector potential first, this is a direct vector integral. It links the current in a thin wire straight to the resulting magnetic field in one massive equation where you integrate around the entire circuit. And look, it works and it's exact. But because it involves all these complex, three-dimensional cross products for every single tiny segment of the wire, man, it is mathematically bulky. It is often vastly harder to use than our really elegant three-step vector potential method. So you might be wondering, why bother with the vector potential at all if the Biot-Savart law can just give us the magnetic field directly? Well, I want to leave you with this incredible quote right from our source material. In more advanced theoretical matters, in relativity, in the principle of least action, and in quantum mechanics, the vector potential plays an important role. And honestly, this is the ultimate takeaway. This invisible scaffold we've been exploring today, it isn't just a clever mathematical trick to make engineering homework a little easier. It is the absolute fundamental reality. It is the bedrock foundation upon which advanced mechanics and the bizarre world of quantum theory are built. So if the vector potential is the true scaffold of the universe, what other invisible structures are out there just waiting to be unmasked? Think about that for a while and keep exploring. All right, let's dive into this breakdown of what is honestly a mind-bending metaphysical detective story. We're going to be looking at one of the most fascinating transitions in physics, how a concept that started out as just a super convenient mathematical trick ended up fundamentally rewriting our entire understanding of reality. Now I want you to imagine an invisible field, something you can't feel, something that exerts absolutely zero classical force, but can still somehow alter reality from a completely different location. Sounds like magic, right? Well, it's not. It's actually quantum mechanics. But to really grasp this spooky behavior, we first need to look at exactly where classical physics got things slightly wrong. Part 1, the magnetic energy deficit, finding the missing energy. So picture a simple rectangular loop carrying a steady current, just sitting there in a uniform magnetic field. If we try to calculate the mechanical work done to bring that loop into the field, we get a very specific value, negative mu dot B. But here's the secret. That's actually a fake number. It completely ignores the electrical work required to maintain that current. Because as the loop moves, the magnetic field exerts a force on the flowing electrons, right? It pushes them along the wire. You can kind of think of this like a balance sheet. If you only look at the mechanical energy, well, your books simply don't balance. Why? Because you totally forgot about the battery doing all the actual work. Turns out, physicists were just kind of bad accountants here. To keep the current steady while the loop is moving, a battery has to constantly deliver energy into the system. Once you account for that, the true total energy is actually positive mu dot B. That initial mechanical energy we talked about, it was just a really useful fiction.
Moving on to our next section, introducing the vector potential, or a mathematical ghost.
This is where we introduce the vector potential, which is usually denoted by the letter A. Think of it as a super handy mathematical bookkeeping tool. Just like we use a scalar potential, like voltage to calculate electrostatic energy, we can use this vector potential to calculate the true total energy of steady magnetic currents. And hey, it works perfectly in the math. But we've got to ask ourselves, is this just an arbitrary math trick to make our integrals easier to solve? Or is it an actual physical reality?
And that brings us to a massive philosophical question. What exactly makes a field real if we can't physically interact with it? In classical physics, a real field is basically just a set of numbers at a specific point in space that completely determines what happens to a particle at that exact spot. It's a nice, neat idea because it completely avoids that whole spooky action at a distance concept. To picture this, imagine a really long solenoid. When you run a current through it, it generates a magnetic field, a B field, but strictly on the inside. Outside that solenoid, the B field is absolutely zero. But here's the kicker. Our mathematical ghost, the vector potential A, is circulating everywhere outside the solenoid. Now, classical physics says a particle absolutely must touch the magnetic field inside to feel a force. Out in the region where only the vector potential exists, a classical electron feels literally nothing. So, for a really long time, physicists just assumed the vector potential wasn't real at all. All right, part 3, the quantum interference test, spooky action.
Now here is where reality just kind of breaks. Imagine a classic double-slit experiment with electrons. They travel as probability waves through two slits, creating that famous interference pattern on a screen. But then, we change things up. We place a microscopically thin, magnetized iron whisker, acting just like that tiny solenoid from before, right smack between the slits. The electrons pass by on either side, they never enter the whisker, they never touch the magnetic field. But the interference pattern on the screen, it actually shifts. There's no way around it. The vector potential acts at a distance, fundamentally altering the quantum phase of the electrons. It is definitively real.
And you know what's wild? This mind-blowing quantum reality was sitting right there, hiding in plain sight in the equations for 30 years. There's this great quote that hits the nail on the head, noting how fascinating it is that something so profound can be ignored for decades just because of our prejudices about what we think is significant. Physicists were just so stubbornly attached to the idea that only the B field was real, they completely missed what the math was practically screaming at them. That is until David Bohm and Yakir Aharano finally came along and proved it in 1959.
Next up, Section 4, Classic versus Quantum View, Bridging the Gap. When we actually compare the quantum and classical views, we see something truly beautiful. On one hand, we have the quantum shift caused by the vector potential. On the other hand, we have a classical particle flying through a thin strip of a magnetic field, experiencing a transverse force that deflects its momentum by a tiny, tiny angle. When we run the math, specifically applying the quantum principle that a particle's momentum is directly related to its wavelength, that quantum phase shift mathematically results in the exact same physical deflection angle as the classical momentum math. It's incredible. At a macroscopic scale, the quantum interference of the vector potential perfectly recreates the classical force of the magnetic field.
Which brings us to our final section, Section 5, Statics versus Dynamics, the true rules. So we have to face facts. A lot of the rules we thought were universal, they're actually false in general. Coulomb's law, that's only true if literally nothing is moving. The idea that electric fields have zero curl, again, only true in static situations. These were really just stepping stones.
The true rules of the universe are found in dynamic equations with time derivatives. Maxwell's equations, the Lorentz force, these are true always. Because when fields change with time, absolutely everything becomes deeply, intrinsically interconnected. In these true dynamic equations require us to factor in a universal speed limit. Physical influences don't just happen instantly. They propagate through space at the speed of light, c. Think about like a universal stopwatch running in the background. When you calculate the potential at a specific target point, you can't use the charges as they are right now. You actually have to use what they were doing at an earlier time, accounting for the exact amount of time it took the signal to travel to that point. So, I want to leave you with this final thought. We've seen how the invisible vector potential dictates reality and how changing magnetic fields create electric fields. But in a fully dynamic universe where every single moving charge influences everything else at the exact speed of light, what happens next? What kind of unseen waves are rippling through this hidden vector potential right now? It's definitely something to chew on.
Welcome to The Explainer. Today, we're exploring one of the most profound leaps in human understanding. We're going on a journey that starts with these microscopic, completely invisible forces and ends with the massive, roaring engineering marvels that literally power our modern cities. We're talking about electromagnetic induction, the actual spark that built the world as we know it today.
You know, when Michael Faraday first went public with his discovery of electrical induction, it really didn't look like much. People actually asked him, what is the use of it? I mean, all he had was this tiny wire and a magnet producing a barely noticeable twitch on a dial. But his legendary response? He asked, what is the use of a newborn baby? It's brilliant, right? Today, we're going to trace exactly how this seemingly useless infant of an idea grew up into the world-powering prodigy it is today.
Okay, let's dive right into our roadmap for this explainer. We're starting with the spark of induction, moving to the flux rule, taking a look at opposing forces with eddy currents, applying that to motors and transformers, and finally, looking at how all of this scales up to powering the modern world.
So, part 1, the spark of induction.
For a very long time, electricity and magnetism were viewed as these completely separate static fields. Sure, they were interesting, but honestly, a bit dull. Back in 1820, scientists first noticed a connection, that currents in wires actually create magnetic fields, and wires carrying current inside a magnetic field experience a physical force. But it took until 1840 for Faraday to find the absolute crucial missing link. He realized that electric effects from magnets only happen when something is changing. And that single realization, that is exactly what separates our candlelit past from the intensely illuminated present we live in.
Take a look at this setup. We've got a wire sitting between the poles of a magnet, hooked up to a galvanometer at the bottom. That's just a meter for detecting tiny currents. Now, if the wire just sits there, absolutely nothing happens. But the very second you move that wire through the magnetic field, the electrons inside the wire experience this sideways force. It physically pushes the electrons right along the wire, and bam, you see the needle on the meter jump. You're literally creating an electric current just through motion.
Now, to make sense of the rest of our explainer, we really need to anchor ourselves with a key concept, electromotive force, or EMF. When those electrons get pushed along the wire by the magnetic field, they repel the electrons further down the line, creating this kind of cascade effect. The total net integrated push on all those electrons once they've made it around the complete circuit, that is our EMF. Think of it as the pressure that actually makes the current flow.
Moving right along to part 2, the flux rule explained.
So, a physical push from a moving magnet is just one way to create EMF. But how do we quantify this magical push across all scenarios? Well, Faraday discovered something even stranger. Notice how we have two coils here sitting next to each other, totally stationary? If you simply switch off the current in that first coil, its magnetic field collapses, and that sudden change, it instantly causes a pulse of current in the second coil. The meter kicks. Switch it back on, and it kicks the other way. No physical movement required.
This is summed up beautifully by the flux rule. The magnetic flux is basically just the amount of magnetic field passing through the loop of wire. The rule tells us that the EMF generated in the wire is exactly equal to the rate of change of that flux over time. Bottom line, if the magnetic field is static, you get absolutely zero power. The absolute fundamental secret to generating electricity is continuous, relentless change.
Which brings us to section 3, opposing forces and eddy currents.
Nature has this really funny habit. Whenever you try to change something, the universe almost always tries to push back. And in electromagnetism, this pushback gives us some visually stunning stuff.
It's defined by Lenz's rule, which says that the direction of an induced EMF and the current it creates will always flow in a way that tries to oppose the change that created it in the first place. You can kind of think of it like the electrical equivalent of inertia. Just like a heavy boulder resists being pushed, an electrical circuit stubbornly resists any change in its magnetic state.
Let's look at what this electrical inertia actually looks like in the real world. Here we've got an aluminum ring sitting right on top of an electromagnet. When you suddenly turn on the alternating current, the magnetic field changes incredibly fast. Following Lenz's rule, a massive current is induced in the ring to fight that change. This new current creates its own magnetic field, perfectly opposing the electromagnet below it. The result? The two magnetic fields violently repel each other, and that heavy aluminum ring literally flies high into the air. It's amazing to watch.
And this brilliantly illustrates what happens if we completely take away all electrical resistance. Here is a bar magnet just suspended in midair above a bowl made of a perfect conductor, a superconductor that's been cooled down to extreme temperatures. Because there is zero resistance here, the induced currents, which we call eddy currents, can flow endlessly without losing any energy. They perfectly and continuously create an opposing magnetic field, allowing that magnet to just magically levitate.
We also see this pushback physically manifest as drag. If you take a solid copper pendulum and swing it through a magnetic field, it forms these massive eddy currents that stop it dead in its tracks. It's literally like hitting a wall of thick, viscous honey. But if we just cut some slots into that copper plate, we break up the pathways for those eddy currents. Suddenly, with the currents drastically reduced, the pendulum swings freely right through the magnet with almost zero resistance.
All right, part 4, motors and transformers. So, the big question: how do we harness these pushing, pulling, and dragging forces to actually create world-changing technology? This is where we pivot from cool science parlor tricks to serious practical tools. By carefully sequencing exactly when electromagnets turn on and off in a circle, we can create a magnetic field that appears to smoothly rotate in space. When you drop a conducting metal ring inside this invisible rotating field, those induced eddy currents fight the changing flux and create torque. The ring gets dragged around and around, desperately chasing that rotating magnetic field. And honestly, this elegant little principle is the absolute foundation of the induction motors humming inside your household appliances right now.
But, it's not just about spinning things, it's about moving the power itself. Take a close look at these two separate coils of wire wrapped around an iron core. There is absolutely zero direct electrical connection between the coil on the left and the coil on the right. None. Yet, that light bulb is brightly lit. What's happening is the changing current on the left creates a varying magnetic field in the iron, which then washes over the right coil, inducing an EMF that powers the bulb.
This right here is a transformer, and it is the key to our entire electrical grid. By simply changing the number of loops in the second coil compared to the first, we can literally transform the voltage. We step the voltage way up to insanely high levels so we can shoot it hundreds of miles over wires without losing all our energy to heat. And then, right before it enters your neighborhood, we step it back down to a safe level for your home.
And that brings us to our final section, part 5, powering the modern world. Okay, let's take a breath, because here is where it all comes together on a scale that is just mind-boggling. Because all these coils, magnetic fields, and induced currents, they aren't just tabletop lab experiments. Let's look at the story of a place like Boulder Dam. You have this colossal river, held back by a massive concrete wall, diverted just to spin these gigantic wheels. Those wheels turn an intricately woven matrix of copper and iron, a giant generator. That spinning motion forces the magnetic flux to change, creating an enormous EMF. Transformers then violently scale up that voltage so it can be pushed hundreds of miles across the barren desert. Ultimately, the brute force of a mighty river is delivered seamlessly to a city, maybe to power something as tiny and precise as a dentist drill.
The engineering required to pull this off is absolutely miraculous. We are talking about massive blocks of iron, 6 feet in diameter, whirling around endlessly with a clearance of just 1/16 of an inch. It's this breathtakingly complex intermixture of specially shaped iron, carefully proportioned copper, and precise insulation, all working in perfect, uninterrupted harmony. It ensures that the microscopic push on an electron by a magnetic field gets converted into the macroscopic lifeblood of a sprawling metropolis, all without melting the entire system down into a puddle of hot metal.
Which brings us right to the edge of tomorrow. We saw earlier how perfect superconductors can completely tear up the rulebook, allowing eddy currents to flow forever with absolutely zero resistance. As we push the boundaries of low-temperature physics, just imagine what this could mean for us. We could theoretically design power networks that transmit energy globally without a single drop of loss.
Faraday's useless baby has clearly grown into an absolute titan. But as we look to these new technologies, it becomes pretty clear that this explainer and our whole journey with electromagnetic induction is really just the beginning of the story. Thanks so much for exploring this with me today. Keep asking those big questions, and I'll see you in the next one.
Welcome to today's explainer. We're diving right in to unravel the beautiful weirdness behind how motion and magnetism literally power our entire world. You know, we interact with it every single day, yet those invisible gears turning behind the scenes, they're nothing short of magical. Think about it. How exactly does a moving wire create the electricity you're using to watch this right now? It's the core mystery connecting your screen to a spinning turbine miles and miles away. How does just shoving a piece of metal through an invisible field light up our cities and charge our phones? Let's figure it out. Part 1. The Magic of Induction. So we start with a really simple observation that basically changed human history. If you take a simple metal crossbar and just pull it to the right through a fixed magnetic field, it immediately shoves charges around that U-shaped wire. Boom, you've got a current. Imagine a steady magnetic field pointing straight out at you. As you pull that bar, you are physically dragging the electrical charges inside the metal through that field. And that motion, it creates this sideways force on the charges, driving them right around the loop. This brings us to the flux rule. The crucial takeaway here is that whether the circuit physically changes size, like making that loop larger, or the magnetic field itself changes in strength, the resulting electrical push, which we call the electromotive force, or EMS, is always perfectly equal to the rate of change of the magnetic flux. And flux is really just the total amount of magnetic field passing through that loop's area. Simply put, the faster you change the magnetic field going through the loop, the stronger the electrical push. It's a beautifully simple rule. Which leads us to part 2. 2 laws, 1 rule. Okay, so it turns out this rule holds one of the absolute strangest twists in all of physics. Our neat little flux rule, it's actually 2 completely different physical laws standing on each other's shoulders in a trench coat, just masquerading as a single deep principle. Richard Feynman himself pointed out that usually a simple, elegant rule stems from one single underlying truth, but surprisingly, not here. Think about the fundamental difference going on. If the wire physically moves, it's the magnetic forces directly pushing the charges along the wire. That's an entirely mechanical process. But if the wire sits completely still and the magnetic field itself changes, well, an entirely new electric field is basically born out of thin air just to drive the current. That's Faraday's law in action. We're talking about 2 wildly different physical realities, yet somehow they give us the exact same mathematical rule. Wild, right? Let's move on to part 3. Breaking the flux rule. Because this rule is just a mashup of 2 distinct effects, you can actually find some pretty clever ways to break it. Take these 2 famous exceptions. First, imagine a spinning metal disc. It creates an EMF even though the magnetic flux through the circuit pathway doesn't change at all. Why? Simply because the actual physical material of the disc is moving through the field. Now compare that to rocking plates. They change the path of the circuit massively, meaning the flux changes dramatically, but they produce almost 0 EMF, because the physical metal itself isn't moving with any real speed through the field. So, the big takeaway here is that you can really only trust the easy flux rule when the physical material making up your circuit remains constant. Otherwise, you basically have to throw out the shortcut entirely and go right back to calculating those 2 fundamental laws we just talked about. Which brings us to part 4, powering the real world. Now that we know the rules, and of course how to break them, let's look at how this exact physics is engineered to actually power your home. Picture a classic alternating current generator. By rotating a coil, you continuously change the magnetic flux passing through it. Just by turning a handle, the angle of the loop changes, which means the amount of magnetic field passing through that loop changes too. And that creates an alternating voltage. It literally pushes charge in and out like a pump, reversing direction with every single half turn. But here's the absolutely crucial point. Electricity is not free. Every single ounce of electrical energy lighting up the room you're in right now requires an exact, equal amount of mechanical work to physically force that coil to spin. See, when the current flows, it actually creates a magnetic force that pushes back against the rotation. You have to put in real work to overcome that resistance. But the cool part is, 100% of the mechanical effort you put in gets converted directly into the electrical energy coming out. Moving on to part 5, the inertia of current. All of this builds into an even deeper, really fascinating concept called inductance. It basically gives electricity a sort of physical weight. Because an induced back EMF always opposes any change in current, a coil of wire acts exactly like a heavy physical object that resists being pushed or stopped. If you try to force current through it too quickly, it literally fights back. The parallels to mechanical physics here are just striking. Trying to instantly start a current through an inductor is basically just as impossible as trying to instantly accelerate a heavy bowling ball to top speed. It just won't happen. Force is exactly like voltage, velocity is like current, and physical mass behaves exactly like electrical inductance. It's a perfect mirror.
And just like a moving mass carries kinetic energy, 1/2 mass times velocity squared, the magnetic energy stored in a live coil is perfectly parallel to that. It's 1/2 times its inductance times the current squared. What this tells us is that electrical momentum isn't just a metaphor, it is a very real, measurable energy perfectly stored right there in the magnetic field.
Let's wrap this up with part 6, a physics paradox. I want to leave you with a completely fascinating puzzle that tests everything we've just learned today. Imagine a perfectly stationary plastic disc. Around its edge, there are charged metal spheres. Right through the middle is a center coil carrying a steady magnetic current straight up. Everything is still, nothing is moving, but we are about to suddenly hit the switch and turn off that center current. And here is where we get trapped between two absolute rules of physics. On one hand, Faraday's law demands that when that flux dies, an induced electric field is going to be created. That field will absolutely push on those charged spheres and create a torque. But on the other hand, we have the unbreakable law of conservation of angular momentum. It demands that since the system started with zero spin, it absolutely positively cannot start spinning without an outside force. So, will the disk rotate? It is not a trick question, and the answer reveals a truly profound secret about where electromagnetic momentum actually lives in our universe. Remember earlier how we said energy and momentum can be stored in the field itself? Well, I'm going to leave you to ponder that. When the power is finally cut, will that disk move? Thanks for exploring the magic of induction with me. Until next time, keep questioning how the world around you actually works.
So, imagine you're fixing a tiny, almost unnoticeable typo in a math equation, and boom, you accidentally unlock the ultimate nature of light itself. Sounds crazy, right? But that's exactly what happened in one of the absolute greatest moments in the history of science. Today, in this explainer, we're going to track how a seemingly simple mathematical adjustment totally transformed our entire understanding of the physical universe. Let's dive right in.
Here's our roadmap for today's explainer. First, we'll look at the missing puzzle piece. Then, fixing physics' glaring paradox. After that, we'll map out all of classical physics, watch the butterfly take off, and finally, unifying light and electricity.
All right, let's start with part 1, the missing puzzle piece.
So, our historical detective story begins with a massive problem. At the time, physicists actually knew a lot about steady currents and static charges, but taking the divergence of Ampere's law created this glaring mathematical paradox. It literally implied that electric charge could just disappear into complete nothingness. You see, Ampere's law said the curl of the magnetic field equals the current, but mathematically speaking, the divergence of a curl is always zero. To put that in plain English, imagine a sealed room. If you watch people walk out the door, but the total number of people inside never drops, well, you've got a paradox. The math was essentially saying charge could flow away, but the source wouldn't deplete, it just magically vanished. No way that works in reality, right?
And that brings us to the ultimate golden rule, conservation of charge. Basically, electric charge cannot be created or destroyed, period. If you have a current flowing out, it absolutely has to be coming from a supply. It can't just pop out of the ether. James Clerk Maxwell looked at this broken math from Ampere's law and immediately knew it had to be wrong, simply because reality just doesn't allow for vanishing charges. He had to find a missing puzzle piece to bridge the gap between that faulty math and, actual physical reality.
Which leads us to part 2, fixing physics' glaring paradox.
Okay, to see exactly how Maxwell fixed this, I want you to imagine injecting a block of Jell-O with a hypodermic needle full of charge. That charge leaks outward in all directions equally, what we call a spherically symmetric current. Now, without Maxwell's fix, the old laws bizarrely suggested there would be a magnetic field circling around this outwardly leaking charge. But Maxwell stepped in and added a tiny, incredibly elegant new term to balance the ledger, the rate of change of the electric field. With this new addition, the increasing electric field perfectly mirrors and cancels out the outward current. The math is saved, and the ledger is officially balanced.
But hey, math on a chalkboard is one thing, right?
Reality is another beast entirely. To test this fix in the real world, we have to look at a charging capacitor. Picture a physical wire carrying a current to a metal plate. Then, there's a literal empty gap of space before the next plate where the wire continues. According to the old laws, the magnetic field circling that physical wire should just hit the empty gap and cease to exist. But does it really just disappear?
Not at all. If you measure the magnetic field around the physical wire and then slide your measurement down into that empty space between the plates, you measure the exact same magnetic field. How is that possible? Well, it's because Maxwell proved that a changing electric flux in that empty space acts exactly like a physical, tangible current. The changing electric field perfectly bridges the empty gap. It's a real game changer.
Moving on to part 3, all of classical physics. Now, you might be thinking Maxwell's new term just fixed a technicality in a capacitor, but it did so much more than that. We have literally just climbed the K2 of classical physics. Just look at this synthesis. In this one beautiful space, we possess the complete set of rules governing the physical universe, as it was known up until 1905. You've got Maxwell's 4 equations right there, right alongside the conservation of charge, the force law, and Newton's laws of motion and gravitation. By adding that one single missing piece to balance the math, Maxwell didn't just patch a glitch, he locked the keystone of electromagnetism firmly into place. It remains, for sure, one of the most triumphant moments in the history of human discovery.
All right, part 4. The butterfly takes off. Now it's time to coast downhill and see what happens when we put these completed equations to the test dynamically. Imagine taking a massive sheet of charge and suddenly shoving it into motion. The exact moment it moves, that current creates a magnetic field. But because that magnetic field is abruptly turning on, it's in a state of change. And as Michael Faraday taught us, a changing magnetic field creates an electric field. That new changing electric field then creates more magnetic field. They literally lock together, marching forward through empty space like a massive self-generating tidal wave. If we look at this from above, we can literally see the front of this wave expanding outward into the void. It's not instantaneous, by the way. The fields aren't just everywhere all at once. They physically travel outward from the source at a constant, uniform velocity, pushing each other along through space, rippling out, just like a stone dropped in a cosmic pond. And viewing this from the side reveals something even more incredible. Through Faraday's law, we can see that the progressively increasing area of the magnetic field generates the exact, precise amount of electric field needed to keep the whole wave pushing forward. It's wild. The wave is literally building a bridge for itself as it moves. It maintains a perfect, unwavering ratio between the electric and magnetic forces to sustain its own journey. But here is where the pure magic happens. What if we abruptly stop the current? Well, a block of this energy completely detaches from the source. The caterpillar turns into a butterfly. It no longer needs the wire, and it no longer needs the charge. It sustains itself in this perpetual dance, the electric and magnetic fields swishing back and forth, endlessly feeding each other. We basically have a self-sustaining block of fields flying freely through empty space forever. The energy has completely divorced itself from matter.
Which brings us to our final section, Part 5, Unifying Light and Electricity. For our grand finale here, we have to calculate exactly how fast this detached, self-sustaining butterfly of energy is actually flying. Because, Maxwell's equations aren't just conceptual metaphors, they generate hard numbers. If you go into a lab and measure the force between 2 stationary charged balls, and then measure the force between 2 boring, static wires, you get a couple of basic experimental constants. But if you plug those mundane laboratory constants into Maxwell's wave equation, out pops a very specific speed, 3.00 times 10 to the 8th meters per second. Yep, the exact speed of light.
As Maxwell himself famously wrote, we can scarcely avoid the inference that light consists in the transverse undulations of the same medium which is the cause of electric and magnetic phenomena. Just take a second to think about the absolute weight of that realization. His tiny mathematical fix didn't just solve a paradox on a circuit board. Before Maxwell, humans studied light as one thing and electricity and magnetism as something completely unrelated. By simply demanding that the math obey reality, he proved they are exactly the same thing. Light itself is literally just a wave of electromagnetism.
This incredible journey, from a frustrating mathematical contradiction to the complete unification of the cosmos, shows us the sheer, almost terrifying power of physics. Just by looking closely at a broken equation and demanding that it makes logical sense, humanity unlocked the secret to light itself.
It leaves us with a pretty provocative thought. What other breathtaking cosmic unifications are still hiding in the fundamental equations of our universe, just waiting for the next missing puzzle piece to be found? Thank you so much for exploring this with me today. In this explainer, I really hope it illuminated the absolute genius of Maxwell's equations for you.
Welcome to this explainer. Today, we are diving into what is honestly one of the most elegant, completely mind-bending concepts in all the physics. We're unpacking a masterclass originally delivered by the absolute legend himself, Richard Feynman. We're going to start with something super simple, just tossing a ball into the air. And believe it or not, we're going to end up uncovering some of the deepest, most hidden truths of quantum mechanics. So let's get into it.
The whole story actually kicks off when Richard Feynman was just a high school kid. His physics teacher, a guy named Mr. Bader, noticed young Feynman zoning out a bit in class. You know how it is. So he pulls him aside and says, "You look bored. I want to tell you something interesting." And what Mr. Bader told him right then and there was a profound secret about how the universe literally operates. It was so captivating that Feynman spent the rest of his entire life and eventually a massive, famous lecture years later, just obsessing over it.
That conversation planted a seed, and it brings us right to this core mystery. How on earth does a particle know which path to take? Think about it. When an object goes from point A to point B, like a ball flying across the room, it follows a very specific arc, right? But out of the literally infinite number of looping, zigzagging, completely wild trajectories it could potentially take, how exactly does nature pick that one perfect path?
Well, that brings us to part 1. A high school physics secret.
Okay, to really uncover Mr. Bader's secret, we've got to look at movement through the lens of two types of energy. You've got kinetic energy, that's the energy of motion, and potential energy, which is basically about height or position. Now, physicists use these to calculate a completely different, almost magical quantity that they call action, which is usually written as a capital S. To find the action, you take the kinetic energy at every single moment of a path, subtract the potential energy, and just tally it all up over the total time. And here's the big secret. The true path an object actually takes in reality is absolutely always the one where this action value is as small as it can possibly be. Basically, the universe demands the path of least action.
Let's make this a bit more tangible. Imagine a particle just floating in space. No gravity, zero potential energy to worry about. To keep its action as tiny as possible, it just needs to keep its kinetic energy at an absolute minimum. This perfectly explains why things floating in a vacuum just coast along at a constant speed in a straight line. Think about driving your car to school. Let's say you have exactly 10 minutes to get there. Now, you could floor it, slam on the brakes, and speed up again, basically wobbling your velocity all over the place. Or you could just cruise at one smooth, steady speed. Since kinetic energy relies on the square of your speed, mathematically speaking, wobbling your speed absolutely punishes your energy average. Cruising at that uniform speed, that's your minimum energy path.
Now, let's see what happens when we toss gravity into the mix. If you throw a ball upward, it gains potential energy. And remember, since action is kinetic minus potential energy, the math actually rewards the ball for going as high as possible. It's like stealing free points. But there's a catch. To go super high within a fixed amount of time, you have to launch it incredibly fast, and that completely skyrockets the kinetic energy penalty. So that super familiar, beautiful parabolic arc you see when you throw a ball, that is literally the universe doing a flawless, real-time balancing act. It's perfectly weighing the desire to go high against the penalty of moving too fast. Which leads us to part 2, finding the true path.
So how in the world do physicists actually calculate this one perfect path out of an infinite number of choices? We aren't just looking for the lowest point on a piece of paper, we're hunting for the lowest curve in three-dimensional space. To do this, they use a specialized branch of math called the calculus of variations. Sounds intimidating, right? But the intuitive logic is actually pretty straightforward. First, you just guess a true path. Second, you add a microscopic little deviation to it, like a tiny false bump. Third, you recalculate the action. Now, if you are truly sitting at the absolute minimum, that tiny little bump isn't going to change the overall action at all. Think of it like standing exactly at the very bottom of a smooth, bowl-shaped valley. If you take a tiny half step in any direction, your altitude basically stays exactly the same. If that difference is zero, boom, you've mathematically proved it's the true path.
And this highlights a massive shift in how we fundamentally view physics. Isaac Newton gave us the differential view, F equals ma. That's a very moment-by-moment way of looking at the world. A particle just inches along, it feels a push, it reacts, moves a tiny bit, feels another push, and so on. But the principle of least action, that is an integral view. It completely zooms out. It makes this grand sweeping statement about the entire path, all at once, from the very beginning all the way to the very end.
And that brings us to part 3, the quantum mechanics miracle.
Okay, brace yourselves, because this is where your brain might actually start to hurt a little bit. If Newton was right, a particle is just blindly reacting moment to moment. But if the principle of least action is right, we've got a massive philosophical puzzle on our hands. How can a particle possibly know the whole path before it even starts moving? Does it, map out its destination, run the integrals, find the minimum, and then decide to take a step? No way. Nature doesn't just mysteriously choose the right path using some kind of divine foresight. The absolute mind-bending truth discovered through quantum mechanics is this: the particle smells all of them. Literally, it doesn't just calculate the right path, it actually explores every single possible trajectory in its vicinity, all at the exact same time.
Let's break down how this quantum magic actually works. In quantum mechanics, every single imaginary path has something called a probability amplitude. Just picture it as a tiny little spinning arrow. Now, the angle of that arrow is directly determined by the action of that specific path. For the vast majority of paths out there, the action is incredibly high, so these arrows end up spinning wildly in completely random directions. When you add all those wildly spinning arrows together, they completely cancel each other out. But for the paths sitting right near the minimum action, the arrows are almost all pointing in the exact same direction, so they add up. Essentially, the wrong paths completely destroy each other through interference, leaving only the minimum action path to emerge as our physical reality.
Now you might be wondering, hey, if baseballs actually work like this, why don't I see them blurring out into a million different paths when I throw them? Well, that all comes down to Planck's constant, which physicists often call h-bar. See, the phase of those arrows is the action divided by Planck's constant. Because Planck's constant is just unimaginably, infinitesimally tiny, normal-sized things, like baseballs, have massively huge actions by comparison. This means that cancellation of all those wrong paths is incredibly harsh and super precise. For a baseball, only the absolute perfect classical path survives. But if you zoom way in on an electron, where its action is super close to the size of Planck's constant, it genuinely acts like it's taking multiple paths at once.
All right, moving on to part 4. Nature's minimum principles. You see, this whole concept isn't just some abstract quantum theory. It is actually a wildly powerful tool for everyday engineering. Honestly, finding the minimum of a single equation is usually a lot easier mathematically than trying to calculate complex, messy forces inch by agonizing inch. Feynman actually showed that electrostatics follows this exact same minimum principle. The electrical potential naturally arranges itself to keep total energy at rock bottom. For example, if an engineer needs to figure out the capacity of a complicated shape, like a cylindrical condenser, they might not know the exact true path of the electric field. But here's the trick. By just making a rough, totally fake guess at the path and finding its minimum, they can get astonishingly close to the real answer. Notice how closely the rough, first approximation capacity aligns with the true capacity numbers. Because errors near a minimum point only show up as tiny, second-order blips, nature's inherent laziness actually makes complex engineering calculations incredibly forgiving.
We've covered a ton of ground today, going all the way from tossing a simple ball to quantum probability, straight through to practical engineering. So the ultimate, completely mind-bending thought I want to leave you with today is this. If nature isn't just blindly reacting inch by inch, but is actually out there exploring literally all possibilities to actively choose the most efficient grand path, what does that actually tell us about the foundational design of our universe? It strongly suggests a universe that isn't just driven by blind, dumb forces, but rather one of profound, staggering elegance. Keep exploring, keep asking those big questions, and I'll catch you in the next explainer.
Okay, let's dive into this. Welcome back to the explainer. Today, we are unpacking something absolutely mind-bending. We're talking about the invisible world of electromagnetic waves. You know, we usually think of the space around us as just empty, right? But it's actually not. It is teeming with this dynamic, chaotic symphony of unseen forces. So let's just jump right in and uncover the invisible framework of our reality.
Take a second and literally just look around the room you're in right now. What do you see? Walls, furniture, maybe a window. But here's a question for you. What invisible things are flying through your room at this exact moment? Imagine, just for a second, you could put on a pair of magic glasses that let you actually see every single force and wave moving through the air you're breathing. If you could see all that, the room wouldn't look empty at all. It would look like a wildly energetic storm.
With those glasses on, you'd see the Earth's steady magnetic field, just quietly pointing toward the poles. You'd see these jagged, static electric fields generated by the simple friction of people moving around. Magnetic fields would be pulsing, specifically at 60 cycles per second, straight out from the electrical wiring in your walls. And you'd see infrared waves traveling right from your warm forehead over to the colder surfaces in the room. There are even X-rays and ultraviolet light. And it gets crazier, right? There are radio waves carrying jazz music, cell phone data, Wi-Fi. Look even closer, and you'll find tiny oscillations arriving from space probes like Mariner 2, and these incredibly faint undulations originating billions of light years away from the most remote galaxies in the universe. I mean, what an astonishing, complicated thing the space around us actually is.
So, to really understand this chaotic symphony, we kind of have to define what these things actually are. And here is the crucial point. An electromagnetic wave happens when fields, which are generated by moving charges, literally detach from their sources and travel completely independently through space. This was a massive, game-changing breakthrough that came out of James Clerk Maxwell's equations. Before Maxwell, scientists just thought of fields as static zones around a magnet or a charge. But the math showed us this totally new phenomenon. When charges accelerate, the electric and magnetic fields they create break free. They travel all by themselves, carrying energy across the universe long after that original charge has completely stopped moving.
Let's try to picture this. Imagine we have an infinite flat sheet of electrical current, and we suddenly flip a switch to turn it on. Well, what happens? A uniform electric and magnetic field is created, but, and this is key, it doesn't just instantly appear everywhere at once. Instead, it extends outward from the source. The very edge of this field, the wavefront, moves forward at a specific constant velocity. We're talking about the speed of light, of course, denoted by c. For any distance further out than the speed of light has had time to reach, the field is absolutely zero. Nothing. It is literally like a wall of energy rushing outward.
Now, this brilliantly illustrates what happens when things get slightly more complicated. Because, in the real world, currents don't just turn on and stay perfectly constant. They vary. If we turn a current on to, say, 1 unit, and then crank it up to 3 units, the resulting fields literally stack on top of each other. This is the principle of superposition. By adding these different current steps together, we build up a complex wave shape. So the electric field is essentially drawing a precise spatial map of exactly what that current did over time.
What's absolutely fascinating here is this concept of memory. Say our current turns on, wiggles around a bit, and then turns completely off. The field that was just generated, it doesn't disappear. It forms this discrete little blob of field, a constant shape that travels perfectly intact toward the right at the speed of light. And this traveling wave acts as a completely detailed memory of the history of all those current variations. Think about it. If you were standing millions of miles away, you could measure this passing wave and know exactly what the source was doing. Even if that original source was completely destroyed millions of years ago.
Okay, so everything we've looked at up to this point involves one-dimensional plane waves, where the field moves in one single direction, kind of like a flat wall. But obviously, our universe is three-dimensional, so we need to contrast those plane waves with spherical waves. Just think of dropping a stone into a quiet lake. You see the ripples spreading out in circles, right? Well, a spherical electromagnetic wave is the 3D version of that, spreading outward in all directions from a central point. But because it's spreading out in 3 dimensions, it behaves a little bit differently than those flat 1D waves.
Since a spherical wave is actively spreading out, its total energy has to stretch over larger and larger surface area as it moves further away from the source. And because energy has to be conserved, the energy density actually falls. Because of this, as the wave travels further outward, its amplitude, the height or strength of the wave, has to steadily decrease. Specifically, it decreases proportionally to 1 over the radius, which, if you think about it, is exactly why a radio signal gets weaker and weaker the further you drive away from the broadcast tower.
Now, right about now, you might be struggling to picture these waves in your head, but let me share this brilliant perspective from physics. It requires a much higher degree of imagination to understand the electromagnetic field than to understand invisible angels. I mean, really think about that for a second. Why on earth are angels easier to imagine? Well, because to imagine an invisible angel, you just picture a normal visible human with wings and a halo, and then you just pretend they're sort of transparent. You have a physical reference point. But electromagnetic waves? There is no visual equivalent. There are no actual squiggly lines flying through the air.
This complete lack of a visual reference absolutely drove early scientists crazy.
Brilliant minds, we're talking Maxwell and Faraday, desperately wanted some kind of mechanical way to picture this. So they proposed the jello analogy. They imagined that the entire universe was filled with this thin, invisible jello that they called the ether. And they thought electromagnetic fields were just stretchings or twistings of this universal jello. It gave them something physical to visualize. But eventually science had to realize that forcing this tangible, physical picture was actually standing in the way of progress, because the jello didn't exist. We had to embrace the really difficult abstraction here. These fields are purely mathematical realities. We can only truly see them using equations and instruments.
And you know, this brings us to a really fascinating philosophical paradox about beauty and just how we perceive the universe. Let's consider a rainbow. When we look at one, our eyes immediately process all those colors, and we intuitively just say, wow, that's beautiful. But imagine for a second that you were completely blind, and you were trying to study that exact same phenomena using only scientific instruments. How would we describe a rainbow if we were blind?
Well, to a blind observer armed with a spectrophotometer, a beautiful rainbow is really just a dry graph. It simply shows the intensity of electromagnetic radiation as a function of wavelength, observed at certain meteorological angles. For instance, at 40 degrees, the instrument measures a bump in the shorter wavelengths, which is what you and I call green. At 42 degrees, there's another bump in the longer wavelengths, what we call red. So it's really just a chart of data points peaking at different spots.
Now, you might look at that data graph and think, okay, well, that's not beautiful at all. It totally lacks the visceral impact of actually seeing vibrant colors in the sky. But I'd argue there's a completely different kind of beauty hidden here. When we strip away our human senses and just look at the mathematical wave equation itself, we find this perfect, pristine symmetry between the spatial dimensions x, y, and z and the dimension of time, t. This beautiful symmetry in the equations suggests a really profound intellectual beauty. The incredible four-dimensional symmetry of space and time, which, as we know, eventually leads us straight to the theory of relativity. It's a beauty of pure logic and natural law.
So, as we wrap up this explainer, I want to leave you with a bit of a provocative question. Can you learn to see the beauty in the invisible? The next time you're sitting in a supposedly empty room, I really hope you don't just see the blank walls. I hope you remember that invisible symphony crashing all around you. You know, the fading memory of distant galaxies, the heat of your own body, those pulsing Wi-Fi signals, literally all of it governed by a breathtaking, invisible architecture of mathematics. Keep questioning, keep trying to visualize the math, and we'll catch you on the next deep dive. All right, let's dive right into this explainer and unravel what is honestly one of the most beautiful connections in all of physics. If you love it when seemingly disconnected ideas suddenly just snap together into a perfect puzzle, you are absolutely gonna love this.
So here's a fundamental question. Where does light actually come from? I mean, sure, you flip a switch and the room lights up, or we look up at the night sky and see photons that have been traveling for millions of years. But mechanically, at the bedrock level of the universe, what's actually making it? Well, it turns out the answer is hidden deep within some incredibly complex 19th century math. As the legendary physicist Richard Feynman pointed out, the goal here is to prove that the fundamental equations of electricity and magnetism, Maxwell's equations, literally contain the blueprint for light itself. We don't even need a separate theory for it. It's been hiding in the math of moving electrons the whole time.
To show you how this works, we're going to build this from the ground up. First, we'll look at the speed of light delay, then the master equations of electromagnetism. After that, how shaking charges make light, followed by the moving target problem. And finally, we'll hit a massive mind-bending payoff, the birth of relativity.
All right, part one, the speed of light delay, the echo of the universe.
To kick things off, we gotta completely rewire how we think about moving charges. Because light has a strict speed limit, information in our universe has a speed limit too. So if we're sitting at point 1 on this graph, and we want to know the electric field hitting us from a moving charge, we literally can't look at where the charge is right now. The field hitting us now was sent out in the past. We actually have to look backward to position 2 prime, or in math terms, time t minus r prime over c.
Physicists call this the retarded position. Think of it like a visual echo. When you hear an echo, you're hearing a sound from the past, right? Well, in electromagnetism, we're constantly calculating this retarded distance because the universe forces this built-in delay on us. And let me tell you, it's a massive headache when you're trying to track moving particles. But from here on out, every calculation we do has to account for the fact that the charge has already moved on by the time its signal actually reaches us.
Moving on to part 2, master equations of electromagnetism. the center of the universe.
Now, what's genuinely amazing here is how we can cram basically all of electromagnetism into one single frame. Feynman called this the center of the universe for electromagnetism. On the left, you've got Maxwell's equations. On the right, there's solutions, the scalar potential phi and the vector potential A. If we integrate the delayed charge and current densities, keeping that universal speed limit delay in mind, of course, we get the definitive solutions for all electromagnetic fields. The whole shebang is right here in these two columns.
Which brings us to part 3. Shaking charges make light, abstract waves to physical rays.
So the big question is, how do these abstract math solutions physically turn into the light that we actually see? Well, imagine taking a dipole, so a positive and negative charge, and just shaking it up and down. The math says this creates an oscillation in space. And if you look closely at the graph, the wave's amplitude is bounded by an envelope that drops off as 1 over r. Now, normally a static electric field dies out super fast, like 1 over r squared. But because we're shaking this charge, we create these really steep spatial slopes in the wave. And when you run the math to find the magnetic field, those steep slopes actually stop the field from dying off. It survives as it travels outward.
And because it's not fading away, by the time we're far away from the source, those oscillations turn into actual physical electric and magnetic fields, E and B, radiating outward. They're at perfect right angles to each other and at right angles to the direction they're traveling. That is the literal, exact definition of a ray of light. So just by shaking a charge and factoring in that time delay, Maxwell's equations naturally pump out light. It's just so elegant.
All right, part 4, the moving target problem, sweeping volumes.
Now here is where things get a bit tricky. We can't just stop at a shaking charge. We have to ask, what happens if that shaking charge is also hurtling towards us at ridiculous speeds? To crack this, we have to calculate the potentials by imagining our point charge not as a tiny dot, but as a small uniform cube of charge, and we need to measure it as it's coming right at us.
And here is where the physics gets incredibly cool. Because of that speed of light delay we talked about earlier, we have to mathematically sweep over the charge to measure it, kind of like a flatbed scanner. But the charge is moving, so by the time our scanner reads the back slice of the charge, the front slice has already moved forward. We're literally forced to calculate different slices of it at different retarded times.
Because of this, notice how the moving slices stack up and stretch out the apparent volume. This visual proves that a moving charge actually contributes way more to the integral than a stationary one. Because it's coming at us while we're delayed in scanning it, it looks stretched out. And that introduces this massive, inescapable correction factor that's based entirely on velocity. This is exactly what gives us the famous Leonard-Wiechert potentials.
And that leads us perfectly into part 5, the birth of relativity, the secret in the math.
This is the grand payoff of this whole explainer. Back in the late 19th century, Hendrik Lorentz took this exact Maxwellian math, the sweeping integrals, the time delays, all those correction factors, and used it to calculate the potential of a charge moving at a uniform speed. His goal was just to translate the coordinates from a stationary frame into a moving frame.
Now just look at these formulas. Up top is your standard equation for a stationary charge. But look down at the moving formula. It spits out this extra transformation factor right at the front. Look familiar? It's 1 over the square root of 1 minus v squared over c squared. That is the exact, precise mathematical factor that drives Albert Einstein's theory of special relativity. It's literally the Lorentz factor.
The absolutely mind-blowing takeaway here is that the 19th century laws of electricity and magnetism were 100% ready for relativity, decades before Einstein even published his papers in 1905. The blueprint was sitting right there. Think about Newton's laws of mechanics. They actually had to be heavily modified and fixed to work with the speed of light. But Maxwell's equations? Zero fixes needed. Electromagnetism naturally, effortlessly predicts relativity just by keeping track of the delay of moving charges.
Which leaves us with a pretty wild thought to chew on. If Maxwell's equations from the 1860s already contained the hidden secrets of relativity, long before anyone even knew what they were looking at, it kind of makes you wonder. As we're pushing the boundaries today with quantum mechanics and string theory, what other profound, universe-shattering truths are already sitting quietly in the equations we use every single day, just waiting for someone to finally notice them? Thanks so much for exploring this explainer with me today.
Have you ever really looked inside a modern computer, or heck, even just a simple radio, and wondered how anyone could possibly calculate what every single electron and magnetic field is doing in that chaotic maze of wires? Well, I'm going to let you in on a little secret. The engineers who designed it, they don't know either. Calculating the complete electromagnetic fields inside a complex device using pure physics, it's literally an impossible task. But engineers are clever. They bypass all that mind-bending electromagnetic chaos using a brilliantly simple conceptual trick. They turn it into basic, structured rules. And today, we're going to dive into exactly how they pull off this magic trick. Okay, here is our roadmap for today. We're going to start with the magic of simplification, then meet our passive building blocks and active engines. After that, we'll lay down the rules of the game before pushing those rules to the absolute limit with infinite networks, and finally, looking at real-world complexities. All right, kicking things off with Section 1, the magic of simplification, or how we escape Maxwell's chaos. See, the ultimate rules of electromagnetism are Maxwell's equations. They describe absolutely everything: light, radio waves, static cling. But if you try to use them to calculate the fields inside a tangled ball of copper wire and silicon, yeah, the math becomes an absolute nightmare. It's just too complex. We need an escape hatch. And the legendary physicist Richard Feynman actually hit the nail on the head here. He pointed out that to actually build and understand everyday tech, we have to descend from the great esoteric heights of pure electromagnetic wave theory and come down to the relatively low-level, but incredibly practical subject of electrical circuits. We're essentially shifting our entire paradigm from continuous, infinite fields in space down to simple, discrete objects. We do this using something called lumped circuit elements. Now, this is the absolute genius of the black box concept. Instead of stressing over the swirling, chaotic magnetic and electric fields going on inside a coil of wire, we just draw a box around it. We literally say, I don't care what happens inside. I only care about what I can measure at the two ends, the terminals. If we know the relationship between the voltage going in and the current coming out, boom, we know everything we need to know. We've completely abstracted away the messy internal physics. Moving right along to Section 2, the passive building blocks. Now that we have these handy black boxes, what actually goes inside them? Well, pretty much any circuit you've ever interacted with is mostly made up of just three fundamental physical pieces. But before we meet the cast of characters, we need a unifying language, and that language is impedance, usually represented by the letter Z. Think of impedance as the ultimate translator between voltage and current. The absolutely crucial point here is that for any of our black boxes, if you divide the voltage across the terminals by the current flowing through them, you get the impedance. It basically just tells you how much a component resists or reacts to the flow of electricity. All right, let's meet our three passive building blocks: inductors, capacitors, and resistors. Notice how they react to alternating current, where the electricity wiggles back and forth at a certain frequency. Take the resistor. Its impedance is just R. It's a real constant number. It just resists, turning electrical energy into heat, totally ignoring how fast the current is wiggling. But look at the equations for the inductor and capacitor. They have an I in them, meaning they are mathematically imaginary. They don't burn energy. They just store it and slosh it back and forth. Plus, they contain that omega symbol, which stands for frequency. An inductor's impedance goes way up as frequency rises, while a capacitor's impedance goes down. They're called passive because they only respond to what you apply to them, but their response depends entirely on how fast that current is moving. So on to Section 3, the active engines. Because let's be real, those passive blocks are great, but they just sit there doing absolutely nothing unless we push some electricity through them. We need a power source, an active element. Picture a classic generator. You've got a fixed coil of wire, and inside it, a spinning magnet. As that magnetic field rotates, it's constantly changing the magnetic flux going through the coil. And thanks to the laws of physics, a changing magnetic field actually induces an electromotive force, a voltage, right there in the wire. The massive takeaway here is the difference between active and passive. Our passive resistors and capacitors only have a voltage drop because a current is being forced through them. But an active element, like a generator or a battery, it actually dictates the potential difference on its own. It determines the voltage based purely on its internal mechanics, like how fast that magnet is spinning, completely independently of what the rest of the circuit is doing. It is literally the engine driving the whole shebang. Okay, Section 4, the rules of the game. We've got our vocabulary now: generators, resistors, capacitors, inductors. Now we need the grammar. How do we read a circuit when we start wiring all these boxes together? Imagine a super tangled setup, multiple generators and passive blocks all mixed up. If you just rely on basic high school physics, you might try to simplify it by adding things up in series or parallel. But you can't.
The circuit is way too tangled, and that standard series and parallel math just entirely breaks down here. We need universal rules that work for literally any circuit, no matter how chaotic. And that brings us to the absolute elegance of Kirchhoff's rules. They are so wonderfully simple. Rule 1, the loop rule. If you walk around any closed loop in a circuit, the total change in voltage has to be exactly 0. Why? Because it's just the conservation of energy. You can't magically create energy out of nothing. If you end up back where you started, your net energy change is 0. Rule 2, the node rule. The sum of all currents entering a junction or node must be 0. Again, this is just conservation of charge. Every single electron that flows into an intersection has to flow out. With just these two basic rules, conservation of energy and conservation of charge, you can mathematically solve any circuit in the universe. It's brilliant. All right, let's turn things up a notch in Section 5, Infinite Networks and Filters. We're going to take our simple black boxes and those two rules and push them to the absolute limit to create things that seem almost impossible. Let me pose a question to you. Can we actually, mathematically, solve an electrical circuit that goes on forever? Like if I hand you a ladder of resistors and capacitors that stretches into infinity, does the math just fall apart? Astonishingly, it doesn't. Picture an infinite ladder network, inductors on the top wire, capacitors crossing over, going on forever and ever. Here is the ultimate math magic trick. If you have an infinite ladder and you tack on one more section to the front of it, well, it's still an infinite ladder, because infinity plus 1 is still just infinity, right? So, we can set up a simple algebraic equation where the impedance of the whole thing equals the impedance of one single section plus the whole thing. By solving that, we find that this impossible, never-ending circuit behaves exactly like a single calculable impedance at the terminals. We literally mathematically conquer infinity. Now watch what happens when we pump alternating current into this infinite ladder. Because inductors and capacitors react so differently to frequency, the whole ladder acts like a giant filter. Send in a low-frequency signal, and it ripples all the way down the line, absorbing energy perfectly. But, and here's the crazy part, send in a high-frequency signal, and the math totally shifts. The wave just cannot propagate. It hits a wall and rapidly dies out. This infinite ladder acts as a low-pass filter. It lets the deep bass notes slip right through, but completely blocks the high-pitched treble. So, why does any of this matter? Well, think about the power coming out of your wall. When engineers convert that AC wall power into DC power for your computer, they initially get this really bumpy, wobbling, lousy output. If you fed that raw, shaky power directly into your computer's microchip, yeah, it would fry it immediately. No way it survives that. But if we take that lousy, bumpy power and run it through the low-pass filter we just discovered, the filter completely absorbs all those high-frequency bumps and wobbles. What comes out the other end is pure, flat, perfectly smooth power. And it works in reverse too. Flip the components and you build a high-pass filter. Audio engineers use those in record players to strip out the low-pitched mechanical rumble of the turntable motor while letting the crisp, high-pitched music through. We are literally sculpting electricity. And if we combine these concepts, we get something even cooler, a band-pass filter. It rejects the extreme lows and the extreme highs, only letting a very specific band of frequencies through. This is exactly how telecom companies can cram hundreds of different voice conversations down a single copper telephone cable at the exact same time. Each voice is shifted to a slightly different frequency band, and at the receiving end, a band-pass filter just snatches that one specific conversation right out of the chaotic noise. Bringing it all home with Section 6, Real-World Complexities. We've seen how our basic black boxes work, but how does this actually scale up to modern tech? Can our simple little model handle the really advanced stuff running our digital age? The answer is absolutely yes. Let's take the transistor, the fundamental building block of literally every computer processor today. The actual quantum physics happening inside a tiny piece of silicon semiconductor is staggeringly complicated. But using our black box method, engineers don't even worry about it. They just model the complex transistor as a highly simplified equivalent circuit, literally just 2 resistors and an auxiliary voltage generator inside. By treating ridiculously complex modern components as simple linear equations, we can connect millions of them together on a microchip and still use good old Kirchhoff's rules to predict exactly what they're going to do. But transistors introduce one final, totally mind-bending twist to our deep dive today. I want you to really think about this. What happens when a circuit's resistance becomes negative? We all know that positive resistance, like in a toaster, burns energy and loses it as heat.
So mathematically speaking, what on earth is negative resistance? Negative resistance actually supplies energy. Because components like transistors draw external power from a battery, mathematically they act like negative resistors inside the circuit. If you pair a standard positive resistance with an equal negative resistance from a transistor, the net energy loss is exactly zero. You create a perpetual oscillator. It's a circuit where an alternating current will just bounce back and forth forever without ever dying out. These oscillators are the ticking clocks inside every single computer. They're the signal generators in radio stations. They are literally the heartbeat of the modern world. By simplifying the impossible chaos of physics down into black boxes and basic math, engineers haven't just learned to describe electricity, they've learned to command it. But as our computer chips shrink closer and closer down to the size of single atoms, you gotta ask, how much longer can these simple black boxes hold back the chaotic quantum reality lurking just beneath them? Thanks so much for joining me today. Let's jump right in. Welcome to This Explainer. Today, we're tackling the absolutely wild physics of what happens when the basic rules of electronics just completely break down. You know, we're usually taught that circuits are just simple wires connecting components together, right? But as always, physics has a massive surprise waiting for us when things speed up. It's actually this exact breakdown that gave us the technology behind modern radar and microwaves. So what exactly does happen when our trusty electronic rules stop working? Well, we're going to investigate why standard components completely fail at high speeds and how physics steps in with a mind-bending, wire-free solution. We're essentially taking a journey from standard everyday circuits straight into the weird realm of empty space and dancing fields. Here's a quick look at our roadmap. We'll start by hitting the high-frequency barrier, then we'll literally dive inside a fast capacitor, witness the birth of the resonant cavity, and wrap up by seeing how traditional circuits completely disappear. Let's get to it. Section 1, the high-frequency barrier. Let's look at why standard circuits start failing us. Okay, so what exactly is this high-frequency barrier? Well, take a look at the hidden reality of these everyday components. At low frequencies, they behave exactly how you'd expect. Simple, predictable. But crank up the speed, suddenly hidden parasitic traits take over. Unintended magnetic and electric effects just go wild. A simple coil of wire suddenly starts acting like a complex network of tiny capacitors. The current literally decides it doesn't want to go around the loops anymore. It just jumps the gaps because, well, it takes the path of least impedance. Moving on to Section 2. Let's step inside a fast capacitor and see these fields in motion. To really grasp why this happens, we need to zoom in on a geometrically ideal parallel plate capacitor. As we apply alternating current, the fields inside begin to slosh back and forth. Now, at low frequencies, the electric field just builds up uniformly across the plates. It's super simple. But as we push that frequency higher, the whole story changes completely. Right, so according to Maxwell's equations, these fields start interacting in this continuous compounding loop. The inside of our capacitor basically goes haywire. Think of it like a battleground. A changing electric field creates a magnetic field, but then that newly changing magnetic field induces new electric fields that actually push back against the original ones. Because of this, the fields get stronger and weaker at different distances from the center. It's totally dynamic. But here's the crazy part. This complex field oscillation isn't just random noise. It perfectly follows a mathematical pattern known as a Bessel function. You might remember this from higher-level math. It's a special function used to describe wave behavior inside cylindrical shapes, which of course is exactly the shape of the circular plates in our capacitor. Now, what's really fascinating here is that as we push the frequency even higher, the electric field wobbles out from the center, dips down, and hits exactly zero. You can see it mapping perfectly to the Bessel graph. Further out toward the edges, it actually reverses direction. Our simple capacitor is literally tearing itself apart electromagnetically. Section 3, birth of the resonant cavity. This is where we find our wire-free solution. So that field dropping to zero? It seems like a catastrophic failure of the component, right? Actually, scratch that. It's the ultimate breakthrough. It's our wire-free solution. Think about it. If we build a solid metal wall exactly where that field hits zero, we create a completely enclosed can. Because there's zero electric field at that specific radius, adding a conductive wall there doesn't disrupt a thing. The fields just sustain themselves perfectly inside. We end up with a closed metallic can where the electric and magnetic fields just bounce back and forth, entirely on their own, without any external wires at all.
This enclosed space acts as its very own circuit. It resonates at a highly specific frequency, determined by just two things, the speed of light and the radius of the can. It is pure, beautiful geometry. For this primary mode, the math shakes out so that the resonant frequency is exactly 2.405 times the speed of light divided by the cylinder's radius.
Let's move to section 4, probing and measuring resonances. How do we actually measure these fields? Okay, but this brings up a massive, obvious engineering challenge. We have a sealed metal can. How on earth do we get energy into it to actually use it? Well, by poking a tiny wire loop through a small hole, we can feed in a high-frequency alternating current to keep those internal fields dancing. This tiny loop acts like a magnetic bridge, coupling our external energy directly into the cavity. And to see what's going on, we just add a second little loop on the other side to measure the output. Now, if we look at that output, we don't get some broad, sloppy response. No way. We see an incredibly sharp spike right at the precise resonant frequency, something like 3010 megacycles. If you stray even a little bit to any other frequency, the fields inside simply cancel out and the energy dies completely. To put into perspective just how sharp this is, we look at the Q factor, the quality of the resonance. Because cavity walls made of silver are such incredible conductors, that Q factor can reach an absolutely massive 100,000. We're talking orders of magnitude better than a standard wire circuit. It's this exact mind-blowing precision that makes modern radar systems and giant particle accelerators possible.
Section 5, Exploring Cavity Modes. Let's look at some different field shapes.
Inside our cavity, the fields don't just have one way to dance. They can arrange themselves in various, sometimes bizarre ways, known as modes. But they have to follow strict rules. They absolutely must satisfy Maxwell's equations, and the electric fields must perfectly meet those conductive metal walls at exact right angles. As long as they do that, anything goes. For instance, we can have transverse modes where the electric field sloshes sideways across the diameter, or entirely new configurations where the fields jump from the sides to the ends. Each of these distinct shapes comes with its own unique resonant frequency. So practically speaking, our single metal can is actually a whole collection of completely different resonant circuits, all depending on exactly how you excite it. And finally, section 6, from circuits to cavities. Let's talk about shrinking the wires. So how do we reconcile our old-school traditional wires with these strange, empty cavities? Well, look at this progressive physical evolution. To handle higher and higher frequencies, we literally shrink the wires until they merge into a solid enclosing wall. We start with a standard capacitor and a coil. Then we put multiple coils in parallel. We keep adding wire paths, shrinking the gaps until the circuit entirely morphs into a loaded cavity. What's happening here is the once separated electric and magnetic fields of a traditional circuit are becoming intimately mixed inside a single physical volume. Think about a low-frequency circuit. The electric field lives totally in the capacitor, and the magnetic field lives entirely in the inductor. They are separate. But in our resonant cavity, they share the exact same space. They are completely and inextricably linked together. And you know, there's absolutely nothing magic about a cylinder. Any enclosed metallic shape will have its own unique set of resonant frequencies and dancing fields. Even a weird bell-shaped cavity like the one you see here will resonate perfectly. The mathematical equations to find the exact frequencies for odd shapes might be an absolute nightmare to solve, but the underlying physics, it's exactly the same. So this leaves us with a pretty profound realization. At high frequencies, the wires really don't matter. The only thing that matters is the geometry of the space we shape for the fields. Electromagnetic energy isn't confined to the copper. It lives in the empty space between. Whether it's the Wi-Fi router sitting on your desk or the microwave heating up your lunch, you're relying on invisible fields dancing in empty space. It really makes you wonder, are we even building circuits anymore, or are we just shaping the void? Thank you for joining me for this explainer. I hope this entirely changes how you look at the high-speed tech all around you.
Hey everyone, and welcome back to The Explainer. Today, we're peeling back the curtain on the invisible architecture that literally powers modern telecommunications systems, radar systems, and, yeah, even that microwave sitting in your kitchen. We're talking about the physics of waveguides. Let's dive right into the mechanics of how we guide massive amounts of energy through seemingly empty space.
Okay,
Let's start with a bit of a mind bender. Imagine you need to send a huge amount of high-frequency power from point A to point B. Naturally, your very first thought is, well, I'll just use a wire, right? But what if I told you that you could transmit all that power flawlessly without a single central wire? Seriously, can an empty, hollow metal pipe actually act as an electrical circuit? Well, let's find out.
All right, setting the stage here with Section 1, Beyond the Wire. To really grasp why we'd ever need empty pipes, we kind of have to look at the limitations of the old-school methods you see on the left. Now, if you're transmitting low-frequency power, standard open wires work just fine. But when you start cranking up that frequency, those wires suddenly start acting like antennas, and they just bleed energy everywhere. It's wildly inefficient. The classic fix for this is the coaxial cable. You just wrap an outer shield around the wire to trap the fields. But here is the massive, totally counterintuitive leap. If you pump the frequency high enough, you can actually yank that inner conductor right out. Poof, gone. And what you're left with is the hollow metal pipe on the right. That is a waveguide, and surprisingly, it guides high-frequency electromagnetic power perfectly.
Which brings us nicely to Section 2, the waveguide mystery.
So how on earth does an entirely empty pipe guide invisible waves without a physical circuit? Well, let's map out our physical space using the coordinates you see here. We're looking at a classic rectangular waveguide. The length of the pipe runs right down the z-axis. That's the direction our energy is flowing. And this means our electromagnetic wave is going to have a transverse electric field, meaning it actually points side to side across the pipe, not forward along the path of travel.
Now, take a look at the beautiful, arching shape of that electric field. Let's assume the field points straight up and down along the y-axis. The walls of this metal pipe entirely dictate how this field behaves. See, because the walls are perfectly conducting metal, a tangential electric field absolutely cannot exist right at the surface. If it tried, electrons in the metal would instantly rush in and cancel it out. So as a hard rule of physics, the field has to drop to exactly zero at the sidewalls, and it crests perfectly right there in the middle.
And it doesn't just sit there static either. As we look down the length of the pipe, we see the z-dependence of the wave. The electric field oscillates, right? Alternating between pointing up and pointing down. And this oscillating, undulating wave travels down the guide at a very specific speed, which we call the phase velocity. But here's the thing. An electric field never travels alone. It is always dancing with the magnetic field. Check out these brilliant loops of magnetic force circulating inside the guide. Because a changing electric field generates a magnetic field, the magnetic lines of force form these enclosed loops that circulate parallel to the xz plane. And they tuck themselves just perfectly right between the crests and the troughs of the electric waves we were just looking at. It's essentially a perfectly self-sustaining, traveling pocket of electromagnetic energy.
But it's not a free-for-all. Let's get into Section 3, the cutoff frequency barrier.
So we know really high frequencies can just zip right through this pipe. But what happens if we dial the frequency down and stretch those wavelengths out? Well, we hit the cutoff frequency. You can think of this as a very strict bouncer at the door of our waveguide. For a given pipe size, if the wavelength is longer than twice the width of the pipe, the complex math governing Maxwell's equations literally spits out imaginary numbers for the wave speed, which means propagation just becomes entirely impossible.
And this brilliantly illustrates exactly what that imaginary number looks like in reality. If you try to force a wave that's below the cutoff frequency into the guide, it goes nowhere. Instead, the fields instantly die out, dropping off in this incredibly steep, rapid, exponential decay. The energy might penetrate a tiny fraction of the guide's width before just vanishing entirely. At that point, it's not even a wave anymore. It's just a localized, dying field. The pipe just outright rejects it.
Okay, moving on to Section 4, faster than light.
Now, we all know the golden rule of the universe. Nothing travels faster than the speed of light, c. But waveguide math actually teases a pretty wild paradox. The secret to resolving it lies in understanding two fundamentally different types of speed. Over on the left, we have phase velocity. This is just the speed of the geometric visual pattern of the crests and troughs. And inside a waveguide, this mathematical phase velocity is actually greater than the speed of light. I know, crazy, right? But look at the right. There's group velocity. This is the speed at which the actual physical power and information are being transported. And the universe is safe, folks, because group velocity is always safely less than the speed of light.
And here is a truly fascinating mathematical nugget. If you multiply that faster-than-light phase velocity by the slower-than-light group velocity, you get exactly the speed of light squared, c squared.
What's absolutely incredible about this equation is how beautifully it mirrors quantum mechanics. It shares the exact same mathematical structure as the relationship between particle energy and momentum. It's all connected.
All right, let's unpack how this energy actually moves in Section 5, the mirror illusion. To really intuitively visualize how this empty tube guides energy without getting bogged down in heavy algebra, we can use a brilliant analogy championed by the great Richard Feynman. We're going to build a mental model in 3 quick steps. First, just imagine a glowing, oscillating line source of energy trapped right between 2 solid conducting walls. Step 2, pretend those physical walls aren't actually there, and instead imagine they reflect an infinite array of out-of-phase image sources stretching out forever in both directions. And step 3, we're going to watch how these infinite signals overlap and constructively interfere.
So here it is. Our single-source wire right in the middle is bounded by those top and bottom solid lines, which are our metal walls. Electromagnetically speaking, those perfect metal walls act exactly like parallel mirrors. They create this infinite sequence of alternating positive and negative image sources stretching out into infinity. So, instead of trying to calculate a super complex wave bounded inside a pipe, we just calculate the fields from this infinite, imaginary row of antennas.
And here is the big reveal. When you add up all those infinite signals, you don't actually get a single wave moving straight forward down the pipe. Nope. You get 2 distinct flat plane waves that crisscross. The energy actually travels down the empty tube by endlessly bouncing back and forth off the perfect mirror walls at very specific constructive angles. Those forward-moving nodes we talked about earlier, they're basically an optical illusion created by these overlapping crisscrossing waves. And that is exactly why the geometric pattern seems to travel faster than light, while the actual bouncing, ricocheting energy takes a longer diagonal path, ensuring it stays slower than light. Mystery solved.
Okay, let's wrap things up with Section 6, Waveguide Plumbing.
So, it's time to bring these crisscrossing theoretical waves back down to the real world. How do engineers actually build these massive power systems? Well, first, we physically inject the waves into the empty space using a tiny little antenna called a driving stub. And once those waves are bouncing around inside, engineers can literally cut a thin slot right along the top of the pipe and insert a sliding pickup probe. By moving that probe back and forth, they can literally map out the peaks and valleys of the invisible standing waves inside.
Now, because waveguides obviously come in finite lengths, they have to be bolted together. But even tiny, microscopic gaps in the standard flanges will cause massive resistive energy loss. So to solve this, engineers use a super clever trick called a choke joint. They essentially cut a tiny groove into the metal face of one pipe. This groove acts like a microscopic resonant cavity, creating a high impedance barrier. It basically forces the high-frequency surface currents to completely bypass the physical gap, tricking the energy into jumping right across the joint without any resistance at all.
And once you have these pipes smoothly bolted together, you can literally route this invisible electromagnetic energy just like water flowing through a plumbing system. What you're seeing here is a waveguide T-junction. It takes the incoming electric fields, those bouncing, guided waves, and flawlessly splits the power, sending it down 2 entirely different branches. You could use this to feed 2 different radar antennas at the exact same time. It is, quite literally, elegant, high-power electromagnetic plumbing.
Well, we have covered some absolutely incredible ground today. From the seemingly impossible idea of a wireless circuit, to the invisible bouncer of the cutoff frequency, to Feynman's brilliant infinite mirrors. So I'll leave you with this final thought. The next time you pop something into your microwave oven or rely on a massive high-speed data stream over a wireless network, ask yourself what perfectly confined, invisible waves and bouncing reflections are crisscrossing through empty metal spaces right now to make that magic possible. The physics of waveguides is all around us, operating silently, invisibly, and flawlessly. Thank you so much for joining me for this explainer, and as always, stay curious. Have you ever stared at a ridiculously messy math problem and just wished there was a cheat code to simplify the whole thing? Well, let's dive right into this explainer, the quest for elegance in 4D physics. We're going to explore the fascinating journey of translating the laws of physics from our familiar everyday 3D world into the incredibly beautiful geometry of 4-dimensional spacetime. Because as it turns out, upgrading our mathematical language doesn't just change the way equations look on a piece of paper, it fundamentally alters our entire understanding of reality. Let's kick things off with a pretty provocative thought. Is it actually possible to condense the sprawling, chaotic complexity of nature into one beautifully simple line of math?
For decades, physicists have chased the dream of the ultimate, elegant equation. But as we'll see today, true simplicity in physics isn't just about using fewer symbols. It's really about finding a mathematical structure that perfectly mirrors the unchanging truths of the universe.
Section 1. The four-dimensional upgrade. Installing a mathematical software update. To answer that big question, we first need to upgrade our mathematical language to match a core rule of the universe, which is that the laws of physics are completely unchanged if we move with uniform velocity. Whether you're standing still on Earth or zooming through the cosmos in a spaceship at a constant speed, the rules of the game remain exactly the same. So we need a mathematical framework that has this truth built right into its foundation.
In classic Newtonian physics, space is described with a 3D vector, just x, y, and z. But the special theory of relativity tells us that space and time are inextricably mixed. You really can't have one without the other. So, to account for special relativity, we must upgrade from a standard 3-vector to a 4-vector by adding a time component, t. And to make our lives infinitely easier, physicists use a brilliant trick. They just set the speed of light to exactly 1. This strips away all those messy constant variables and puts space and time on the exact same mathematical footing.
But translating 3D concepts into 4D isn't just slapping a t onto the end of a list. Take velocity, for example. In 3D, it's just distance over time. But in relativity, time actually bends depending on how fast you're going. So if we just use a standard time denominator, the math totally breaks down when you start moving. To fix it, we have to divide the components by a very specific factor, the square root of 1 minus v squared. Think of it as a universal conversion rate. It ensures our new 4-vector survives completely intact, no matter how fast our coordinate system is moving. Boom, our velocity vector is officially upgraded.
Moving on to Section 2, Math in Spacetime, Rebuilding the Toolkit for 4 Dimensions. Now that we have our shiny new 4D vectors, we need the actual tools to multiply them, measure them, and calculate exactly how they change.
Let's talk about measuring length. In traditional 3D space, you just use the Pythagorean theorem, right? X squared plus y squared plus z squared. But in space-time, it works a little differently. We calculate length as t squared minus x squared minus y squared minus z squared. That strange twist of the minus signs for the spatial components, it's pure magic. It ensures that this 4D length remains an absolute constant, completely unchanged under Lorentz transformations. Sitting still or flying past at half the speed of light, this calculation yields the exact same number. It is a universal invariant.
And we have to scale up all our mathematical operators too. It's kind of like upgrading from hand tools to power tools. The familiar 3D gradient, which measures how things change in space, gets a time upgrade to become the 4 gradient, and it carefully manages those tricky minus signs we just talked about. Meanwhile, the Laplacian, which is a massive staple in 3D physics for calculating fields, evolves into a 4D operator called the D'Alembertian. We're essentially teaching the entire language of calculus how to speak fluently in the theory of relativity.
Section 3. Collisions and Energy, Grounding Abstract Math in Physical Reality. Okay, so you might be wondering, how does this high-minded 4D math actually help us solve real-world problems? Is this just an exercise in algebraic aesthetics, or does it actually predict the universe?
Let's look at a concrete historical example. Imagine a proton colliding with a stationary proton. Physicists wanted to know the exact amount of energy needed to smash them together and spawn a brand new proton-antiproton pair. By using our new invariant 4D math, physicists could easily solve the equation from the simpler center of mass perspective, where the particles just mush together at rest, and then flawlessly translate that result back to a stationary laboratory setting.
The math didn't just give them a rough estimate either. It gave them a highly specific target, exactly 6.6 giga-electron-volts of kinetic energy. And this wasn't just some fun theory. That exact number directly dictated the engineering of the massive Bevatron accelerator at Berkeley. They literally spent millions of dollars building a machine specifically designed to hit the exact energy mark demanded by this beautifully simple 4D calculation. That is the jaw-dropping power of space-time math.
Section 4. Unifying the electromagnetic field, condensing Maxwell's legacy. Let's see how this 4D toolkit completely revolutionizes our understanding of electromagnetism.
Before relativity, electricity and magnetism were honestly a huge headache. They were treated as totally distinct forces with incredibly messy, different variables. You had scalar potentials for electricity and vector potentials for magnetism. Charge density over here, current density over there. It was just a lot to keep track of. But using our clean 4D logic, we can unify scalar and vector potentials into a single 4 potential. And we do the exact same thing with charge and current density to create a unified 4 current. Electricity and magnetism aren't separate things anymore. They are literally just different components of the exact same 4D vector.
And this changes absolutely everything when we look at moving objects. When you observe a moving charge from different coordinate frames, traditional 3D math turns into a convoluted nightmare. But by treating these elements as unified 4D vectors, the transformations become incredibly straightforward. A pure electric field in one observer's frame naturally bleeds into a magnetic field for a moving observer. The 4D math handles it perfectly, simply because they were never truly separate forces to begin with.
And here is the breathtaking payoff. Think of traditional Maxwell's equations. It's a sprawling, complex set of equations that takes up a whole chalkboard and gives physics students a serious run for their money. By using our 4D power tools, all of that mess magically condenses into one tiny, elegant expression. You don't even need to know how to pronounce the Greek letters to appreciate the beauty here. In this one tiny string of characters is the entirety of classical electrodynamics, perfectly surviving the rules of relativity.
Section 5. True elegance versus tricks. The trap of the unworldliness equation. It is incredibly satisfying to see the laws of nature condense so perfectly. But we really have to ask ourselves, is the goal of physics simply to hide messy math behind neat little symbols? Did we just sweep the mess under a mathematical rug?
To prove a point about what real simplicity is, the legendary physicist Richard Feynman invented a cheeky concept he called unworldliness. It goes like this. Imagine taking Newton's law, F equals ma. Rewrite it as F minus ma equals 0. Let's call that the mismatch. Now square it. Do that for every single law of physics, electricity, gravity, thermodynamics. Square all their mismatches and add them up to a total value called u. Because squares can only be 0 or positive, the only way for the total sum u to be 0 is if every individual physical law is perfectly balanced. By doing this, Feynman showed you could theoretically squish every single law of the universe into the tiny equation u equals 0.
You can print u equals 0 on a coffee mug. It looks incredibly elegant. But a simple notation that just hides the complexity in the definitions of symbols is not real simplicity. It is just a trick. U equals 0 is a cheap accounting trick. It teaches us absolutely nothing new about how the universe actually operates. When you unwrap that U symbol, you're exactly back where you started with a massive pile of unrelated equations. It is false elegance. So what is true elegance? True simplicity is mathematical symmetry reflecting nature's physical invariance. The reason 4D electrodynamics is truly beautiful isn't just because it's short. It's elegant because the notation physically mirrors the principle of relativity. It perfectly describes a universe where laws remain invariant across moving spaceships. The 4-vector notation wasn't just made up to save ink, it was forged directly from the geometrical reality of space-time. If you write an equation using valid 4 vectors, you automatically know it aligns with the absolute truth of relativity. It essentially restricts you to writing laws that can actually exist in our universe.
The language of 4D space-time revealed that electricity and magnetism were essentially two sides of the exact same coin, governed by a single unifying geometry. So, as we wrap up this explainer, I'll leave you with this thought. If updating our math from 3D to 4D revealed this much underlying beauty, what other profound hidden symmetries of the universe are just waiting for us to uncover them with the right mathematical language? What forces might unify if we just looked at them through the lens of a new, truly elegant symmetry?
Welcome to this explainer. Today, we're taking a pretty mind-bending journey into the realities of physics. We're going to be looking at relativistic electrodynamics. And hey, if you think you already know exactly how electricity and magnetism work, you might want to brace yourself, because we are about to zoom way out of our standard, comfy, three-dimensional world and look at the universe through the lens of relativity.
I want to hook you right out of the gate by posing this provocative question. Think about it. Is magnetism truly its own independent force, or is it literally just electricity in disguise? You know, in our slow-moving everyday lives, we absolutely experience them as two entirely separate things. But as we start approaching the speed of light, nature actually starts to reveal a really profound hidden symmetry.
So here is our roadmap for today. 1. Electricity in motion. 2. The squished electric field. 3. The magnetic side effect. 4. The four-dimensional truth. And finally, 5. Fixing Newton's law. Let's jump right in.
Section 1. Electricity in motion.
Okay, let's dive into this. When a charge is just sitting there, completely stationary, it has a totally simple, static electric field, right? But when it starts moving, uniformly in a straight line, things get really interesting, because the physical influence of that charge can only travel at the universe's ultimate speed limit, the speed of light. The electrical potentials we measure right now, at a specific point, well, they actually depend on what that moving charge was doing in the past. In physics, we call this the retarded position. It's kind of like ripples in a pond. The field ripples you feel at your present location actually originated from where the charge used to be at a previous point in time, radiating outward. In fact, if you were ever, say, stranded on a desert island and suddenly needed to reconstruct the entire core of electrodynamics from scratch, you'd literally only need three things. First, you'd need to know that the potential is a 4-vector. Second, you'd need the standard Coulomb potential for a stationary charge. And third, you just need to know that potentials produced by a moving charge depend only on its velocity and position at that past retarded time. With just those three core assumptions and the Lorentz transformation, boom, you can rebuild the whole thing. It just goes to show how deeply foundational the relationship between space, time, and moving charges truly is.
Moving right along to Section 2, the squished electric field. So here we get to see relativity in action. If you look at the top, a stationary charge has its field lines radiating out perfectly and evenly in all directions. But look right below it. As a charge flies by at, let's say, 90% the speed of light, the Lorentz contraction physically squishes the electric field. Imagine drawing the field of a resting charge on a piece of paper and then yanking that paper past your eyes at near light speed. That compressed picture you'd see? That actually represents the true physically squished field.
And because of this severe squishing effect, the actual distribution of the electric force changes dramatically. Directly ahead of and behind the fast-moving charge, the electric field is significantly reduced. But check out the sides. The field at right angles to the motion is enormously increased. To put that into perspective, the field bulging out sideways is actually bigger than the standard Coulomb potential by the exact ratio of the particle's energy to its rest mass. It's a massive distortion.
Which brings us to Section 3, the magnetic side effect.
And this brilliantly illustrates that very first question we asked. What exactly is the magnetic field of this moving charge? Mathematically speaking, if you take the velocity of the charge and cross it with that radioelectric field we were just talking about, you get a magnetic field. Visually, it just circles around the line of motion. So the takeaway here is that the magnetic field is fundamentally born from the motion of the electric field itself.
To really wrap our heads around this, let's look at a real-world application, or, well, at least a famous historical attempt at one. I want you to imagine a coordinate frame, like an airplane, moving through a static field, such as the natural magnetic field of the Earth.
Okay, picture this. It's before radar was invented, and pilots flying in terrible weather couldn't see the ground. They had no idea how fast they were actually going. So some very clever physicists thought, wait a minute. The airplane is flying horizontally through the Earth's vertical magnetic field. According to relativity, moving through a pure magnetic field actually makes an electric field appear from the perspective of the moving object. So the idea was, if you just hang an insulated wire across the airplane, the motion itself should induce charges on the ends of that wire. All you'd have to do is measure the voltage across the wire, and you've got yourself a makeshift speedometer that works completely blind. Pretty genius, right?
It was a gorgeous, elegant idea built on solid relativistic electrodynamics, but there was a catch. Actually, a pretty big one. Why did it fail? Well, while the theory was totally flawless, the real world is incredibly messy. You see, the background atmospheric electric fields naturally present out there are around 100 volts per meter, and they fluctuate wildly. This natural background noise is just enormous compared to the tiny, millivolt-level electric field induced by the airplane's motion. So unfortunately, that brilliant little signal was just completely masked by the noise.
All right, let's zoom out again for Section 4, the four-dimensional truth.
So, when physicists really tried to figure out how these fields transform when you change your frame of reference, like say, if you were flying by in a rocket, they realized these fields fit absolutely perfectly into this 4x4 grid. It's a mathematical object called an anti-symmetric second-rank tensor. It looks like a giant puzzle, but notice how the electric field components, the E's, live in the time columns and rows, while the magnetic field components, the B's, sit cleanly right in the spatial intersections. They aren't separate things at all. They are elegantly interlocking pieces of the exact same puzzle.
The legendary Richard Feynman summed up this triumphant realization perfectly. He said, "Our physical field is really the six-component object. That is the way we must look at it for relativity. It hits the nail on the head. Electricity and magnetism are absolutely not separate forces. They are literally just different three-dimensional shadows cast by a single four-dimensional reality. Depending on how fast you're moving through space-time, you're going to see a different mix of the two, for sure, but the underlying 4D object, that tensor, remains the exact same.
Which leads us to our final stop, Section 5, Fixing Newton's Law.
Now take a look at this truly bizarre scenario. Imagine two protons with velocities at right angles to each other, crossing paths so they just barely miss a collision. The proton on the top is moving horizontally, the one on the bottom is moving vertically. Naturally, they both exert an electric force on each other. But because the top proton is moving horizontally, it doesn't create a magnetic field in the forward direction where the bottom proton happens to be. However, the bottom proton is moving right through the magnetic field generated by the top one. So the bottom proton feels only an electric force, while the top proton feels an electric force plus a sideways magnetic force. So the forces on these two moving charges are clearly not equal and opposite. And I have to ask, does action not equal reaction? Is Newton's fundamental third law of motion literally broken here? Well, in the classical 3D sense that we're all used to, yes. Yes, it absolutely has been broken. Good old F equals ma just doesn't work when we are dealing with relativistic speeds and electrodynamics.
To actually fix this paradox, we have to look to the fourth dimension. We basically have to redefine time itself. We introduce something called proper time, which is usually denoted as s. This is an invariant interval of time. Think of it this way. If you carried a little pocket watch right along with that moving particle, the time that specific clock shows is the proper time. Because it is an interval in four-dimensional space-time, it remains perfectly, exactly the same in all coordinate systems, no matter how fast you are zipping around.
So, by swapping out our normal, everyday sense of time for this four-dimensional proper time, we get the true relativistic correction. The new equation says the four-dimensional force equals the rest mass times the acceleration with respect to proper time. This is a real game changer because it beautifully unifies motion and electromagnetism. It perfectly accounts for both electric and magnetic fields as a single unified entity, acting on particles in a way that is flawlessly consistent across any frame of reference in the entire universe.
So, we've seen today that the fields around us aren't just rigid, invisible lines. They squash, they completely transform, and they morph between electricity and magnetism simply based on how fast we're moving. So, as you go about the rest of your day, driving in your car, or even just walking down the street, I want to leave you with this to chew on. How is your own daily motion bending, squishing, and transforming the invisible electric and magnetic fields around you right now? Thanks so much for joining me on this explainer. See you next time.
Welcome to the Explainer. Today, we're going on a totally mind-bending journey into the invisible physics of energy and momentum. Seriously, if you think you know how energy moves in the world around you, get ready, because we are about to completely shatter your everyday physical intuition. We're going to explore forces that surround us every second of every day, yet behave in ways that seem, well, literally impossible.
Let me start by challenging you with a pretty simple question. When you plug in your laptop, does the energy powering your computer actually travel through the power cord? I mean, your everyday common sense probably screams, yes, obviously. The electrons travel down the copper wire and carry the energy directly to the battery, right? Well, hold on to your hats, because by the end of this explainer, you're going to see exactly why that assumption is entirely wrong. We are going to explore the ultimate intuition-busting reveal of how the universe actually works.
Okay, let's dive into this. Section 1. Local conservation of energy.
So let's talk about this foundational rule of how energy exists and moves in our universe. Basically, there are kind of two ways you might imagine energy being conserved. The first is what we could call worldwide conservation. In this scenario, energy could theoretically just disappear from point A and magically teleport or reappear at point B just as long as the total amount of energy in the entire universe stays the exact same. But the theory of relativity says absolutely not. Relativity strictly requires what we call local conservation. This means energy cannot just vanish and teleport. If energy leaves one region and arrives at another, it must physically flow continuously through the empty space in between. It actually has to cross the boundaries. Locally, nothing is just lost or teleported.
Which brings us to Section 2, meet the Poynting vector.
So if energy has to physically flow through the empty space between objects, how do we track it? Obviously, we can't see it. Well, we use a sort of mathematical decoder ring called the Poynting vector. Named after its discoverer, it's a vector representing the directional flow of electromagnetic field energy. You calculate it simply as the cross product of the electric field and the magnetic field.
Now, I know the calculus behind Maxwell's equations that gets us here can be incredibly complex, but the concept itself is beautifully simple. The pointing vector points exactly in the direction the field energy is moving, and its magnitude tells us just how much energy is flowing.
And this brilliantly illustrates exactly how this works for a simple light wave. You have the electric field vector, E, pointing up, and the magnetic field vector, B, pointing to the side. They're at right angles to each other. When you take their cross product, you get S. That's the pointing vector, pointing at a right angle to both of them, literally pushing the light energy continuously forward through space at the speed of light. It's just a perfect three-dimensional representation of energy in transit.
Moving right along to section 3, how energy actually flows.
Now that we have our mathematical tracker, we can apply it to some real-world examples. And this is where we completely shatter your everyday physical intuition. Consider a charging capacitor. It's basically two circular metal plates with a gap of empty space between them. As the electric field between the plates builds up, the energy is increasing in that gap. You'd naturally think the energy flows right down the vertical charging wires to fill the space between the plates, right? But if you map out the pointing vectors labeled S, the math proves the energy doesn't travel down the wires at all. The vectors point radially inward from the outside. The energy is actually sweeping in from the completely empty space surrounding the outer edges of the capacitor.
But wait, it gets even crazier. Let's look at a standard wire carrying a current, just like that power cord we talked about at the very beginning. The wire has electrical resistance, so as current flows, it gets hot, which obviously takes energy. If you trace the pointing vector S here, it is pointing radially inward, from the outside of the wire into the wire. Let that sink in for a second. The electrons inside your standard wire are getting their heat-generating energy from the invisible field outside the wire, flowing inward from the surrounding void, not flowing down the wire itself.
I know exactly how backwards this feels. It completely defies common sense. Actually, even the legendary physicist Richard Feynman directly acknowledged this, writing, "Our crazy theory says that the electrons are getting their energy to generate heat because of the energy flowing into the wire from the field outside. It's wild, but the math and the physics are incredibly clear and proven. The energy pushing the electrons actually comes from distant charges, travels through a wide area of empty space, and then literally dives inward into the wire to do its work."
Now, what's truly mind-bending is what happens when absolutely nothing is moving. Here we have a static point charge sitting perfectly still right next to a static bar magnet. Nothing's changing, so the energy shouldn't be moving, right? Well, hold on. There is an electric field from the charge and a magnetic field from the magnet. They overlap in space. Because of that, their cross product is not zero. This creates a pointing vector that continuously circulates in closed loops. This perfectly static setup is actually creating an invisible, continuous whirlpool of circulating energy in the empty space around it. If your brain is hurting a little bit right now, you are in very good company. Feynman himself wrote about this static circulation, exclaiming, "How absurd it gets! It is clear that our ordinary intuitions are quite wrong." I mean, I want to reassure you, it feels completely ridiculous to imagine a constant river of energy flowing in circles around a static magnet and a charge just sitting on a desk. But this invisible flow isn't just some mathematical quirk. It's an absolute requirement of nature, and we're going to see exactly why.
All right, section 4, momentum in the field.
So, the crucial point is this. If field energy physically flows through space, even in those absurd circles we just talked about, it must also carry physical momentum with it. Energy and momentum are intrinsically linked in the fabric of the universe. There's a powerful theorem in mechanics. Wherever there is a flow of energy, of any kind, it creates a momentum density. Specifically, the field momentum density equals the energy flow divided by the speed of light squared, or c squared. This means that an electromagnetic field doesn't just hold energy, it effectively gives invisible, seemingly empty space a physical push. The vacuum isn't empty. It carries actual, physical momentum.
Which brings us to section 5, the boxcar thought experiment.
To prove exactly why this invisible field momentum absolutely must exist to prevent the laws of physics from entirely breaking down, imagine a frictionless boxcar on a train track. Inside, at one end, we shoot a flash of light toward the other end. Light carries energy. Since energy has mass equivalence, remember Einstein's E equals mc squared. Moving that energy from one end of the car to the other physically shifts mass. If the car just sat there perfectly still, the center of gravity of the whole system would move. But without an outside force, the center of gravity cannot move. Therefore, to compensate, when the light shoots out, the heavy car must recoil backward. When the light hits the opposite wall, giving its energy back, the car stops rolling.
The entire car shifts position to perfectly balance the movement of the light's energy.
Let's map that logic perfectly to what's happening here. The flash of light carries an energy U across the length of the car. For the heavy car to physically recoil, the light itself must be carrying a momentum equal to U divided by C. The invisible field energy shooting across the empty space inside the boxcar forces the massive car to physically roll in the opposite direction. It mathematically and physically proves that energy in transit absolutely must carry momentum.
And let's go back to that absurd circulating whirlpool of energy around the static magnet in charge. Looking at the boxcar scenario again, if we shoot light downwards while moving, the light must carry momentum to conserve the angular momentum about point P. Without this invisible field carrying momentum, the foundational laws of the universe simply fall apart. When you turn off an electromagnet near some charges, the angular momentum stored in that invisible circulating field is actually released, and it can physically spin a disk. That absurd whirlpool of energy is secretly holding the angular momentum required to balance the universe.
Which leaves us with a truly profound realization to end on. If the space around us isn't empty at all, if invisible electromagnetic fields are constantly carrying flowing energy and physical momentum, powering our devices from the void and holding the fundamental laws of physics together, what else is hiding in empty space? The next time you look at the seemingly empty air around you, remember, your intuition is just the surface. Reality is far more complex and honestly, far more fascinating. Thank you so much for exploring this with me today, and keep questioning what you see.
Light, radio waves, the very chemistry of our own bodies. I mean, they're all governed by one of the most successful and genuinely beautiful theoretical structures ever built by human minds, classical electromagnetism. Welcome to this explainer. Today, we're diving into a massive secret that's basically been hiding in plain sight, because deep down, this tremendous, hyper-successful edifice has a fatal flaw. When you push the theory to its absolute limit, it just breaks. And understanding exactly why it breaks, well, that actually strikes at the heart of what makes up everything around us, including you and me. You know, no one described this failure better than the legendary physicist Richard Feynman. He famously said, "This tremendous edifice ultimately falls on its face." And here's the core problem. When classical mechanics and electromagnetism try to calculate the energy of a simple point charge, something like an electron, they just hit an absolute brick wall. Because the energy of an electric field increases so drastically the closer you get to the center of the charge, if you assume the electron is a true point with a radius of literally 0, the calculation spits out an impossible result. You get infinite energy. Now, infinite energy might sound like, just a really annoying math glitch, but it actually opens the door to something incredibly profound. When I first read about this, it completely blew my mind. It leads us straight to this fascinating question. What if the mass of everything in the universe is just an illusion created by electricity? What if a charged particle's mass isn't mechanical or physical mass at all, but is purely the momentum of its own electromagnetic field just dragging along with it? Section 1. Is mass an illusion? So before relativity came along, the origin of mass was completely unexplained. Objects just sort of carried mass, right? But the laws of electrodynamics offered physicists this thrilling possibility, a grand opportunity to understand the origin of mass entirely through electrical forces. Just look at the momentum density here, that's represented by the vector g. When an electron moves through space, it creates both an electric field E and a magnetic field B. Together, they create a momentum density in the space surrounding the electron that's directly proportional to its velocity. It acts exactly as if the particle has mass. For a brief, glorious moment, physicists really thought they had solved the universe. Mass is just the effect of electrodynamics. But here's where the dream kind of turns into a nightmare. If you calculate the electromagnetic mass based on its momentum on one side, you get a formula with a coefficient of 2/3. But on the other side, if you calculate the mass based on the energy of the field, especially after Einstein came along and proved that energy equals mass times the speed of light squared, you get a totally different formula with a coefficient of 1/2. So the absolute crucial point here is the theory contradicts itself. The two calculations just don't match. Something massive is missing. Section 2, the rubber band problem. To figure out what was missing, physicists realized they'd actually forgotten something fundamental about the electron itself. Think about an electron for a second. It's a tiny sphere of negative charge, right? Well, what do negative charges do to other negative charges? They repel. So theoretically, the electron should instantly, violently explode. To keep the electron together, there has to be some other kind of force pulling it inward.
These mysterious, non-electrical forces were named Poincaré stresses after the physicist who proposed them. You can basically think of them as tiny subatomic rubber bands holding the charge together. Now, if you include the energy of these rubber bands, the math perfectly balances out. But it completely ruins the elegant idea that mass is purely electromagnetic, because now we've had to invent these magical non-electrical rubber bands just to make the equations work.
Section 3. An electron pushing itself. And honestly, the strangeness doesn't even stop there. If an electron has mass, you have to exert a force to accelerate it. We know it radiates energy when it accelerates, so there must be a resistance force holding it back. But if the electron is totally alone in an empty vacuum, what on earth is pushing back on it? The bizarre answer is, the electron is pushing on itself. This took me a minute to wrap my head around, but let's walk through exactly how that's even possible. Step 1. When an electron is at rest, all its internal repulsive forces balance out perfectly in pairs. There's no net force. Step 2. When the electron accelerates, the electromagnetic influence takes actual time to travel from one side of the electron to the other. That time delay is called retardation. Step 3. Because of this tiny delay, the forces from the back of the electron reaching the front are based on where the back used to be. The forces are no longer balanced. The electron literally exerts a force on itself, holding itself back by its own bootstraps.
Notice the arrows on the accelerating electron we're looking at here. Because of that time delay we just talked about, the force arrows don't cancel out anymore. But here is the fatal mathematical trap. The equation for this self-force has a term that divides by the radius of the electron. So once again, if we assume the electron is a point charge with a radius of 0, the self-force becomes infinite. The classical theory has completely, irreversibly cornered itself.
Section 4. Modifying the laws of nature.
So, what do brilliant scientists do when their absolute best theory gives them impossible infinities? Well, they rewrite the rules. Look at the incredibly tight knots people tied themselves into trying to get a working theory of the electron. Born and Infeld tried making Maxwell's equations nonlinear. Dirac proposed this mind-bending idea where an electron reacts to a mix of standard waves and advanced waves that literally travel backward in time. Wheeler and Feynman suggested the resistance comes from all the charges in the universe reacting backwards in time. And Bob tried modifying the very concept of distance itself. For instance, check out Bob's approach. He tried to fix the equations by mathematically decreeing that a charge only feels an effect from another point in spacetime if this strict, narrow spike function, f of s squared, is satisfied. It was a mathematically beautiful attempt to get a finite mass. But, just like all the other wild theories we just looked at, it suffered a fatal blow. It failed completely when combined with the messy realities of quantum mechanics. To this day, nobody has successfully merged a fix for this classical problem into a self-consistent quantum theory.
Section 5. A mystery that survives today. Now, you might be sitting there thinking, okay, why don't we just throw this whole concept of electromagnetic mass out the window and start over? Well, because we have hard physical proof that it's real. Nature has actually given us identical particles that interact using the exact same strong nuclear forces, but have different electrical charges. A proton and a neutron act exactly the same under the strong force, yet the neutron is slightly heavier. Or look at the neutral pi meson compared to the charged pi meson. The charged one is about 4.6 mega-electron volts heavier. That extra mass, it is almost certainly the literal physical weight of the electromagnetic field itself. Now, actually, you might have noticed on that last slide that the neutron is heavier than the positively charged proton, which seems totally backward if charge adds mass. But the secret lies in its internal structure. The neutron isn't just some empty neutral sphere. It has a deeply complex internal makeup. It actually spends some of its time as a positively charged proton surrounded by a cloud of negative pi mesons. It has internal magnetic moments, internal charges. The electrical forces inside are just incredibly complex, and all of that contributes to its electromagnetic mass. So the mass difference is real, it's measurable, and it's definitely electrical. But just when you think you finally have a handle on the mystery of the electron's mass, the universe throws a massive curveball at you, and that curveball is the number 206.77. See, there's a particle called a muon. It interacts with the exact same fields as the electron. It completely lacks nuclear forces, just like the electron. It does absolutely nothing different from an electron, except it is exactly 206.77 times heavier. Which brings us to our final, lingering puzzle today. Even if someone, someday, figures out the math that perfectly calculates the electromagnetic mass of the electron, they're going to immediately run face first into an even bigger wall. If the electron and the muon are fundamentally identical in their electrical interactions, why on earth does the muon have so much more mass? Is mass a physical reality, an electrical illusion, or something even stranger that we just haven't discovered yet? That question remains right at the very frontier of modern physics. Thanks for exploring this massive mystery with me, and I'll see you next time.
Welcome to The Explainer. I am so thrilled you're joining us today. We're going to embark on a really fascinating journey to demystify one of the coolest aspects of electromagnetism, which is how we actually control and direct the tiny, completely invisible building blocks of our universe. Our goal today is to start small, literally looking at a single, isolated particle. And then we'll scale all the way up to some of the most massive, complex machines ever engineered by humanity. It's a huge leap in scale, so let's jump right in and uncover how it all works.
So let me throw this question out there. How exactly do we steer a single, completely invisible particle well enough to theoretically photograph a molecule of DNA? Or for that matter, how do we keep billions of them perfectly aligned inside massive, miles-long particle accelerators? I mean, it sounds like absolute magic, right? But it's actually pure, elegant physics. Understanding this is absolutely crucial because these principles are literally the hidden gears driving modern science and technology.
All right, let's get into Section 1, Particles in Uniform Fields.
Okay, let's dive into this slide. To start building these complex machines, we first have to establish the baseline rules of how these fields move a single particle. If you just drop a charged particle into a uniform electric field, the result is fairly straightforward, right? It just accelerates in a straight line. But a uniform magnetic field? Well, that's where things get interesting. A magnetic force always pushes at a right angle to the particle's motion. Notice the diagram on the left. If the particle is moving perfectly perpendicular to the field, it gets locked into a continuous circle. But check out the trajectory on the right. If the particle has a little bit of forward momentum along the direction of the magnetic field, well, that forward motion isn't affected at all. So you combine a forward drift with a circular push, and you get this beautiful, sweeping cylindrical helix.
Moving right along to Section 2, Measuring Particle Momentum.
Now that we know a magnetic field forces these particles into circles, we can use this geometric quirk for a really practical application, actually sorting and measuring them. The crucial takeaway here is that the radius of a particle's circular orbit is directly proportional to its momentum. So a faster, heavier particle takes a much wider turn, while a slower, lighter one cuts a really tight corner. We can exploit this by building what's known as a momentum spectrometer. You shoot a beam of various particles into a uniform magnetic field, and they just fan right out. The field neatly sorts them. We place a detector at a specific distance, like point C on the diagram here, and we can precisely focus and count only the particles that have the exact momentum required to curve at that specific radius. And this brilliantly illustrates an even more advanced setup, the axial field spectrometer. By using an elliptical coil to create a specific uniform field inside, we aren't just relying on particles entering in perfectly straight lines anymore. This device can actually accept particles spraying out from a source in a much wider solid angle. Even if they're entering at totally different trajectories, particles with the same momentum travel in those helical paths we saw a minute ago and converge back to a single focal point near a detector aperture. It's essentially like a giant funnel that perfectly isolates particles by their momentum.
Which brings us to Section 3, Focusing with Particle Lenses.
So we've seen how to analyze particles, but what if we want to actively control them? We can actually bend beams exactly like a glass lens bends light, using an electrostatic lens. Let's break down the complex physics of how this happens into 4 distinct steps. When an electron enters the lens, it first gets a sidewise kick toward the center axis. But as it moves through the varying electric field into the next region, it accelerates. Because it's moving faster, it spends less time in that second region, meaning the outward kick it gets there is weaker than the inward kick it just received. Even as the forces flip later on in the lens, the particle always spends more time in the regions pushing it inward than the regions pushing it outward, resulting in a net inward impulse.
If you look directly at this visual of the curved lines representing the electric field between the charged electrodes, you can see how the particle's trajectory dips slightly, but ultimately bends right toward the central axis. The absolute brilliance of this design is that the net impulse pushing the electron toward the center is perfectly proportional to its distance from the axis. And guess what? That is the exact mathematical definition of a lens. This is exactly how we focus electron beams to paint those glowing pictures on old-school cathode ray tube televisions. Let's look at Section 4, Limits of Electron Microscopes. If we can focus electron beams just like light, well, we should be able to build a microscope out of them, right? I absolutely love this aspirational quote from the source text. Biology would be easy. We would have a photograph of the DNA structure. Traditional light microscopes are fundamentally limited by the wavelength of visible light, which is about 5,000 angstroms. But a 50 kilovolt electron, its wavelength is a mere 0.05 angstroms. Since atoms are roughly 1 or 2 angstroms apart, an electron microscope theoretically gives us the resolving power to physically look at individual atoms in chemical compounds. It promises a world where we could simply snap a photo of a complex organic molecule to understand it. But, biology is rarely that easy. Enter the villain of our story, spherical aberration. This is a geometric defect inherent to lenses. Because of spherical aberration, we just cannot build an electron lens with a wide open aperture. And because we're forced to use very narrow lens openings to avoid this defect, our actual practical resolving power is restricted to about 20 angstroms. So we are agonizingly close to seeing individual atoms, but they remain just slightly blurred out of focus.
Direct your attention to the slide here, and you'll see exactly how this happens. Notice how the electron pathways, or rays, that are far from the central axis are bent way too sharply. They cross the center line well before the rays that stay nearer to the axis. They totally fail to meet at a single, crisp focal point. And the really heartbreaking physics of this situation is that it has been mathematically proven that any symmetric electrostatic or magnetic lens must have an irreducible amount of this spherical aberration. It's simply a hard limit of the symmetric geometry.
Okay, flipping the script entirely. Section 5, Taming Particle Accelerators.
So, we've looked at the microscopic scale. Now let's scale things up massively. We just saw how to bend one particle in a tiny tube. But how on earth do you keep a billion fast-moving particles from drifting off course and crashing into the metal walls of a vacuum tube that is literally miles long? If the magnetic field is even a fraction of a percent off, the particles will just slowly spiral outward or dive straight into the floor.
Now, what's really interesting about this slide is the visual contrast showing two potential solutions. Physicists use a magnetic field gradient to create a restoring force. This field slope is called the field index, or n. On the left, we see a stable orbit where the particle oscillates nicely around the ideal path because n is perfectly balanced between 0 and -1. This provides both radial inward focusing and vertical focusing to keep it from hitting the ceiling. But on the right, if that gradient is too large, a large negative slope, the particle wildly spirals out of control and crashes. Balancing this n value is known as weak focusing, and honestly, it severely limits how powerful we can make these machines.
To break past this limitation, physicists developed a genuinely revolutionary and completely counterintuitive concept called alternating gradient focusing. It relies on using alternating magnetic lenses, one that strongly focuses the beam, immediately followed by one that violently defocuses it. And somehow, crazy enough, this creates a net, incredibly powerful focusing force that keeps billions of straying particles perfectly in line.
So how does combining a focusing force with a defocusing force actually help? Well, let's heavily lean into this mechanical analogy right here. Imagine a pendulum. Normally, it just hangs straight down, right? But if you connect the pivot to a motor that rapidly vibrates it up and down, a really bizarre thing happens. You can balance the pendulum completely upside down. When the pivot accelerates downward, the bob tends to fall inward. When it accelerates upward, it's pushed outward. The force is alternating between helping and hurting, but the net average effect is a restoring force toward the center axis. Alternating the magnetic gradients in an accelerator does the exact same thing to wandering particles.
And here is how that alternating gradient is actually achieved in practice. This is a horizontal focusing quadrupole lens. It features 4 magnetic poles. If a positively charged particle drifts horizontally to the left or right, the magnetic field lines push it directly back toward the center. If it drifts vertically, it gets pushed away. By lining up a series of these quadrupoles and rotating every second one by 90 degrees, you create that incredible alternating focus-defocus effect. It functions exactly like a powerful compound optical lens, but for a particle beam.
Finally, Section 6, Crossed Fields and Cycloids.
Up until now, we've looked at electric and magnetic fields separately. Let's move to gyroscope and see how this builds when we overlap them at right angles. Imagine a particle in a uniform magnetic field going in its normal circle. But now we add an electric field pointing straight up. When the particle swings up, moving with the electric field, it gains speed. Because it's moving faster, the magnetic field bends it less. When it swings back down against the electric field, it loses speed, and the magnetic field curves it much more tightly.
The end result of speeding up and slowing down in this crossed field is this beautifully looping trajectory called a cycloid. Mathematically, it is just a uniform circular motion superimposed on a constant sideways drift. It's kind of like watching a point on a bicycle wheel as the bicycle rolls down the street. And this isn't just a fun math trick. This exact sidewise drift motion of electrons inside crossed fields happens to be the foundational physics behind the magnetron tube, which is the device inside your everyday microwave that generates the energy to heat up your lunch.
Which leaves us with a truly astonishing realization. From the theoretical dream of directly photographing the structure of DNA, to keeping a billion high-energy particles perfectly contained in a multi-billion-dollar accelerator, all the way down to simply heating up yesterday's leftovers, the exact same foundational rules apply. By understanding just a few uniform fields, we can literally shape the world. So I'll leave you with this to ponder. From seeing atoms to heating our lunch, how else are these invisible, perfectly steerable forces silently shaping the technology all around you right now? Thank you so much for joining me on this explainer, and keep questioning the invisible world around you.
Welcome to the Explainer. Today we're diving into a microscopic world that literally dictates the behavior of every single object you touch. From the smartphone in your hand to the massive steel beams holding up the ceiling above you, we kind of assume this stuff is just perfectly solid all the way down, right? But beneath the surface, there's a highly organized geometric reality running the whole show.
Let's start with a really cool mystery. Why is pure iron actually incredibly soft and pliable, but steel, which is fundamentally almost entirely just iron, strong enough to build massive skyscrapers and frame cars? Well, the answer is a massive paradox. It sounds totally backward, but the perfect geometry of a crystal is exactly what makes it weak. Actually, scratch that. It's the structural flaws, the imperfections, that give materials their true strength.
Section 1. The hidden wallpaper, crystal lattices.
Okay, so to get this, we first need to know what a crystal actually is. And physicists don't just mean quartz crystals or magic rocks here. They're talking about a structure that essentially acts like three-dimensional wallpaper. Think about a repeating floral design. The elements form these patterns that just go on and on. Over millions of years, as materials are churned around inside the Earth, atoms drift and bump into each other trillions of times a second. Eventually, they find the absolute lowest possible energy state, and boom, they lock together into an endlessly repeating pattern.
We call this repeated arrangement a crystal lattice. Imagine a crowded room full of exhausted dancers who suddenly find the absolute perfect arrangement where everyone finally has enough space to rest. That lowest energy configuration creates this strict geometric building block for everything. We're talking salt, diamonds, copper wires, you name it. And once that pattern starts, it desperately wants to keep perfectly repeating forever.
Section 2. The rules of symmetry. Mathematical limits.
So, when you start building these structures, you quickly hit an unbreakable universal law. And it brings up a really fun mathematical question. You've probably seen square crystals, or even hexagons, like a snowflake, right? But have you ever wondered why there are absolutely zero pentagon-shaped crystals in nature, no matter where you look? Well, mathematically, it's just not possible.
And here is exactly why. If you trace the lines connecting these atoms, you instantly fall into a geometric trap. You literally cannot close the gap. To make a five-fold pentagonal pattern work, the atoms would either have to aggressively overlap each other, or the lines would fall maddeningly short of reaching the next spot. It's a fundamental limit. No matter how hard nature tries, you simply can't tile a flat floor or a 3D space with regular pentagons without leaving gaping, empty voids everywhere.
The crucial takeaway here is that pentagonal and even octagonal shapes are strictly forbidden by geometry. In a repeating lattice, only specific folds can tile space perfectly without gaps or overlaps. We're talking 1, 2, 3, 4, and 6-fold symmetry. That's it. It's kind of mind-bending when you really think about it. The endless, infinite complexity of the physical universe is completely constrained by this incredibly short mathematical list.
Section 3. The illusion of strength. Why metals are soft.
Now, you would naturally expect these rigid, beautifully symmetrical, mathematically perfect structures to be incredibly strong, right? But here is the massive twist. Pure metals, which are built on these perfect crystalline lattices, are actually incredibly soft. If you apply a shear force to a pure metal, you might think you have to push hard enough to drag an entire, massive layer of millions of atoms over the bottom layer all at once. If that were the case, metals would be impossibly strong. But reality? The crystal slips just one atom at a time. It's exactly like trying to move a massive, heavy rug across a floor. You don't grab the edge and yank the whole thing at once. You make a fold, and you push a wrinkle across it.
take a look at how that slippage actually plays out. It takes way less energy to lift one single atom over the hump of the atom below it than it does to shift an entire infinite row all at the exact same time. Once the force starts the process, that little empty gap, that wrinkle, quickly travels down the line, and the entire layer shifts almost effortlessly. This microscopic jumping mechanism is exactly why pure, perfect metals will easily bend right in your hands.
Section 4. The power of imperfections, dislocations, and strength.
And this brings us to the real heroes of solid matter. If you want to make a material strong, you don't make it more perfect, you actually introduce defects. Look closely at the center here. See that missing row of atoms? That's called a dislocation. Just like the wrinkle in our rug, these dislocations can move freely through a perfectly repeating lattice when force is applied. But what happens if that wrinkle suddenly smashes into a giant boulder? It gets totally stuck. And stopping these dislocations from moving is the precise mechanism that gives metals their incredible strength.
Let's look at a real-world example. If you take soft, pure iron and mix in a tiny amount of carbon, those carbon atoms precipitate out and create microscopic distortions all throughout the iron lattice. The dislocations can no longer effortlessly slide past each other because they hit these carbon roadblocks. That simple roadblock mechanism is literally the magic that transforms soft iron into the hard steel we use to build giant cities. We literally engineer flaws to create strength.
But wait, imperfections aren't just for strength, they are fundamentally essential for existence. Think about how a crystal grows in the first place. An atom drifting by wants to attach where it has the most bonds, right? To lower its energy state. But if an atom lands on a perfectly flat, flawless surface, it only has one single bond holding it from below. It's super likely to just bounce right off into the abyss. So if atoms just bounce off perfectly flat surfaces, how do huge crystals ever manage to form?
Check out this brilliant structural flaw. It's called a screw dislocation. This mismatch in the atomic lattice creates a permanent step, or a ledge. And the absolute magic of this step is that no matter how many thousands of atoms you pile onto it, the ledge never disappears. It just spirals upward endlessly, creating a continuous, infinite staircase for new atoms to land on.
You can really see how the growth process takes advantage of this. Atoms preferentially cling to the inner corner of that ledge, because right there, they get to form bonds on multiple sides, below them and beside them, locking them tightly into place. This is a profound paradox in nature. Crystals actually require a built-in dislocation, a fundamental break in their perfection, in order to grow into the giant, beautiful structures we see in the natural world. Without that flaw, growth would literally stall out cold.
Section 5. The bubble universe, a soap bubble model.
Now, because we can't easily see individual atomic movements with our own naked eyes, two brilliant scientists named Sir Lawrence Bragg and J.F. Nye came up with an absolutely ingenious way to visualize all of this. They built these physical apparatuses to blow thousands of tiny, perfectly uniform soap bubbles, some as small as 1/10 of a millimeter. They created these massive rafts of bubbles floating on a liquid solution. It is completely wild to think about, but these macroscopic soap bubbles flawlessly mimic the quantum mechanical behavior of atomic crystal structures.
As Bragg and Nye noted, the bubbles behave exactly like a sea of electrons in a metal. The bubbles are held together by a general capillary attraction, that sticky surface tension pulling them together into a tight formation. Because there's no friction between them, they slide past each other, they form distinct crystal grain boundaries, and they visually prove right before our eyes how those dislocations, those wrinkles in the rug we talked about, actually move across the lattice when physical stress is applied. It's a real game changer for visualizing this stuff.
Section 6. Conclusion, Strength in Flaws.
To wrap up this explainer, we've gone on a pretty wild ride from theoretical 3D wallpaper to the mathematical impossibility of pentagons, all the way to using literal soap bubbles to prove the hidden physics of atomic structures. It kind of changes how you view the physical world, doesn't it? Next time you look at a towering skyscraper or even just bend a simple copper wire, I hope you remember that it's not geometric perfection keeping things intact. The flaws, the wrinkles, and the missing pieces are exactly what give the materials of our modern world their true, unbreakable strength. Thanks for hanging out with me for this explainer, and keep questioning the structures around you.
Welcome to this explainer. Okay, let's just admit a fascinating little secret right off the bat. Physicists usually oversimplify the world. I mean, when we first learn basic science, we're taught that everything acts the exact same way in every single direction. But as you probably know, the real world just doesn't work like that. Today, we're going to dive headfirst into the messy, multidirectional reality of the physical universe, and we're going to use a pretty brilliant mathematical tool called tensors to understand exactly how it all works. Here's our roadmap for today. We'll be looking at physics in the real world, what is a tensor, visualizing the energy ellipsoid, tensors in everyday motion, the tensor of stress, and finally, venturing into the fourth dimension. Section 1, Physics in the Real World, the lie of basic science. So, you know how physicists have a habit of assuming things are identical in all directions? It's a nice, simple concept called being isotropic. But what actually happens when you push one way and an object reacts in another? Imagine pushing a block forward, but instead of going straight, it slides sideways. That happens because the real world is anisotropic, meaning a material's properties actually vary depending on the direction you measure them. Take a look at how this plays out in an anisotropic crystal, something like calcite. You've got an applied electric field pushing one way, but the resulting polarization, it points in a completely different direction. The internal atomic charges are actually quite stiff and resist moving side to side, so the displacement just doesn't line up with the external force. Section 2. What is a tensor? Tracking the multidirectional. To wrangle this wild problem of multidirectional properties, we need to introduce our mathematical hero, the tensor. By definition, it's a set of 9 coefficients describing physical properties that vary by direction. Basically, it's the ultimate bookkeeping system for a reality where pushing forward might result in moving forward, up, and to the left all at once. Now, rather than some terrifying mathematical beast, a tensor is really just a simple 3x3 grid. These 9 numbers tell us exactly how much a force in the x, y, or z direction contributes to the result in those exact same dimensions. So, if an electric field has components along x, y, and z, the resulting polarization is just the sum of the contributions from all 3. These 9 coefficients form the tensor of polarizability. Think of it as the complete, unique fingerprint of the crystal. Section 3. Visualizing the energy ellipsoid. Giving math a shape. To make this a little less abstract, let's actually give these numbers a physical shape by looking at the energy required to polarize our crystal. If we plot the electric field needed to reach a specific energy density in just 2 dimensions, we get an ellipse. Why? Because the energy for any field is always positive and finite. It literally takes different amounts of force in the x versus the y direction to achieve the exact same energy, which creates this beautiful geometric shape. It's a really wonderful way of visualizing the math. Now let's bump this up to 3 dimensions and see how it builds into an energy ellipsoid, where the shape and orientation of this 3D object uniquely characterizes the tensor polarizability of any crystal. Notice those 3 principal axes. No matter how complicated the crystal is, we can always tilt our perspective to align with these axes. And when we do that, our messy grid of 9 numbers simplifies beautifully down to just 3 diagonal components. The physical symmetry of the crystal itself literally dictates the shape of this ellipsoid. Section 4. Tensors in everyday motion. The tensor of inertia. And hey, tensors aren't just restricted to microscopic crystal grids. They totally govern the motion of the everyday spinning solid objects all around us, too. Take a spinning rectangular block, for example. Because its moment of inertia is different along its 3 principal axes, the direction it spins isn't perfectly aligned with the forces actually making it spin. You can clearly see that the angular velocity, which is the axis it's spinning around, points in a totally different direction from the angular momentum. This perfectly illustrates that angular velocity and angular momentum are absolutely not always parallel in the physical world, and that right there is exactly why we need the tensor of inertia to bridge the gap. Just like our crystal reacting sideways to an electric field, a solid block reacts with a complex, direction-dependent momentum when you try to spin it. Section 5. The tensor of stress. Cutting through jello. All right, let's imagine pushing and slicing through a big block of jello to understand the internal forces, what we call stresses, inside a solid material. When you press on a solid, internal forces between neighboring parts keep the material in place. We define the stress tensor by making 3 imaginary microscopic cuts corresponding to the x, y, and z axes, and we track the shear and pressure forces across each tiny area. While static liquids only push straight outward, solids have shear forces. Those are forces that push tangentially, actively trying to slide the material sideways. As we break these forces down into rectangular components for each of those imaginary cuts, we naturally build up another 9-number tensor. You'll notice how a force across an area perpendicular to the x-axis gets resolved into an x, y, and z component. We do this for all 3 directions to map exactly how the jello is being pushed, pulled, and sheared internally. Now, since our jello block isn't just spontaneously spinning around on its own, the shear forces on this tiny unit cube must balance out into this incredibly elegant equilibrium, proving our stress tensor is perfectly symmetric. Think about it. The pulling forces on the top and right side must be exactly balanced by the bottom and left side, otherwise the cube would just start twisting. The symmetry means the stress tensor, much like the polarization tensor we looked at earlier, can be perfectly mapped by a 3D ellipsoid.
Section 6. Into the 4th dimension, the space-time tensor. Okay, let's really scale this up. In 4 dimensions, we expand our stress tensor to track not just the flow of momentum in 3 spatial directions, but we add a time component that traps the density and flow of energy itself. Just as electric charge has a density and a flow, momentum in space-time has spatial components and a time component. Bringing all of this together gives us the magnificent 4-dimensional stress-energy tensor. Applying this whole concept to empty space leaves us with a truly profound realization. Electromagnetic fields aren't just abstract math. No, they act as a 4-dimensional tensor, exerting actual, measurable physical pressure and tension on space-time itself. Energy flow and momentum density are intrinsically, beautifully linked. So the next time you step outside and feel the heat of the sun on your face, ask yourself, how much invisible geometric tension is that light exerting on the very fabric of reality you're standing in?
All right, let's dive right into this explainer. Today, we're unpacking Richard Feynman's literally brilliant breakdown of how electromagnetic waves interact with the world around us. Specifically, we're digging into his lectures on the refractive index of dense materials. And honestly, this is going to completely change how you look at the physical objects you interact with every single day.
So let's start with a bit of a mystery. Why is it that a dense block of metal stops visible light totally cold, but it lets high-energy X-rays pass right through as if the metal were just, completely transparent? Think about that for a second. The actual material hasn't changed at all. The atomic structure is exactly the same. Yet one type of light hits an absolute brick wall, and another just sails right through without a care in the world. Well, by the end of this explainer, you're going to know exactly why. To solve this mystery, we're going to take a journey from the microscopic to the macroscopic, moving through 5 key stages. 1. Light in a crowded room. 2. The complex math of light. 3. Mixing it up with sugar water. 4. Metals and free electrons. And 5. Skin depth and plasma.
Okay, section 1. Light in a crowded room, where atoms essentially act as tiny springs.
Now, in a lot of basic physics, we tend to look at gases where atoms are totally isolated. They're sitting far apart, just reacting independently to an incoming light wave. But dense materials, stuff like glass, water, or a solid crystal, they are a completely different beast. The atoms there are packed so tightly together, literally elbow to elbow. So they aren't just driven by the incoming wave, they're also reacting to the radiated waves of all their neighbors. It's kind of like trying to dance in an empty room versus a completely packed nightclub. In the dense material, the electric field of the light wave polarizes the molecules. It essentially stretches them into positive and negative ends, which produces these oscillating dipole moments. The atoms basically act like tiny masses bouncing on springs, and that incredibly crowded environment drastically changes the rules for how light moves through them.
Which brings us to section 2, the complex math of light. Imaginary math, real consequences.
See, because of all these interacting atoms and the sheer resistance to their motion, the index of refraction isn't just some simple single number anymore. It becomes what physicists call complex. It has a real part, which is what we typically think of as refraction, how much the light slows down and bends, but it also has an imaginary part. Now, don't let the word imaginary fool you here. In physics, this imaginary math has very real physical consequences. Specifically, it dictates the attenuation and the energy loss of that light wave as it literally fights its way through the dense material.
And when you graph it out, it's actually pretty wild to see. The strength of the electric field goes up and down as the wave moves through the material, sure, but the overall height, the amplitude, is caught in this strict exponential decay. It just fades out over distance. And that exact curve, that's directly dictated by the imaginary part of our complex index equation.
The wave is quite literally losing energy, fading out because of the resistance or the damping force in those tiny atomic oscillators. This is the fundamental microscopic theory behind exactly why materials absorb light.
All right, let's move to section 3, mixing it up. Sugar water, grounding the theory in reality.
Because, theory is just theory until we actually test it. Feynman uses a genuinely great practical example here, mixing sucrose, just plain sugar, into water. If our mathematical theory about atomic polarizability is right, the polarizability of a sugar molecule shouldn't really change whether it's floating freely in a weak dilute solution or packed tightly into a solid crystal. And guess what? When you map the refractive index across different concentrations of sugar, from pure water all the way up to a solid crystal, the calculated polarizability stays almost exactly the same. It's right around 0.210 all across the board. This is a massive win for the theory. It absolutely proves that our microscopic model of atoms acting as complex, interacting oscillators perfectly scales up to the physical liquids and solids we handle every single day.
So, let's shift gears for section 4. Metals and free electrons, the chaos inside a conductor.
When we look at a metal, the rules change entirely because the electrons aren't bound to atoms like neat little springs anymore. Metals are absolutely full of free electrons. So when an electric field from a light wave hits these free electrons, they don't just vibrate neatly in place. They drift. They go on this wild, totally jagged path from one scattering collision to the next. Between collisions, sure, they move freely, but the collisions themselves create a massive drag force. The resistance is just unbelievably high compared to an insulator.
And that brings us to section 5, skin depth and plasma, the cosmic speed limits of light.
This chaotic, high-drag environment in a metal drastically alters how electromagnetic waves behave. Because of that massive drag from the free electrons, lower-frequency waves, like radio waves or visible light, are killed off incredibly quickly. This gives us the concept of skin depth. Skin depth is the extremely short distance an electromagnetic wave can actually penetrate into a metal before its amplitude drops by roughly a third. And we aren't talking about meters here, we're usually talking about microscopic fractions of a millimeter.
To really put that crazy rapid drop-off into perspective, imagine blasting a 10,000 megacycle microwave at a solid block of copper. That wave dies out in less than a 10,000th of a centimeter. It literally barely scratches the surface. This is exactly why the inside of your microwave oven at home or high-end electronics only need a microscopic plating of silver or gold to block waves entirely. The current is only active in a layer that's as incredibly thin as the skin depth.
But here is the grand finale, the answer to that mystery we started with. While low-frequency waves, like radio and visible light, get totally absorbed or reflected within that tiny skin depth, high-frequency waves tell a completely different story. See, there's a universal threshold in physics known as the plasma frequency. If a wave's frequency is below this threshold, it's blocked, no go. But if a wave's frequency is intensely high, way higher than the plasma frequency, like X-rays or even ultraviolet light for certain metals, the electrons simply cannot react fast enough to stop it, so the wave just sails right through. The metal's index of refraction basically becomes real and less than 1, making that solid, dense block of metal functionally transparent.
Which leaves us with one final staggering thought to wrap up this explainer. The exact same plasma frequency rules that dictate why the copper in your smartphone drops its cell signal when you step into a metal elevator, well, those are the exact same rules that dictate how radio waves interact with the plasma of Earth's ionosphere and even the atmospheres of distant stars. This unbelievable universality of physics really should leave us all wondering, if a simple block of metal holds the exact same mathematical secrets as the cosmos, what other profound rules are just hiding in plain sight in the everyday materials all around us?
Welcome to today's explainer, where we're going to be looking way past the memorized formulas of physics to understand the hidden machinery of how light actually interacts with surfaces. We interact with light literally every single waking second of our lives, right? Yet the exact mechanics of what happens right at the boundary of two materials is wonderfully, beautifully complex. So today, we're taking a microscopic magnifying glass to the exact fraction of a second when light hits a surface. To kick things off, I want you to think about this central mystery. Why is a mirror reflective, but glass is totally clear? You know, it kind of sounds like a question a 5-year-old might ask, but answering it actually forces us to challenge the basic laws of reflection that we take for granted every single day. Most of us just accept that light passes through some things and bounces off others, end of story. But the universe doesn't operate on just because. There is a rigorous microscopic mechanism dictating every single bounce and every single bend. To help guide us through this, we're relying on the legendary physicist Richard Feynman. He actually sets up the physics of electromagnetic waves by jokingly introducing the following terrifying problem that was the ultimate test for graduate students back in 1890, which honestly sets the perfect tone for us. We are absolutely going to be playing with some intellectually challenging concepts today, but I promise we are going to make them incredibly accessible and honestly pretty fascinating. Okay, let's look at this geometry here to establish our baseline. This is probably knocking loose some memories from high school physics. You've got an incident light wave coming in from the top right, hitting a boundary. Some of it bounces off, that's your reflected wave, and some of it punches right through into the new material, bending as it goes, and that's your refracted or transmitted wave. And as we know, the angles of these waves are perfectly predictable. That predictability is entirely captured in a famous equation. Here it is, Snell's law. It simply states that the way light bends when crossing from one medium to another depends on the index of refraction, that's the little n value you see there, for each material. Basically, if you know the index of the air and the index of the glass, you can calculate the exact angle the light is going to bend. It's a beautifully neat rule. But we aren't here to just blindly accept the rule. We are here to ask, why does this law actually exist? What is physically happening to the electromagnetic fields to strictly enforce this mathematical rule? Let's dive right into Section 1, inside the boundary layer. To actually figure out why light reflects and refracts, Feynman gives us a really logical three-step procedure. First, instead of thinking of the boundary as an infinitely sharp wall, we assume it's just a very, very rapid transition layer. Second, we apply Maxwell's equations, which are basically the foundational laws of electromagnetism, to this unimaginably thin layer. And third, we mandate that the electric and magnetic fields from the incoming light wave must seamlessly match the fields on the other side of the boundary. Because, you can't have a mathematical break in reality. The fields absolutely have to connect. Now check this out. When we apply that math, we see a massive invisible spike because the physical transition between, let's say, air and glass is so sudden, the properties of the fields literally shoot off the charts right at the wall. But Maxwell's equations demand balance. If there is a whopping big spike on one side of the equation, there absolutely must be an equally huge spike on the other side to compensate. So here is the crucial point to take away from this. Matching these continuous waves perfectly across the boundary is exactly what physically forces the creation of a reflected wave. The incoming wave carries electric and magnetic fields. When they hit that boundary and experience that sudden spike in material properties, the only way the universe can balance the electromagnetic books, ensuring the fields remain perfectly continuous, is to instantly spawn a new wave traveling backward. So reflection isn't just light physically bouncing like a rubber ball hitting brick. It's actually a strict mathematical requirement of a continuous universe. All right, let's move on to Section 2, why metals shine. This all comes back to that index of refraction we mentioned earlier. For transparent materials, like glass, the index is what we call a real number, allowing waves to safely transmit and bend. But for metals, the math gets wild. Metals have an imaginary index of refraction. In the language of physics, a large imaginary index means waves are highly absorbed by the material. And here is the fantastic rule of thumb Feynman points out. If a material gets to be a very good absorber at any frequency, the waves are strongly reflected at the surface. Because the metal tries to absorb the light so rapidly, it triggers a really extreme version of that boundary spike we just talked about, causing almost 100% reflection. And we can actually see this exact concept play out in a totally unexpected way. A puddle of dried red ink on a glass plate. Red dye strongly absorbs the green frequencies of light. Because it is such a strong absorber of green, our new rule tells us it must also be a strong reflector of green. So if you shine white light on the back of dried red ink, you aren't just going to see a dull surface. It'll actually give off a distinct, shiny, metallic green reflection. Strong absorption literally creates a metallic shine. It's so completely counterintuitive, yet it perfectly validates the math. And that brings us to Section 3, jumping the gap. This is where things get truly bizarre. If light traveling inside a piece of glass hits the boundary with the air at a shallow enough angle, it doesn't escape. It reflects 100% right back into the glass. But wait, remember how we said fields absolutely must be continuous? The light wave doesn't just instantly drop to zero at the exact edge of the glass. The math predicts what's called an exponential tail, which is basically a tiny, invisible, phantom shadow of the electromagnetic field that extends just a microscopic distance out into the open air. If you bring a second piece of glass incredibly close to the first one, so close it enters that invisible tail, that fading electric field physically shakes the electrons in the new piece of glass, and suddenly, boom, a brand new transmitted wave is generated. And guys, this isn't just some mathematical quirk. It's a real, measurable effect that can be physically demonstrated. Now, with visible light, the gap has to be unimaginably tiny. But if you use microwaves, which have much longer wavelengths, that tail actually stretches out for centimeters. The source describes an experiment using microwaves and paraffin prisms. When the prisms are separated by a small air gap, the wave hits the edge, totally internally reflects, but its invisible tail reaches across empty space, touches the second prism, and the wave just continues on its way to the detector. The wave literally jumps the gap. It's mind-blowing. Learning this forces us to completely rethink what a boundary even is. The core takeaway here is that light doesn't care about solid walls the way we do. It only cares about maintaining the continuous flow of its electromagnetic fields, which leaves us with this pretty incredible thought to chew on. If light can maintain a phantom presence in empty air and literally jump an impossible gap to continue its journey, what else is sneaking past the seemingly solid boundaries of our physical world? It's an awesome quantum-like reminder that the universe is far more interconnected and far more fascinating than it appears on the surface. Thanks for joining me for this explainer. I'll see you next time.
All right, let's dive right into this explainer and uncover the hidden and, frankly, kind of mind-bending mechanics of magnetism in ordinary materials. You know, we're all super used to those heavy-duty magnets stuck to our fridges, but what you might not realize is that literally all ordinary matter has magnetic properties. It's this subtle, almost invisible world, and the journey to actually understand it, well, it completely breaks the rules of classical physics.
We've got a really fascinating journey mapped out today. We're going to cover the two kinds of magnetism, the classical physics guess to explain them, exactly why that classical guess completely fails, the mind-blowing quantum reality, and finally, the strange splitting of energy levels.
Starting off with Section 1, Two Kinds of Magnetism. Let's look at the physical reality we can actually see and measure in a lab.
It's honestly fascinating how everyday materials react to a strong magnetic field in two totally opposite ways. Imagine hanging a little cylinder of bismuth on a string right between the poles of a super powerful electromagnet. The bismuth actually pushes away from the high field region. It's literally repelled, but if you swap that out for a piece of aluminum, the aluminum gets gently pulled in towards a stronger field.
So, the big takeaway here is that ordinary magnetism comes in two weak flavors, diamagnetism and paramagnetism. Diamagnetism, which by the way all materials have, is that repelling force. It happens because turning on a magnetic field induces tiny opposing electrical currents inside the atoms themselves. It's kind of like a miniature version of Lenz's law. Then you have paramagnetism, which is the attractive force. This happens in substances where the atoms already have permanent magnetic moments, almost like tiny compass needles. When the external field turns on, these little atomic compasses try to line up with it, which causes the attraction. But as you can probably guess, the constant random thermal jittering of the atoms is always trying to mess up that nice, neat alignment.
Moving on to Section 2, the classical physics guess. Let's see how early physicists tried to figure this all out using the classical rules they knew.
They naturally tried to build a mental model of the atom based on stuff like planets and spinning tops. It seems incredibly logical, right? Picture an electron orbiting a nucleus, just like a planet orbiting the sun. Because the electron has mass and is moving in a circle, it has angular momentum, and since it's a moving electrical charge, it acts exactly like a tiny wire loop carrying a current. This circulating current then generates its own magnetic field, which is what we call a magnetic moment.
The classical assumption ties all of this together beautifully. The magnetic moment is directly tied to the angular momentum. Because the electron carries a negative charge, its magnetic moment points in the exact opposite direction of its angular momentum, perfectly perpendicular to the orbital plane. In classical physics, the ratio between these two is totally fixed. It's just the charge of the electron divided by twice its mass. Simple enough, right?
But here's where it gets highly dynamic. Because our little atomic magnet has angular momentum, making it essentially a microscopic gyroscope, a magnetic field doesn't just snap it into alignment like a regular compass resting on a table. Instead, the torque from the magnetic field causes the spinning atom to precess.
Think about how a spinning top behaves on a table. When an external magnetic field tries to twist the atomic magnet, that angular momentum makes the entire axis of the atom sweep out a cone.
It processes around the magnetic field at a very specific, predictable rate, which classical physics calls the Larmor frequency.
This precessing motion actually gives us our neat classical explanation for diamagnetism. As you slowly turn on a magnetic field, the rules of electromagnetism, specifically Faraday's law, tell us an electric field gets induced. This electric field twists the electrons, giving them a tiny bit of extra angular momentum. This added rotation creates a small, opposing magnetic moment. And boom, that's exactly why the bismuth we talked about earlier was pushed away. It really seems to perfectly explain the physical stuff we observe in the lab.
Which brings us to Section 3, Why Classical Physics Fails.
Okay, so everything we just went through sounds perfectly reasonable, right? Precessing orbits, induced current, a beautiful planetary model, but here is where we literally pull the rug right out from under classical physics. If you follow classical mechanics to its ultimate thermodynamic conclusion, you arrive at this absolute failure of the model. There's a famous quote that totally shatters it. According to classical mechanics, there can be no diamagnetism and no paramagnetism at all. None. Zero. The classical model actually destroys itself if you do the math all the way to the end. Let's look at why.
The whole problem lies in statistical mechanics. Think about a box full of particles. According to classical physics, the probability that a system will have a particular motion depends entirely on its energy. But here's the massive catch. A constant magnetic field does no actual work on a moving charge. It only changes its direction. Because the magnetic field doesn't change the total energy of motion, classical statistical mechanics proves that when their box reaches thermal equilibrium, all those beautifully induced diamagnetic and paramagnetic moments, they must perfectly cancel out. In a purely classical universe, at thermal equilibrium, average magnetic moments are exactly zero.
So how do we fix this? That leads us to Section 4, the quantum reality. To actually understand the physical world and why that piece of aluminum really gets pulled toward a magnet, we have to completely abandon classical mechanics and step into the incredibly weird realm of quantum mechanics. In the quantum world, angular momentum isn't just physical spinning that can point in any random direction. It's a completely different quantized property. The electrons aren't just little spheres spinning on their axes. They possess this intrinsic, fundamental property that we simply call spin.
And the quantum rules for spin dictate that our atomic magnets can't just tilt at any angle they please. Classically, a gyroscope can lean at, say, 30 degrees or 31.5 degrees, right? But a quantum system is locked into a strict menu of allowed orientations. We measure this total spin with a number designated as J, and it can only be an integer or a half integer. An electron, for instance, is permanently assigned a built-in spin of exactly 1/2, and its orientation along an axis, it can only jump in rigid, discrete steps.
What's totally wild is that the rules for the magnetic power of this spin are also completely different. Remember our classical guess? The one where the ratio of magnetic moment to angular momentum was perfectly fixed by mass and charge? Well, for an electron's pure quantum spin, that ratio, which physicists call the G-factor, is exactly 2, meaning it produces twice as much magnetism for its angular momentum as the classical orbital model predicted. There is absolutely zero classical explanation for this. It's purely a rule of the quantum universe, and it is fascinating.
Now for our final section, splitting energy levels.
So what actually happens when we put these locked quantum magnets into a strong magnetic field? Well, they definitely don't smoothly precess like a classical top slowing down. Because the vertical component of the atomic spin is restricted to those discrete jumps we just talked about, the magnetic energy of the atom is also sliced into specific, distinct stairs, rather than a continuous smooth slide. Basically, if you tell me the spin of the atom, that number J, quantum mechanics tells me its energy will split into exactly 2J plus 1 distinct levels.
This contrast is super clear when you look at different atomic systems. Take a complex atomic system with a spin of 3/2. Plug that into our 2J plus 1 formula, and you get exactly 4 possible energy stairs. The atom has to sit on one of those exact lines. Then contrast that with a simple isolated electron with its built-in spin of 1/2. It only has 2 possible energy states in a magnetic field. We colloquially call these states spin up and spin down. There is literally no in-between.
We've covered a lot today about the weak, ordinary magnetism of all matter. We've seen how classical physics utterly fails, and how the strange, quantized rules of electron spin swoop in to save the day. But, this leaves us with a massive, provocative mystery. We know that thermal energy at room temperature easily overpowers those weak alignments of paramagnetism we talked about. So, how in the world does a solid iron bar stay powerfully magnetic enough to stick to your fridge?
What massively strong quantum force is locking billions of those atomic compasses together against all odds? Well, that is the profound mystery of ferromagnetism, and exactly what you should be pondering as we wrap up this explainer.
Welcome to this explainer. Today, we're jumping headfirst into the bizarre reality of quantum angular momentum to see exactly how it builds our modern world. It's a pretty wild journey, taking us from highly abstract physics theory all the way to the life-saving technologies sitting in almost every hospital right now. Let's get into it. Now, if the word quantum immediately makes your brain hurt, hey, you're in good company. As the brilliant physicist Richard Feynman famously put it, actually, your minds will never become more advanced in the sense of being able to accept such a thing easily. The truth is, quantum mechanics is fundamentally unnatural to our everyday macro-level experience. So we're not going to try to force it to make classical sense. We're just going to lean right into the weirdness. Here's our roadmap for today. We've got 6 main stops: the quantum spin shock, proving it with Stern-Gerlach, tickling atoms with resonance, bulk magnetism and saturation, cooling toward absolute zero, and finally, nuclear magnetic resonance. Section 1. The quantum spin shock. Breaking classical expectations. When you put classical physics side by side with quantum mechanics, the absolute biggest shock is how subatomic angular momentum actually behaves. Classically, we expect smooth, continuous adjustments. You can tilt a normal bar magnet to literally any angle you want. But in the quantum realm, spin is locked. It completely ignores that smooth spectrum and snaps into very specific, discrete jumps, always existing in either integer or half-integer multiples of a set value. It's a totally different ballgame. To visualize this, classically, we totally expect an atomic magnet to wobble smoothly in a magnetic field. Think of a child's spinning top precessing under gravity. As it slows down, its angle shifts freely and continuously. That's what our common sense tells us should happen. But reality throws a curveball called quantized spin. This is a rigid, unbreakable rule dictating that a system's angular momentum is restricted to very specific, equally spaced values. For example, a particle with a spin of 1/2 is strictly locked to values like positive h bar over 2 or negative h bar over 2. There is no sliding scale, no in-between. And this really brilliantly captures what those discrete energy levels actually look like. When we switch on a magnetic field, that spin 1/2 particle is split into 2 distinct energy states. Notice how the path cleanly branches into an upper track and a lower track? There is absolutely zero middle ground there. It's a perfectly digital reality happening right at the atomic level. Section 2. Proving it. Stern-Gerlach. Moving from theory to reality. Now, we can't just run around claiming nature behaves this bizarrely without some rock-solid proof. Enter physicists Stern and Gerlach in 1922. They designed a beautifully elegant experiment using 3 basic steps. Evaporate silver in a hot oven to create a beam, shoot that beam through an extremely uneven or inhomogeneous magnet, and then collect the atoms on a simple glass detector plate. Based on the classical physics of the time, they fully expected to see a continuous vertical smear of silver painted across that glass plate. Instead, they witnessed the miraculous, undeniable failure of classical ideas. As you can see, the beam perfectly split into 2 distinct separate spots. The atoms were physically forced into either a spin-up or a spin-down state. No smear, just 2 distinct dots. Section 3. Tickling atoms with resonance. Inducing quantum jumps. So once we confirmed these lock states actually exist, the next obvious question was, how do we manipulate them? This brings us to the Rabi molecular beam apparatus. This thing is a massive upgrade from Stern-Gerlach. It was specifically designed to not just look at spins, but to actually reach in and flip them mid-flight. It pulls this off in 3 really clever steps. First, it splits the beam in magnet 1, just like we saw before. Step 2 is where the magic happens. We literally tickle the atoms using a weak, oscillating horizontal field in magnet 2. If we tune that frequency just right, we force the atoms to jump from one spin state to the other. And finally, step 3, magnet 3 deflects those newly flipped atoms completely out of the way. The big payoff is right here, at this sudden dip in the graph. The detector measures the current of atoms hitting it, right? And that current drops off a cliff exactly when our oscillating frequency perfectly matches the atom's natural wobble. That perfect match is what we call resonance. Hit that frequency, the atoms flip, they get deflected, and the detector current plummets. This little dip unlocked staggering levels of precision, giving us a whole new toolkit to decode the physical world. Section 4. Bulk magnetism and saturation. Zooming out to the macro scale. Okay, we've spent a lot of time on individual atoms. Let's zoom out and see what happens when you cram billions of these tiny, spinning magnets into a bulk material. Inside any solid object, there's actually a constant, invisible turf war going on. Heat causes thermal motion, constantly jiggling atoms around and fighting to randomize them. But against that, you have magnetic fields aggressively trying to force all those quantized spins into a perfectly straight line. And we can literally map out who's winning that battle. If you crank up the magnetic field to extreme levels, or drop the temperature super low to freeze out that thermal jiggling, you hit this flat plateau at the top right of the curve. That flat line is called saturation. It's the exact critical moment when every single subatomic magnet in the material surrenders and lines up in the exact same direction. Section 5. Cooling toward absolute zero, a thermodynamic trick. So what's the real-world application of knowing about bulk saturation? Well, we can use it to completely hack thermodynamics and reach temperatures near absolute zero. It's a brilliant trick called adiabatic demagnetization. Here's the playbook. Step 1. Hit the material with a massive magnetic field, so all the spins align. Step 2. Thermally isolate it so absolutely zero outside heat can get in. Step 3. Slowly turn off that magnetic field. Because the atoms are isolated, they have to pay an energy toll to flip their spins back to random directions. To do that, they steal their own thermal energy, literally cooling themselves down from the inside out. And the crazy part? Physicists chain this effect together. Stage 1 uses the magnetic moments of electron shells, which drops the temperature to mere thousandths of a degree. But we can go colder. Stage 2 targets the atomic nuclei themselves, which have magnetic moments 1,000 times weaker. By running a second round of demagnetization on the nuclei, we can literally freeze matter down to within 1/1,000,000th of a degree of absolute zero. Absolutely mind-blowing. Section 6. Nuclear magnetic resonance. The ultimate payoff. Which brings us to the ultimate technological flex of measuring these tiny nuclear moments. If we put a simple water sample inside a nuclear magnetic resonance, or NMR, apparatus and sweep the magnetic fields, our electronics let us actively watch those tiny hydrogen protons absorb power as their spins flip. We are directly detecting the resonance of the nucleus itself. And that leads us to a pretty profound realization. How does a highly abstract, totally unnatural subatomic math rule give us the power to peer inside the human body? Well, it turns out this exact phenomenon, detecting the discrete, quantized wobble of a proton in water, is the literal foundational science making modern MRI machines work. It is saving lives in hospitals everywhere. It just goes to show how understanding the tiniest, weirdest pieces of our universe can completely transform our everyday world. So what else are we going to unlock as we push further into the quantum realm? Something to think about. Thanks for joining me on this explainer. I'll catch you next time.
Welcome to This Explainer. Today, we're jumping right into a seriously fascinating journey. We're starting with something incredibly ordinary, the everyday magnets currently holding up that grocery list on your fridge, and we're going all the way down into the quantum mysteries you can't even see. You know, ferromagnetism feels so normal to us, but the moment you actually try to explain how it works, well, the physics gets wild very quickly.
So here's the fundamental question we're trying to figure out today. Why are some materials, like iron or nickel, fiercely magnetic, while other materials, sitting right next to them, feel absolutely nothing at all? I mean, it sounds like a totally simple question, right? But honestly, answering it is going to completely shatter our classical understanding of physics. We're going to have to look deep inside the structure of matter to figure out what's really going on.
What's genuinely amazing here is how we can visualize the invisible. If you were to take a cross-section of a magnetized iron rod, you'd see something pretty remarkable going on. Inside the material, there are all these tiny atomic currents circulating. Now, right in the bulk of the iron, right in the middle, each tiny current is sitting next to another current going in the exact opposite direction. So they just cancel each other out completely. But if you look at the outer edge, there's absolutely nothing to cancel out that outermost layer of current. So what you're left with is a massive net surface current wrapping around the entire rod.
Okay, let's dive into this a bit more. These tiny loops are called Amperian currents, named after the scientist Ampere who first proposed them. And what they reveal is actually profound. The macroscopic magnetism we feel, when two magnets snap together in our hands, is actually just moving electrical charges at the microscopic atomic level. Basically, a permanently magnetized bar of iron is effectively just a tightly wound coil of wire carrying a continuous electrical current. It's really all just currents.
Right, before we go any further, we have to navigate the horribly confusing world of physics units. Seriously, it's a complete mess. You've got the B field and the H field, and historically, scientists couldn't even agree on what to call them or how to measure them. For our journey today, just keep in mind that B represents the actual total magnetic field, while H is often thought of as the field we apply externally to try and magnetize the material.
Let's see how this builds when we actually apply an external magnetic field to a piece of soft iron. The magnetization curve here is highly nonlinear. You start applying a field, and initially, the magnetic field inside the iron shoots up incredibly fast. I mean, way faster than if there were just empty air there. But as you keep pushing, the curve starts to level off. The iron saturates. There's a hard physical limit to how much you can magnetize it, no matter how much external field you keep pumping in.
And here is the absolutely crucial point. Magnets actually have a memory. This phenomenon is known as hysteresis. When we turn that external field back down to zero, the iron doesn't just lose its magnetism. No, the iron remembers its past state and stays permanently magnetized. This is exactly how we create permanent magnets in the real world. The magnetic state of the material depends on its entire past history. It's a sort of locked-in magnetic memory.
This memory effect brilliantly illustrates what happens when we use alternating currents, like the ones in a transformer. Instead of pushing the iron all the way to saturation, we drive it in smaller, tighter loops back and forth. Because the iron has that hysteresis memory we just talked about, the path it takes when the field increases is completely different from the path it takes when the field decreases. That creates a loop, and here's the kicker. The area inside that loop represents energy that is completely lost from our electrical circuit and turned into heat inside the iron. That is exactly why your electronics and transformers get hot.
To control where these incredibly powerful magnetic fields go in the real world, human engineering really takes advantage of these properties. We shape the iron into things like C-shaped electromagnets or closed toruses. By doing this, we're essentially harnessing the iron's little slave magnets, those atomic currents we talked about earlier. A small electrical current in our wire tells the atomic currents to line up, which multiplies the field's power tremendously. The iron acts like a conduit, guiding and amplifying the magnetic flux exactly where we need it to go.
Now, this real-world engineering is incredibly useful for everything from electric motors to our entire power grid. But it brings us to a really profound mystery. We know the iron amplifies the field, sure, but what actually causes this immense, spontaneous magnetization deep inside the solid iron in the first place? Like, why do those atomic currents want to line up so strongly?
Well, deep down inside the atom, there is a constant, invisible battle raging. On one side, you have magnetic fields, either external ones we apply or just the fields from neighboring atoms, trying desperately to line up the electron moments, making them all point in the exact same direction. On the other side, you have random thermal motions. Heat is literally just atoms jiggling around, and that violent jiggling is constantly trying to derange the magnets and randomize their directions. The resulting balance between these two competing forces is what determines the material's overall magnetism.
Experimental data gives us a massive clue here. If you look at what happens to the spontaneous magnetization of nickel as the temperature drops, it's wild. As the material gets colder, the random thermal shaking slows down. Eventually, it slows down so much that the material spontaneously magnetizes itself, entirely on its own, without any external field being applied at all. The atoms just suddenly decide to all point in the same direction.
This sudden dramatic onset of magnetic behavior happens at a very specific point called the Curie temperature. Above this temperature, the thermal jiggling wins, and the material acts like a weak paramagnet. But below it, the magnetic forces win out and it becomes a strong ferromagnet. For nickel, this dramatic shift is observed in reality at exactly 631 degrees Kelvin.
Okay, let's play the role of classical physicists for a minute. If we use our classical physics equations to calculate what this Curie temperature should be based solely on the magnetic interactions between neighboring atomic magnets, we can run the numbers. We find the saturation magnetization, we set the mathematical slope of thermal alignment to 1, and we calculate our theoretical temperature. So what does the math actually say? Our classical physics equations give us an expected Curie temperature of exactly 0.24 degrees Kelvin.
And here is the spectacular plot twist. Our theoretical classical value is 0.24 Kelvin. The real, measured value in the laboratory is 631 Kelvin.
That means our classical math isn't just a little bit off, it is wrong by a massive factor of 2600. The forces lining up the atoms are 2,600 times stronger than what classical magnetic theory can possibly explain.
As the legendary physicist Richard Feynman himself stated, we just have to admit defeat here. Clearly, our magnetic theory of ferromagnetism is a dismal failure. The purely magnetic fields between atoms are nowhere near strong enough to overcome the thermal shaking at room temperature. This means some completely unknown, incredibly strong, non-magnetic interaction is what's actually forcing these atomic spins to line up. Classical physics is entirely broken here.
To make things even weirder, if you pick up a bulk piece of unmagnetized iron, it doesn't even seem to have these massive internal forces at work. Why is that? Because the iron is broken up into microscopic regions called domains. Inside each tiny domain, the atoms are perfectly aligned by these massive mysterious forces. But the different domains point in completely random directions, canceling each other out on a macroscopic scale, and perfectly hiding these massive internal forces from our everyday perception.
So, if classical physics can't explain that simple little magnet sitting on your fridge right now, what is the answer? Well, the true explanation lies in the Pauli exclusion principle and the bizarre world of quantum mechanics. It's an effect of electrons interacting at a quantum level, an exchange force that has absolutely no classical equivalent. Which leaves us with a final, provocative thought. If our classical models are this fundamentally broken when trying to explain a simple fridge magnet, what other quantum secrets are hiding in plain sight in our everyday lives? Thanks for joining me on this explainer, and I'll see you next time.
Welcome to this explainer. Today, we're going on an absolutely fascinating journey. We're going to trace the origins of something you probably interact with every single day, magnets. But to truly understand them, we have to start way down in the invisible, subatomic world of quantum mechanics, travel up through the microscopic architecture of metals, and finally arrive at the engineered materials that power our modern world. And honestly, the best part? We're going to see that despite centuries of intense study, some of the absolute most fundamental questions about magnetism remain a complete mystery. Let's get into it. Okay, let's dive into this. Here is the roadmap for our micro to macro journey. 1. The quantum origin of magnetism. 2. Inside the magnetic domains. 3. The jerky magnetization process. 4. Engineering magnetic materials. And 5. Exotic magnets and mysteries.
To kick things off, let's pose a really foundational question. Why are some things magnetic while others just aren't? I mean, it sounds like a simple question, right? But the answer is incredibly deep. As it turns out, nature generally hates being magnetic. The fundamental rules of physics actually force most materials to naturally resist having any net magnetism at all. So why on earth do materials like iron or nickel break this rule?
Part 1. The quantum origin of magnetism.
All right, so to answer our question, we've got to transition from our everyday world down into the quantum realm, specifically looking at the behavior of electrons' spin. You see, the general theory of ferromagnetism, which is that strong, everyday magnetism we see in iron, relies entirely on the spin of the electron. Basically, electrons act like tiny, microscopic magnets. Now, there's a strict rule in quantum mechanics called the exclusion principle, which essentially says two electrons absolutely cannot occupy the exact same state. If they get too close to each other, this principle heavily forces them to have opposite spins. One points up, the other points down. And when they point in opposite directions, their tiny magnetic fields just cancel each other out entirely. That right there is exactly why most substances in the universe aren't magnetic. But in special elements like iron, nickel, and cobalt, the incredible complexity of their atomic structure creates this strange double interaction. The conduction electrons buzzing around the outside actually trick the inner magnetic electrons into lining up parallel to one another. So instead of canceling out, their magnetic forces stack up.
Now, what's really interesting about this slide is just how fragile this quantum alignment actually is. Looking at this graph, you can see spontaneous magnetization on the vertical axis against temperature on the horizontal axis. As you heat a magnet up, you're pumping it full of thermal energy. This causes the atoms to jiggle around more and more furiously. And at a certain point, called the Curie temperature, that thermal jiggling completely overpowers the delicate quantum forces that are trying to keep the electron spins parallel. The spins become completely randomized, the curve just drops off a cliff, and the material suddenly loses its strong magnetic properties. But if you let it cool down, the spins snap right back into alignment and the magnetism returns.
But hey, let's embrace a little bit of scientific candor here. As much as we know about quantum mechanics, physics absolutely does not have all the answers yet. Even today, nobody can calculate the exact magnitude of that spin aligning force just by knowing that iron is element number 26 on the periodic table.
Furthermore, exactly how those atoms behave statistically right at the Curie point, right where they transition from magnetic to non-magnetic, remains a highly complex, unsolved problem in theoretical physics. The sheer interconnected complexity of nature still defies a complete mathematical analysis. Pretty wild, right?
Part 2. Inside the magnetic domains.
This brings us to our next level of scale. If quantum mechanics is magically making all the electron spins in iron line up parallel, we have to ask, why isn't every normal, everyday piece of iron acting like a giant, powerful magnet all the time? Well, the answer lies in the concept of magnetic domains. A domain is simply a localized neighborhood within the crystal where all the atomic magnets are perfectly aligned. You see, if a whole block of iron was aligned in just one single direction, it would project a massive magnetic field out into the space around it. But projecting that field takes a huge amount of energy, and nature is fundamentally lazy. It always wants to find the absolute lowest energy state possible. So the crystal actually spontaneously breaks itself up into these smaller, self-contained magnetized neighborhoods to save energy.
And this brilliantly illustrates exactly how that works. Look at the top block. That's a single, fully magnetized piece projecting a huge external field. To reduce that wasted energy, the crystal just splits right down the middle, creating a domain wall, with one side pointing up and the other side pointing down. It can even split further into multiple strips. But nature is way more clever than that. Look at the bottom diagrams. The crystal can actually create sideways pointing triangular domains right at the edges. In this configuration, the magnetic field essentially loops around continuously, perfectly contained inside the metal itself. There's zero external magnetic field. The piece of iron has basically neutralized its own macroscopic magnetism by hiding it all internally.
Of course, real-world iron isn't a perfect, beautifully organized single crystal. It's polycrystalline, meaning it's a messy jumble of many tiny crystal grains, each facing completely different directions, with their own internal axes of easy magnetization. And within every single one of those grains, there are multiple domains pointing this way and that. So, on a macroscopic scale, the kind we can see and touch, an everyday piece of iron is entirely unmagnetized because all of these millions of microscopic domains are perfectly canceling each other out.
Part 3. The jerky magnetization process.
Okay, so if the iron is happily sitting in this unmagnetized, low-energy state, what physically happens when we force this messy material into an external magnetic field? Well, when you apply a small magnetic field to a piece of iron, the domains that just happen to be lined up with your field start to grow. Their boundaries, those domain walls we talked about, literally physically move, eating up the domains that are pointing the wrong way. But because real iron is completely full of impurities, structural defects, and grain boundaries, these walls don't just slide smoothly. They get stuck on a microscopic piece of dirt, they hold, and then they snap forward when the magnetic pressure gets high enough. If you hook a coil of wire around the iron and connect it to a loudspeaker, you can actually hear this happening. As the source material beautifully describes it, it would sound something like the noise of sand grains falling over each other as a can of sand is tilted.
And that builds a really complete picture for us. On the right, you can see the schematic for that very loudspeaker experiment. And on the left, when we zoom in on the actual magnetization curve, you see it's not a smooth line at all. It's actually a staircase. This is called the Barkhausen effect. The microscopic jerks and snaps of the domain walls mean that magnetization is not a perfectly reversible, smooth process. Every single time a domain wall snaps past an impediment, it causes rapidly changing microscopic magnetic fields that create heat. And it even sends out tiny sound waves because the crystal is physically changing its shape slightly. It literally takes energy to drag those domain walls back and forth over those microscopic hurdles.
Part 4. Engineering magnetic materials.
Now, once physicists fully understood this jerky, messy domain wall movement, engineers realized they could intentionally design materials to exploit it. I mean, if you're building a transformer, you want the magnetization to flip back and forth incredibly easily without losing energy to heat. You want a soft magnetic material with almost zero impurities so the domain walls just slide with no friction. Check out the top row of this table. An alloy called supermalloy has a coercive force, which is the force needed to erase its magnetism, of just 0.004, barely anything. But what if you want a permanent magnet? You actually need the exact opposite. You want to intentionally stuff the material full of impurities and physical strains so the domain boundaries get permanently frozen in place. Look at the bottom row. The alloy Alnico V has a massive coercive force of 550.
So the crucial point here is that extremely wide shape you're looking at. That is the hysteresis loop for Alnico V. Hysteresis is basically the measurement of how much a material stubbornly resists changing its magnetic state.
Because El Nico V was engineered with a highly complex composition and is actually cooled inside a magnetic field during its creation, its domain walls are heavily trapped. Once you push it to full magnetization and turn the external field off, it stays magnetized. It takes a massive reverse magnetic field to push it back the other way, which is exactly why that loop is so incredibly wide. And that's what makes for a spectacularly strong permanent magnet.
Part 5. Exotic Magnets and Mysteries.
We've talked about soft and hard iron alloys, but nature is full of far stranger things. Take a look at how different elements manage their electron spins here. In column A, we have standard ferromagnetism, like iron, where all the spins desperately want to point up together. But look at column B. In materials like chromium, the quantum forces actually make the spins perfectly alternate, up, down, up, down. From its own internal perspective, chromium is highly organized and magnetic, but from the outside, the spins perfectly cancel each other out, leaving absolutely zero external magnetic effect. We call this being anti-ferromagnetic. But nature, in its infinite complexity, actually found a way to make alternating spins incredibly useful for us.
Enter the ferrites. Nature essentially found a massive loophole here. These are crystals made of oxygen and two completely different types of metal atoms. In these structures, quantum mechanics again forces the spins to alternate. Metal A points up and metal B points down. But here is the brilliant trick. The magnetic moment of metal A is inherently stronger than metal B. So even though they are fighting each other tooth and nail, the up spins overpower the down spins, resulting in a net leftover magnetism. The material is technically ferromagnetic, but unlike a chunk of iron, it's an electrical insulator. Because it's an insulator, high-frequency microwaves can pass right through it without causing massive heat-generating electrical currents. Without these exotic ferrites, a lot of our modern high-frequency technology, literally the microwave in your kitchen or the Wi-Fi router you're probably using right now, just wouldn't be possible.
So we have traveled all the way from the invisible quantum dance of electrons to the visual geometry of domains, right up to engineering permanent magnets and exotic microwave insulators. It kind of feels like we have magnetism completely figured out, doesn't it? Well, actually no. Despite this incredible array of practical and theoretical knowledge, there's a massive lingering blind spot right beneath our feet.
Think about the very first magnetic things human beings ever discovered. Amber rubbed with fur and naturally occurring magnetic rocks called lodestones. In all of our physics, with all of our talk of quantum exchange forces, Curie points, and domain walls, we still haven't actually explained why a piece of lodestone sitting in the dirt naturally becomes magnetized in the first place. Sure, we know it aligns with the Earth's magnetic field, but where does the Earth's magnetic field actually come from? The truth is, nobody really knows for sure. There are some good guesses involving molten iron in the core, but the exact physics remains an incredibly beautiful, entirely unsolved puzzle. We've built our entire modern technological world on the back of magnetic phenomena that, at their deepest planetary origins, we still don't fully comprehend. And honestly, I think that's what makes science so endlessly exciting. Thanks so much for joining me on this explainer, and keep wondering.
Welcome back to The Explainer. I'm absolutely thrilled you're joining me today because we're going to dive right in and demystify the hidden rules that literally keep our physical world intact. We're talking about the physics of elasticity. You know, the study of how materials give when they're pushed and exactly how they snap back into shape. It's essentially the secret language of every single solid object around us.
I mean, just think about this for a second. Why doesn't a towering skyscraper just crush itself under its own massive weight? We're talking millions of pounds of steel and concrete pushing down relentlessly, and yet it stands tall. How in the world do these materials handle those invisible, incredibly high-stakes forces without shattering into a million pieces? Well, the answer lies entirely in the mechanics of elasticity, and by the end of this explainer, I promise, you're going to see the structures around you in a completely new light. So here's our roadmap for today. First, we'll cover the rules of stretching. Second, pressure, squeeze, and shear. Third, twisting rods and earthquakes. Fourth, the physics of bending. And finally, number 5, buckling and structural failure. Let's get into it.
Part 1. The rules of stretching. This is the basics of give and take.
We've got to begin at the very foundation here. What exactly happens when we simply pull on a piece of material? Well, it all comes down to a fundamental principle called Hooke's law. Basically, if you push or pull on a piece of material, it deforms. If that force is small enough, the amount the material stretches is directly proportional to the force you're applying.
Physicists measure this using two main concepts. First, there's stress, which is just the force per unit area, and then there's strain, which is the fractional stretch. So Hooke's law simply tells us that stress equals a constant property of the material, which we call Young's modulus, multiplied by the strain.
Now, what's really interesting about this is if you picture a rectangular block stretching under uniform tension. You've got forces pulling on the ends, right? Causing its length to increase. As long as that extension is just a small fraction of the original length, we're usually talking just a few % before things actually break, the behavior remains perfectly elastic. You stretch it, it pulls right back. Simple enough.
But actually, there's a fascinating catch here, captured by something called Poisson's ratio. When you stretch a block of material lengthwise, it doesn't just get longer, it naturally thins out in its width and its height. Stretching in one direction basically causes a proportional contraction at right angles to that stretch. It's kind of like nature's way of balancing the total volume.
Moving on to part 2, pressure, squeeze, and shear, dealing with forces from all sides.
Okay, so we've got the simple pull figured out, but let's be real, the real world is messy. Materials rarely face a force from just one single direction. Take a look at the stark contrast here. On one side, we have uniform hydrostatic pressure. Think of a block submerged deep underwater in a pressure tank, where the force is pushing inward equally on every single face. But on the other side, we've got a state of pure shear. This happens when sliding, twisting forces distort a square into a diamond or a parallelogram. So instead of a simple squeeze, shear is all about planes of material sliding past one another. Let's zoom in on that hydrostatic pressure for just a second. To calculate the change in a block's length underwater, physicists do something pretty clever. They use the principle of superposition. Basically, they treat that complex all-around underwater pressure as the sum of 3 separate, independent longitudinal compressions. That's a push on the ends, a push on the sides, and a push on the top. By calculating these 3 relatively simple problems and just adding them up, we can find the total change in volume. That's the volume strain, and it's governed by a property called the bulk modulus.
Part 3, twisting rods and earthquakes, the motion of shear waves.
Imagine taking a heavy steel drive shaft in a machine, or maybe carefully turning a super delicate quartz fiber suspension in a lab. What exactly is going on inside that material? Well, if you take a long rod and suddenly twist one end of it, the whole thing doesn't just twist instantly all at once. Instead, that sudden twist sends a wave of torsion working its way down the entire length of the rod. It's a surprisingly dynamic process.
Let's break down the timeline of how that movement actually happens. First, your sudden twist creates a local torsional strain right at the end of the rod. Next, because the torque isn't uniform everywhere yet, there's a net torque that literally gives angular acceleration to just a tiny slice of the rod. And then Newton's laws kick in. This local acceleration triggers the next slice, and then the next one, propagating a one-dimensional shear wave right down the material. And the speed of this wave? That entirely depends on the density and the stiffness of the rod itself.
So, what does this all mean? Why does this matter outside of a highly controlled laboratory? Well, because the Earth itself is essentially a giant elastic body. When a fault line slips, it sends out both longitudinal compression waves and these exact transverse shear waves we were just talking about. Now, because longitudinal waves travel faster through rock than shear waves do, seismologists can measure the time delay between the two arriving at a single station, and they use that gap to calculate exactly how far away the earthquake is. Pretty amazing, right?
All right, part 4, the physics of bending, finding the neutral surface.
Grab a soft, rubbery eraser in your mind and just bend it. What are the forces doing inside that rubber? The hidden geometry here reveals that when you bend a bar, the material on the inside of the curve gets squished. It's under compressional strain, and the material on the outside curve, that gets stretched. But right in the middle, running perfectly parallel to the axis of the bar, is a surface that is neither stretched nor compressed. It's completely untouched. In physics, we call this middle layer the neutral surface.
And knowing that brilliantly illustrates why our world is built the way it is. Think of any construction site you've ever walked past. You almost always see steel beams shaped like a capital letter I. Have you ever wondered why? It's because to make the stiffest possible beam using a specific amount of material, you want to put as much of that material as far away from the neutral surface as possible. The further the mass is from that untouched middle line, the higher the moment of inertia and the stronger the beam is against bending forces. It's such an elegant engineering trick. Which brings us to part 5, buckling and structural failure. This is when the math breaks down. We've seen how materials can successfully handle stretching, twisting, and bending. But what happens when the stakes get raised and the math kind of breaks down? There is a massive, massive difference between safe bending and catastrophic buckling. Safe bending creates these predictable, gentle curves that engineers can easily account for. But imagine a massive space rocket sitting on a launch pad. It has to be incredibly light to actually fly, but strong enough to hold its own weight. If the downward force of its weight exceeds a specific threshold, which we call the Euler force, the supporting columns won't just bend a little bit. They will suddenly and violently buckle, leading to a total collapse.
Picture a straight rod being pushed from both ends. For small amounts of force, nothing visible really happens. It holds up. But the absolute instant that critical Euler force is surpassed, the rod suddenly gives way, bowing out into a massive curve. It's a sudden failure. And in structural engineering, sudden failure is literally the ultimate enemy. There is no warming.
And this brilliantly illustrates what happens if we push the math of this buckling far beyond the normal limits, basically allowing the displacements to get incredibly large. The rod forms these beautiful, looping, chaotic shapes known as elastic curves. But what's absolutely mind-blowing here is that the differential equations describing these wild loops are the exact same equations that describe the large swings of a pendulum. It just goes to show how the underlying math of our physical world is deeply, deeply connected. Which brings us to the end of our journey today. From the simple stretching of a metal block, to the twisting shear waves of an earthquake, to the absolutely critical math preventing a skyscraper from buckling under its own weight, elasticity is really the silent guardian of our physical reality. So the next time you cross a steel bridge or watch a rocket launch, will you see the hidden forces holding it all together? I hope you'll look just a little bit closer. Thanks so much for joining me on this explainer, and as always, keep your curiosity alive.
Welcome to this explainer. Today, we're diving straight into the surprisingly fascinating physics of how things stretch, bend, and break. You might think you have a pretty good handle on how solid objects work, but today we're going to pop the hood on reality. We're going to uncover the incredible, hidden mathematical mechanics that govern literally every material around us. Think about this everyday mystery for just a second. If you take a standard piece of blackboard chalk and pull it straight apart, it snaps with a perfectly flat break. Simple enough, right? But if you take that exact same piece of chalk and twist it, it suddenly breaks along this complex diagonal angle. Why on earth does it do that? Well, stick around, because by the end of this explainer, you'll know exactly what invisible forces are at play here, and honestly, you'll probably never look at a broken object the same way again. To solve this mystery, we'll hit 5 quick stops today. Inside the jello to understand strain, the tensor of elasticity, motions and polarized light, the breaking point of non-elastic behavior, and finally, atomic springs and elasticity.
All right, let's jump right into section 1, inside the jello, understanding strain.
Okay, picture a massive, wobbly block of jello. If we want to really grasp how a material distorts, we need a reliable way to measure that distortion locally at any given point. So imagine we're keeping our eyes on a tiny speck of dirt stuck right inside our jello block. We can actually track the local strain by seeing exactly how that single speck moves from its original starting point to a brand new position the second we squash or twist the block. That displacement vector, that is the absolute foundation for figuring out what's happening on the inside. And tracking that speck shows us that there are really just 2 fundamental ways this jello can deform. You've got your homogeneous stretch, which is basically just pulling the material uniformly in one direction. And then you've got shear strain, where a tiny square of the material gets warped sideways into a parallelogram. The cool thing here is that literally every complex distortion you can imagine is just a mashup of these basic stretching and shearing motions. Now, here's the catch, where the math gets a little tricky. If our whole block of jello just rotates in space, like tumbling through the air without actually squishing or stretching, the relative positions of the atoms inside don't change at all. A pure rotation means there is 0 actual strain. So we've got to be really careful to build our mathematical definitions so they completely ignore simple rotations and only measure true structural distortion. Which brings us nicely to section 2, the tensor of elasticity. So we've got the strain figured out. But now we have to figure out how these strains relate to the internal forces, the stresses that are pushing back. Hooke's law, as you probably know, tells us that stress is proportional to strain. But here's the kicker. Because we're dealing with 3 dimensions of stress interacting with 3 dimensions of strain, the math just absolutely explodes. Initially, we are looking at a terrifying 81 different coefficients just to describe a single material's elastic properties. Imagine trying to calculate the structural integrity of a massive bridge using 81 variables for every single piece of steel. It's a nightmare. But thankfully, nature absolutely loves symmetry. And by applying mathematical symmetry, we can systematically collapse this giant problem. First off, because stress and strain are symmetric tensors, bam, those 81 constants drop to 36. Then, if we look at something like a cubic crystal, its physical properties are identical whether you rotate it 90 degrees or reflect it like a mirror. That drops our number down to just 3. And for a non-crystalline isotropic material, like a solid chunk of metal or plastic, the symmetry is perfect in every single direction, plummeting our coefficients all the way down to just 2. So what started out as a complete mathematical headache simplifies perfectly into just 2 constants. We call these the Lemay elastic constants, represented by the Greek letters mu and lambda. Just 2 numbers, that's it. Those 2 numbers completely define exactly how any uniform, non-crystalline material will behave under stress. Kind of mind-blowing, right?
Let's keep moving. Section 3, motions and polarized light.
So how do we actually measure these invisible internal forces out in the wild, especially when engineers are designing crazy complex shapes? We can't always calculate them easily, but we can visualize them. If you take a clear plastic, like lucite, and put it under stress, it becomes birefringent. That means you can literally shine polarized light right through it and see the internal stresses. The internal tension physically twists the plane of the polarized light, highlighting exactly where all those hidden, dangerous forces are concentrating. It's like X-ray vision for mechanical engineers. And these internal forces don't just sit there holding tension. They totally dictate how motion travels through the material. Those 2 constants we talked about, mu and lambda, they cause waves to split into 2 very distinct camps. You get compressional waves, which push and pull to change the material's density, just like sound waves. And you get shear waves, which move transversely, side to side, without changing the density at all. But what happens when things go wrong? Section 4, breaking point, non-elastic behavior. Hooke's law is great, sure, but it's really just an approximation for small, manageable strains. You pull hard enough, and that nice, neat linear relationship completely breaks down. The material stops fighting back proportionally, the internal structure yields, and eventually, snap. It reaches its breaking point. And right here is the answer to that chalk mystery from the very beginning. Chalk is basically just packed particles, making it way weaker in tension when being pulled apart than in shear. So you pull chalk, it breaks flat. Easy. But when you twist it, you're introducing this intense, complex shear. And mathematically, shear is basically just tension and compression acting together at 45-degree angles. So that twist actually creates a massive amount of diagonal tension, and boom, the chalk fails right where that tension hits its peak, giving us that beautiful, complicated diagonal break. But snapping in half isn't the only way materials get weird. Think about a crumpled piece of plastic wrap slowly, almost magically unfolding itself over time. It's a bizarre memory effect. To understand it, picture microscopic, stiff fibers trying desperately to spring back to their original shape. But to do that, they have to fight against a viscous liquid, slowly squeezing it back into tiny hollow cells. It is a literal microscopic battle between internal tension and internal viscosity. Which brings us to the grand finale, Section 5, Atomic Springs and Elasticity. We're zooming all the way down to the atomic level now. Where does all this macro-level stretchiness actually come from? Well, the atoms themselves. We can calculate elasticity by imagining that every single atom in a crystal lattice is connected to its closest neighbors by tiny, invisible linear springs. The atomic bonds literally are the springs. So when you deform that massive chunk of crystal or metal, you're actually stretching billions and billions of these microscopic springs. By mapping out the exact geometric displacement of every nearest and next nearest neighbor atom, we can mathematically add up the tiny bits of energy stored in every single one of those atomic springs. And that gives us the total macro energy of the whole object. It's like the universe's most incredibly complex jigsaw puzzle coming perfectly together. And the best part? The real-world experimental data completely backs this up. For simple ionic crystals, like sodium chloride, our theory predicts that 2 specific elastic constants should be mathematically identical. And in the lab, they practically are. Now, it does get a bit messier with stuff like diamond, because those complex covalent bonds introduce tricky sideways forces that our basic linear spring model misses. But the fundamental foundation is absolutely rock solid. So, to tie it all together, we've gone from massive, 81 coefficient strain tensors down to just 2 numbers, all thanks to the sheer elegance of mathematical symmetry. And we've traced the everyday stretch, bend, and snap of the things you hold in your hands right down to the microscopic atomic springs that hold our universe together.
It really makes you wonder, doesn't it? If a crumpled up piece of plastic wrap relies on this much hidden mathematical beauty and complex internal machinery just to remember its own shape, what other invisible atomic forces are secretly shaping your reality right now? Keep asking questions, keep observing, and thanks for joining me on this explainer.
Welcome to This Explainer. Today, we're going to explore Richard Feynman's brilliant breakdown of how we try, and ultimately fail, to perfectly model the flow of fluids using mathematics. It's this absolutely fascinating story of human ingenuity hitting a brick wall when it meets natural reality. Let's dive right into this beautiful opening thought from Feynman. He compared our strict mathematical equations to a child trying to stubbornly corral water in a mud puddle. You know, as we get older, we're still mesmerized by streams, waterfalls, and whirlpools because fluids almost seem alive compared to solid objects. And for centuries, we've tried to essentially dam the water up in our minds by writing the perfect laws to describe exactly how it flows. We've got a really fun journey ahead today. We'll be covering 1. Welcome to dry water, 2. Fluids at rest, 3. The rules of flow, 4. Bernoulli's beautiful theorem, 5. Circulation and lift, and finally, 6. The vortex paradox. Let's jump in. Welcome to dry water, the perfect assumption. So, to make the incredibly complex math actually work, physicists often study an idealized, entirely friction-free liquid. The great mathematician John von Neumann playfully characterized physicists who did this as studying dry water. We basically temporarily ignore the messy reality of elasticity, that internal friction that makes honey pour slower than tea. We also assume our fluid is completely incompressible, meaning its density never ever changes. It is a pristine, mathematically perfect substance. Section 2. Fluids at rest. The basics of hydrostatics. Now, without any shear forces in a resting fluid, the pressure stress on any imaginary surface inside it is exactly the same in all directions. It's pretty cool. No matter which way you tilt those tiny imaginary planes, the pressure force is always going to be perfectly perpendicular, or normal, to the surface. If we mentally isolate a tiny little cube of water, a net force only exists when the pressure actually changes from one side to the other. If the pressure is identical on the left and right, well, the cube doesn't go anywhere. But if the pressure is higher on the bottom than the top, that creates a gradient. That upward force perfectly balances against external forces like gravity, which is exactly why the water doesn't just collapse in on itself. Section 3. The rules of flow, setting things in motion.
Let's get things moving. If the flow is steady, meaning the velocity at any specific point literally never changes over time, we can map it out using these elegant paths called streamlines. Think of them like invisible train tracks for the fluid particles. The fluid just continuously replaces itself, following those exact unchanging tracks perfectly. But water doesn't just flow straight, right? It swirls. It rotates. We measure this local rotation with a super powerful mathematical concept called vorticity. Basically, imagine dropping a microscopic speck of dirt into the water. If that speck starts spinning on its own axis as it travels along, boom. That means the fluid has vorticity at that location. Section 4. Bernoulli's beautiful theorem. Energy conservation in fluids. Okay, before I throw any math at you, I want you to ask yourself a quick question based on your own intuition. If you hold 2 parallel sheets of paper, maybe an inch apart, and you blow a fast stream of air right between them, what happens? Do those sheets blow apart from the force of the air, or do they mysteriously pull together? Seriously, take a second and think about it. If you actually try it, they pull together. No way, right? But why? It's because the faster moving air between the sheets has lower pressure than the still air on the outside. This is a beautifully simple real-world application of Bernoulli's theorem, which is basically just the law of conservation of energy applied to fluids. If the fluid speed goes up, its pressure simply has to go down to keep the total energy balanced along that streamline. And this brilliantly illustrates Bernoulli's principle in action across totally different scenarios. Whether water is converting potential energy from its height in a tank into kinetic energy as it jets out the bottom, or it's flowing through a horizontal pipe that suddenly gets narrow, the rule holds. To get the same amount of water through that narrow gap, it has to accelerate. And, as we just learned, speed goes up, pressure drops. It's that simple.
Section 5, circulation and lift, making things fly.
Now let's combine things. Because our math equations for ideal fluids are linear, we can take a straightforward horizontal flow and literally just add a circulating flow right on top of it. The result is honestly pure magic. The fluid moving over the top of the cylinder speeds up because it's moving with the circulation. The fluid on the bottom slows down because it's fighting it. Faster air on top means lower pressure on top. And what does lower pressure on top give us? Lift, a net upward force. You've absolutely seen a similar rotational effect in your own bathtub. As water moves inward toward the drain, the conservation of angular momentum forces it to spin faster and faster. Just picture an ice skater pulling her arms in to spin in an absolute blur. It creates that wonderfully familiar swirling vortex right over the drain. Section 6, the vortex paradox, when the model breaks. Here's where things get wild. According to Helmholtz's mathematical laws governing our pristine, dry water, vortex lines are completely glued to the fluid particles. They move perfectly with the fluid. More importantly, they never start and they never stop. According to these flawless equations, you can theoretically never create rotation in a fluid that's perfectly still, and you can never, ever destroy it once it starts. Watch what happens to a bundle of this fluid as it gets stretched out. As it elongates, its cross-section naturally shrinks. Because the vortex lines are glued to the material, they get packed tighter and tighter together. This means the vorticity has to increase to keep the total angular momentum perfectly balanced. It's like a mathematical lock, totally unbreakable. But then we look at reality. You can build a simple drum with a hole in one end and a rubber diaphragm on the other. If you fill it with smoke and give that rubber a good smack, you'll shoot a perfect, swirling smoke ring right out of the hole. That invisible bundle of swirling vortex lines is so incredibly stable it can literally blow out a candle 20 feet away. And this right here exposes a fatal flaw in everything we've done so far. If we started with completely still air inside that box, our dry water equations say it is physically, mathematically impossible to ever generate that smoke ring. The math firmly dictates that if vorticity is 0, it must remain 0 forever. Plus, dry water supposedly slides perfectly past solid walls, but in reality, a fluid's velocity is always 0 right at the boundary of a solid object, all because of friction. And so, we are left with this really profound realization. Our beautifully structured, perfectly frictionless model of dry water is fundamentally broken. It simply cannot explain the smoke ring. We are left craving the messy, frictional reality of wet water to finally solve the mystery of how fluids actually move in the real world. Think about that the next time you see a smoke ring or a whirlpool. You are literally watching nature break our simplest mathematical rules. If perfect math can't explain a simple puff of smoke, what other everyday miracles are hiding just beyond our equations?
Hey everyone, welcome back. I am absolutely thrilled to have you here for this explainer. Today, we're going to uncover a truly profound concept. We're going to look at how the chaotic, unpredictable, and just breathtaking beauty of the physical universe actually stems from incredibly simple rules. We're going to see how a few basic equations can hide literally infinite complexity. And to do this, we're going to explore the fascinating everyday physics of what we call wet water. Okay, let's dive right into this with a question you've probably asked yourself while cleaning up around the house. Think about a ceiling fan or a little desk fan. Even though those blades are slicing through the air at really high speeds, just churning up a storm, they always manage to collect this thin, super stubborn layer of dust that just will not blow off. I mean, why is that? Well, it actually reveals a totally counterintuitive fact about reality. Fluid velocity, and remember, air is a fluid just like water, goes to exactly 0 right at the surface of a solid object. No matter how fast that blade is moving through the air molecules directly touching the blade aren't moving relative to it at all.
And that zero velocity boundary brings us directly to our key definition for today, viscosity. Put simply, viscosity is the internal friction inside a moving fluid. Now, in purely theoretical dry water, physicists pretend this friction doesn't exist to make the math easier. But in the real world of wet water, fluid layers resist sliding past one another. Because that very bottom layer of air is stuck to the fan blade at 0 velocity, the next layer up has to drag across it, and then the next layer drags across that one, and so on. This viscous friction is precisely the reason that microscopic dust stays completely glued to the blade.
And this brilliantly illustrates how we actually measure that internal friction. Imagine water trapped between two solid flat surfaces. Say the top one is moving and the bottom one is completely stationary. We can actually measure the force required to keep that upper plate moving. And that shear force isn't just random. It's perfectly proportional to the area of the plates and the velocity, divided by the distance between them. That constant of proportionality, that's what we call the coefficient of viscosity. If you picture a tiny rectangular cell of fluid, the shear stress across it is driven entirely by how fast the velocity changes from one microscopic layer to the next.
Section 1. Enter the Reynolds number, the master scale.
Now, you might be thinking, okay, we've got fluid density, velocity, the size of the objects, and now this viscosity coefficient. That is a lot of math to juggle. But don't worry, we aren't going to get bogged down in equations here. Instead, we have one unifying master scale that dictates almost all fluid behavior. To get why this is so powerful, imagine an aerospace engineer. They need to know how a massive, full-scale airplane wing is going to behave at cruising altitude. Do they have to build the entire giant plane just to test it? No way! Because all of those complex variables we just talked about, the air's velocity, the size of the wing, the density, the viscosity, they all magically condense into one single parameter. If you match this one parameter, a tiny plastic model in a wind tunnel experiences the exact same fluid flow as a real jet airliner up in the sky.
So the absolutely crucial point here is this parameter itself, which we call the Reynolds number. It's a dimensionless number, and the rule it gives us is incredibly simple but insanely powerful. Any two situations with the exact same Reynolds number will look identically the same in their flow behavior, both mathematically and physically. You could be comparing water flowing around a tiny pebble to air flowing around a massive skyscraper. If the Reynolds number matches, the shape of the flow is exactly the same.
Section 2. Visualizing complexity, the cylinder experiment.
To really grasp what a massive difference this master scale makes, we're going to visually scale up the Reynolds number on one specific, simple shape, a solid cylinder. We're going to watch how the fluid completely transforms from something perfectly smooth into absolute chaos. First, let's start very low. When the Reynolds number is less than 1, the fluid velocity is extremely low or the fluid is incredibly thick and viscous. Think of slowly pushing a cylinder through a vat of honey. The flow lines part perfectly around the cylinder and smoothly, beautifully rejoin right behind it. It's perfectly steady. This elegant, symmetrical flow was actually mathematically solved by the physicist George Stokes, and it's the exact same physics that governs how tiny grains of dirt settle down in a centrifuge.
Now let's move to the next level and see how this builds as we crank up the Reynolds number. As the fluid speeds up and we hit a Reynolds number of, say, around 10 at 30, that perfect, smooth symmetry suddenly breaks. The fluid moving past the cylinder creates a pair of distinct circulating vortices right behind the object. But at this stage, they're stationary. They just sit there, spinning gently in the wake, permanently trapped behind the cylinder.
But wait, look what happens to the flow pattern as we keep pushing that speed even higher. We see a sudden, really dramatic shift at a Reynolds number of just over 40. Suddenly, those stationary vortices get too long, they snap off, and they go traveling downstream. Then the fluid curls around and makes a brand new one on the opposite side. They peel off alternately, creating this gorgeous left-right-left pattern known as a Kármán vortex street. The whole system completely changes from a steady flow to a regular, cyclic, pulsing flow. And if we push it all the way past 100,000, it becomes a turbulent boundary layer. The flow lines are twisting and turning in all three dimensions. It becomes totally chaotic, unpredictable, and noisy.
Now, what's really interesting about this slide is how this chaos actually affects the physical world. When we map out the drag coefficient, which is the resistance the cylinder feels as the Reynolds number goes up, you'd logically expect that as the fluid gets faster and more violently chaotic, the drag force pushing against the cylinder would just keep climbing, right? But look what happens at the far end of the scale. At highly turbulent, totally chaotic speeds, right around a Reynolds number of 100,000, the drag force actually plunges. It drops drastically. Nature is just full of these bizarre, counterintuitive surprises.
Section 3. Chaos between two cylinders. Couette flow.
Now you might wonder if this vortex chaos is just some weird quirk of pushing fluid past a stationary obstacle. Well, to prove this variety of flow happens everywhere, let's look at an entirely different setup, couette flow. Think of an experiment where fluid is trapped between two concentric glass cylinders. Literally a cylinder sitting inside another cylinder.
If we fill the gap between them with fluid, maybe add a little aluminum powder so we can actually see the movement, and start spinning the inner cylinder, something truly fascinating happens. The inner layers of fluid move faster than the outer layers, which means they get pushed outward by centrifugal force. Exactly like you feel pushed against the door when you take a sharp turn in a car. But they can't easily move out because the outer layers are blocking the way. So, to balance out the pressure, the fluid physically breaks itself apart into these distinct, highly structured horizontal bands, almost like convection currents in a room with a hot radiator.
And here is where it gets deeply, deeply mysterious. As we increase the rotation speed, those straight horizontal bands suddenly become wavy, and those waves actually travel around the cylinder. Now, you would naturally think the speed of these waves would come from some incredibly messy, complex calculation, but experimental measurements show they travel at exactly 1/3 the speed of the inner cylinder. Exactly 1/3. That's a perfectly simple fraction that incredibly modern science and all our current mathematical capabilities still cannot fully explain. And if we spin it even faster, this beautiful wavy structure just completely breaks down into total chaotic turbulence.
Section 4. Simple equations, infinite complexity.
I actually want to slow down for a second here, because everything we've just discussed, the sticky boundary layer of the fan blade, that alternating Kármán vortex street, the crazy dramatic drop and drag, and the mysterious 1/3 wave speed between the spinning cylinders, literally all of it comes from the exact same fundamental equation of fluid dynamics. It points us toward one of the most profound realizations in all of science. To really capture the magnitude of this, I want to share a brilliant quote from the legendary physicist Richard Feynman. He wrote, "Unaware of the scope of simple equations, man has often concluded that nothing short of God, not mere equations, is required to explain the complexities of the world. All of this staggering visual chaos, the barber pole turbulent bands, the spinning vortices, they are entirely contained within one simple set of fluid equations. The problem isn't that the universe is doing something magical outside the math. The problem is that we human beings simply don't have the mathematical power yet to fully unpack everything that's hidden inside those equations."
Feynman goes on to say, "The next great era of awakening of human intellect may well produce a method of understanding the qualitative content of equations." Think about the massive implications of this for a moment. If the simple hydrodynamic equations for a nearly pure hydrogen gas contain within them the swirling nebula, the sunspots, and the explosive galaxies of our entire cosmos, and if the simple equations of water flow contain the chaotic turbulence we just looked at, imagine what else is hidden out there. We possess the simple equation for quantum mechanics. Is it possible that hidden inside that short little mathematical sentence are the intricate complexities of frogs, of musical composers, of morality, and perhaps life itself? We just don't know how to extract them yet.
So what you should really take away from this explainer is a profound sense of awe. When we look at a flowing river or a rising plume of smoke from a campfire, we aren't just seeing randomness. We are witnessing the infinite variety and novelty that can be generated from incredibly simple principles. It leaves us with a pretty compelling final thought. If all this breathtaking complexity hides in a simple equation for wet water, what other unimaginable secrets are just sitting there waiting to be discovered, hiding in the fundamental equations of the universe? Thank you so much for exploring this with me today. Keep asking questions, keep looking closely at the world around you, and as always, keep learning.
Welcome to this explainer. Okay, today, we're going to demystify one of the absolute most mind-bending ideas in all of physics, Einstein's theory that gravity, well, it isn't actually a force pulling on you at all. It's literally just the curvature of space and time. Now, to wrap our heads around our massive 3D universe, we kind of have to admit our own lack of imagination. We can't just step outside the universe to see its overall shape, right? We're trapped inside the whole shebang. So we have to act like a blind bug trying to figure out the shape of its world strictly from the inside. So how do you measure a curve you can't even see? Let's find out.
Picture this bug living on a sphere. Since it doesn't have eyes and has zero concept of up or down in a 3D sense, it naturally just assumes its world is perfectly flat. I mean, it makes sense, right? It only feels the surface right beneath its feet, just going about its day assuming the rules of a flat world totally apply.
Okay, let's complicate things a bit with a second bug. Imagine this one hanging out on a flat, hot plate that's freezing cold right in the center, but gets hotter and hotter toward the edges. But here's the catch. The bug and its measuring rulers physically expand as they move outward into the heat. But since they're expanding together, the bug never even notices the change.
Now watch what happens if both of these bugs try to just walk the shortest distance between 2 points. The bug on the normal flat plane walks what you and I clearly see as a straight line. But the bug on the sphere? It walks an arc of a great circle. But remember, to that bug, because it can't look up or down, it feels perfectly 100% straight.
And this is exactly what brilliantly illustrates the problem. If the bug on the sphere tries to do geometry, say it tries walking 4 100-inch lines separated by perfect 90-degree right angles, look at what happens. The endpoint literally doesn't touch the starting point. The square just completely fails to close.
And fascinatingly, the bug on the hot plate discovers the exact same geometric failure, because those expanding rulers trick it into drawing longer lines that curve outward into the warmer areas. It draws lines that just won't connect into a closed square. The geometry mimics a sphere perfectly.
So here's the absolutely crucial point to take away from this. We don't need to actually see space bending from some impossible, godlike outside perspective. We can define curved space purely from the inside, as any space where standard geometric rules, like the angles of a triangle or the lines of a square, just completely break down.
Let's scale this up to our own 3D reality. It brings up a huge question. If we act exactly like the bug and we lay out massive geometric shapes across our universe, do the standard rules of geometry actually hold up, or do they fail, just like our bug's square?
Astonishingly, no, they don't hold up. Listen to this. If you measure the surface area of the Earth, calculate the expected mathematical distance to the center, and then compare it, the actual physically measured radius is exactly 1.5 millimeters longer than it geometrically should be. Just think about the sheer massive size of the Earth for a second. That tiny 1.5 millimeter difference completely shatters the rules of standard geometry.
This absurdly specific 1.5 millimeter excess radius proves Einstein's law. Matter acts a bit like a heavy bowling ball sitting on a trampoline. It creates a local dent or curvature in space wherever there's a really heavy mass, like the Earth or the Sun. It is literally physically stretching the geometry of space.
But of course, Einstein didn't just stop at 3D space. He boldly brought time into the mix using something called the principle of equivalence. He basically asked, hey, if you were locked inside a box without any windows, could you actually tell the difference between accelerating upward in a rocket and just sitting perfectly still in a gravitational field on Earth?
To see why this matters, imagine you put a ticking clock at the front of an accelerating rocket, and you sit all the way at the back. Well, that front clock will actually appear to run faster. Why? Well, because the light flashes from the clock have a shorter distance to travel to reach you, since the ship is constantly speeding up toward those flashes.
And since acceleration and gravity are entirely equivalent, this leads us to a seriously mind-blowing reality. A clock sitting on a high shelf on Earth genuinely ticks faster than a clock sitting on the floor. Gravity literally alters the speed of time depending on your altitude. Actually, scratch that. It means your head is aging slightly faster than your feet. How wild is that?
So just like our blind bug's feeling square earlier, if we try to draw a geometric rectangle using height and time, the lines don't connect. The top of the rectangle stretches out, because as we just saw, time moves at different rates, at different altitudes, meaning space-time itself is structurally curved.
Let's play a little game with this new knowledge. If you toss a clock from point A to point B, and you wanted to record the absolute maximum amount of elapsed time during its trip, what path should it take? Now remember, going higher speeds time up, but moving too fast actually slows time down.
Well, the math shows that dipping upward into the weaker gravity to gain faster time while perfectly balancing the slowdown from your travel speed results in a parabolic curve. And what is that exactly? It's the exact natural path of a freely thrown ball. This completely rewrites Isaac Newton's whole concept of gravity. Objects aren't being pulled downward by some mysterious invisible force at all. They are simply taking the most efficient, straightest possible path of maximum time through a curved space-time geometry. And we know for a fact that this mind-bending geometry is real because it perfectly predicted Mercury's strange shifting orbit. It predicted the bending of distant starlight around the sun, and it predicted the fact that astronaut Gordon Cooper's watch literally recorded a later time while orbiting high above the Earth. So, boiling it all down, the two great laws of gravity in this explainer are beautifully simple. First, the mass of an object determines exactly how severely spacetime bends. And second, objects move simply by following the natural geometry of those bends to maximize their proper time.
We know the Earth creates a local curve for sure, but astrophysicists are still out there measuring distant galaxies today to answer the ultimate question. If mass bends space, what is the geometric shape of the entire universe we live in? Is it open, closed, or perfectly flat? Next time you look up at the night sky, just remember, that is the grand cosmic mystery we are still trying to solve.